think so. Hello, can someone confirm in the Zoom that you can hear me?
Yeah, I can hear.
Yes, I can hear you.
Okay, great, thank you. Hello, okay. Okay, so can everybody hear me well in the room? Okay, that's great. So sorry for the small delay here. My name is Matthias de Lange from CLVision, and it's my pleasure to introduce you today to the workshop of Continual Learning in Computer Vision, CVPR 2022. So let's dive right into it. What is continual learning? There are different terms based on the context and different fields, sometimes referred to as continual, lifelong, endless, never-ending learning. And what we try to do is to really get away from this static learning, from a static data set that we collect, train offline, and then have our deployment phase. What we try to do is actually interact or collect data from our environment or world and try to accumulate this knowledge through the lifetime of our learner. And this is what the workshop is all about. So we have a lot of topics covered today. We'll look at real-world applications. Can we do self-organization, continual learning? What's the role of sparsity? What about post-deployment continual learning? We'll also look at different priors we can use for knowledge adaptation and so much more. So continual learning is very interdisciplinary. So we have fields like transfer learning, domain adaptation, open world learning, and so on. You can all see it on the slide. And that's not limited to this list, of course. And having so many, such an interdisciplinary field and environment, we think that requires community. So we are here to have the discussion, the scientific discussion, and also look where are we now in the state of the art, which directions can we go in the future. So we have a very busy schedule today. We have, so also put some in the front. You can also find it on the website. If you have any questions, also contact any of us about the schedule. We will have an amazing list of speakers. We have live poster sessions and oral presentations. So we had 47 submissions this year, from which 32 were accepted, and all of this content will be presented here to you on this workshop. We also have a very nice challenge. So we have the Ego objects data sets provided by Meta, and we look at both classification and detection tracks in continual learning. So mostly classification had been considered, and we're also extending this to these detection benchmarks. So stay tuned and check out the program if you want to check that out. So how can you participate? Well, if you're live here, everything will just be here at this location. For the posters, you can explore in the main expo halls during the coffee breaks, and there will also be like the catering. If you're virtual, this is for people that are registered. You can follow the workshop, and we got the sound connected, so you can also put ask questions through Zoom. So, and again, all info is on the website. You can exit it here with the QR code or on the CVPR website. And then the most important thing, yes?
Comment, the posters are not on the expo floor. They're past the free return for lunch and coffee. You gotta keep going down that hall, and then they're on the right-hand side. They're not the expo.
Okay, cool. So, okay, thanks for the update. So the posters will be, I think, hall D and E, where like yeah, all of the catering is also happening. So you'll find them when you see them. So then the most important thing is also to enjoy this workshop. We'll have a lot of fun today discussing continual learning, all different perspectives. And now Antonio Carta will introduce our first speaker. Thank you.
So the first invited speaker of the day is Tyler Hayes. Tyler recently defended her PhD at the Rochester Institute of Technology, where she worked under the direction of Christopher Cannan. And her interests include lifelong learning, streaming environments, and continual learning for embedded systems, among many other things. So she also won the Best Paper Award for the first edition of the CLVision workshop. And I'm very excited to have here Tyler to start the day. Tyler, the stage is yours. Oh. Sorry. Yes.
All right, great. Thank you so much for the introduction. Good morning, everybody. I'm excited to be here and talk about continual learning with all of you. As Antonio mentioned, I'm Tyler Hayes, and today I'll be pleased to present real-world considerations and applications for continual machine learning. So let's start off by talking about the supervised machine learning paradigm. Given a set of data, we can split it into various partitions, like a training and a testing set that often come from the same underlying data distribution. We can then spend time training the system in an offline way on this static training set, which often, if you're using a deep neural network, means we're spending time batching and looping over the data set many times. We can then perform a separate testing or evaluation phase where we can determine how well our performance of the model is. If our performance looks good, then we can deploy the system. But what happens when we obtain more data? This is exactly where continual learning comes into play. So we're updating a network with new data as it becomes available, which means we're training our systems from evolving training streams. This more closely resembles the natural world and how we as humans and animals are constantly learning from an evolving stream of data. Because we're learning from this evolving stream, there's often temporal correlations, and we can't necessarily assume that our input distribution is independent and identically distributed. But this is typically what systems like offline deep neural networks assume, right? So this introduces some challenges that we have to face. The first is catastrophic forgetting of previous knowledge. So catastrophic forgetting is the abrupt loss of performance on previous tasks in favor of learning new tasks. So that's one of the challenges that we have to overcome if we're going to perform continual learning. The other challenge is the ability to enable backward and forward knowledge transfer. Our visual world around us shares lots of similarities among different tasks, and it would be nice if when learning a new task that's visually similar to something that we've learned in the past could help us learn that new task better and more efficiently by making use of those shared visual representations. So these are just some of the few reasons why we should study continual learning. From a basic research perspective, we can study how to make more efficient learning algorithms. So this looks at things like making algorithms that are more computationally efficient or more memory efficient so that we can do things like deploy them on device and enable several new applications. Another interesting basic research question is how to enable backward and forward knowledge transfer. So this goes back to the question I was just talking about a moment ago about how we can make the systems learn new things better and more efficiently with fewer samples potentially because of making use of those shared visual similarities in the feature representation space. And again, this opens the door to several new applications. One interesting application we could consider is something like on-device learning. On-device learning means that we have to consider those compute and memory requirements quite heavily because we're perhaps limited by the hardware that we're actually deploying the system on. If we're deploying things on device, then we don't have to deal with cloud computing, which means we can deploy the systems in internet-deprived locations, or we don't have to necessarily send it back to a server, which could potentially reduce privacy concerns of sharing user data over some type of cloud or shared server. We can also do things like making customized user experiences, right? So maybe our smartphones adapt to our preferences over time, or we have automatic speech recognition systems that adapt to our different changing vocabularies over time. We could also consider deploying things like robotic agents that are traveling and navigating their environments and learning about the various objects and instances within those different environments. More recently, I think applications like AR and VR have become quite popular, and we could use something like continual learning in order to localize the coordinates of specific objects within a user's frame to give them a more customized AR/VR experience. So I'm going to outline some of the criteria that I think our desired continual learning systems might have. The first is the ability to learn and recall immediately from a single training example. I call this capability online continual or online streaming learning. So on the right, you can see an example of this where basically the agent is provided with a single cat image. It immediately updates on that and then can be instantly evaluated before receiving another instance like a dog, update immediately, and then be evaluated. This more closely resembles how we as humans and animals are naturally navigating our environments and learning immediately as those new inputs become available to us. The next capability is the ability to learn data in any order without catastrophic forgetting. So in the computer vision community, I think that we're very familiar with this class incremental learning setting where we learn one class at a time. Maybe I learn about cats, then I learn about dogs, but I never revisit those classes, which seems highly unrealistic, right? We're constantly revisiting classes. Maybe they've changed a little bit or something like that, but we revisit them over time. So I also think it's important to test other data orderings, perhaps IID, right? Just to understand the gamut of which our algorithms can actually perform. This is crucial since at deployment time, the agent doesn't necessarily have control over the acquisition of the data stream, right? Those inputs are just being provided and it must process them in the order in which they're being received. The next capability is the ability to learn using limited memory and compute overhead. Again, this means that we have to consider how much memory and compute we're actually using so that we can make things like on-device learning more readily available. And the final thing is the ability to scale to large-scale high-dimensional problems. What I mean by this is being able to process high-resolution images, perhaps from thousands of categories, thousands of images. High-dimensional problems can consist of things like even multimodal data streams where the agent must process multiple inputs at each time step, right? So overall, I think that these are some of the various capabilities that our continual learning systems that we're designing need to have. So now that we've kind of talked a little bit about the motivation, I want to set up the problem for continual learning, specifically in the computer vision context in which we study it. So there's two major paradigms in which we can study continual learning. The first is what I'm going to call incremental batch learning. So in this setting, we basically take a data set, we can break it up into several batches. Those batches can be defined based on class boundaries or task boundaries or something else entirely. At each time step, the learner receives a batch of data from one or more classes. It can then loop over that batch and shuffle through it many times before it's been learned, and then it's subsequently evaluated at the end of training the batch. I argue that this has some caveats, the first being that it's slow. So we have to wait for the agent to actually accumulate data. We have to wait for it to loop and train on that data, and then it perhaps delays our evaluation cycle because then we have to wait until after it's done looping and batching over that data in order to actually evaluate how well it learned it. It's also not necessarily reminiscent of how we as humans and animals learn, right? We're not receiving batches of inputs at each time step, spending time processing those, and then being evaluated. We're rapidly learning one at a time from those natural inputs from our environment as they become available. So I argue this is closer to online continual or online streaming learning. In this setting, at each time step, the learner receives a single new instance from the environment. It immediately learns that sample, and then it can immediately be evaluated. The additional constraint is that the learner is only allowed a single pass through the data set unless it caches some data in an auxiliary memory buffer, but then this counts towards the memory requirements of the model. As you notice here, we can still organize the data stream by different classes or tasks, right? So similar to incremental batch learning, I can still organize that data stream however I want, but the difference really just being that we're learning one sample at a time. This is closer to how we as humans and animals learn, and I argue that it's better suited for real-time applications where we want to understand how well the model is actually observing and learning from those new instances as they rapidly become available. In addition to these two paradigms, there's often a pre-training phase that happens before the continual learning actually begins. So this pre-training phase is often performed in an offline setting where we can train the agent on the first set of classes, examples, batch, or alternative data set that we want. And this is in order to initialize the features of our network, right? So something like a convolutional neural network, maybe we want to first initialize those feature representations before we actually perform the online continual learning. Then we can perform the continual learning after this, and we can either keep those features fixed or we can keep them plastic so that we can continue updating them over time. So now that we've kind of talked a little bit about how we set up the problem and how this is actually working, I want to start off by talking about this paper, which was published here 2 years ago, called Lifelong Machine Learning with Deep Streaming Linear Discriminant Analysis. So our motivation for this paper really hinged on that idea of using those pre-trained features. If we perform this pre-training phase before continual learning, do we even need to update the feature representations, or could we instead just update the output layer of the neural network? So to study this question, we revisit a simple baseline from the data mining community called streaming linear discriminant analysis. If you're not familiar with how it works, we basically first pre-train a convolutional neural network to use it as a feature extractor. We can then push a new image through that pre-trained CNN to obtain an image feature, and then we can actually train our incremental LDA model. So this consists of storing one running mean vector per class and a shared class covariance matrix among all of the classes. And then at test time, provided a new image feature vector, we can compute how close it is to those Gaussians in feature space, which are defined using those running means and class covariance matrix. I'll present now the results that we obtained on the ImageNet 1K dataset using that streaming linear discriminant analysis. So on the right, I'm actually showing you the learning curve of how well these methods worked when performing incremental learning on the ImageNet 1K dataset. I want to note that they were first only pre-trained on 100 randomly selected classes of ImageNet. They were not pre-trained on the full ImageNet dataset. So this iCarl and end-to-end model were state of the art at the time, and they operate in that incremental batch learning paradigm. So they're provided with 100 classes worth of data at once. They can spend time looping and shuffling and batching through it, whereas SLDA is only operating one sample at a time. So what's interesting is you can see SLDA ends with the highest top 5 accuracy after learning the entire stream. But I think what's much more interesting is it ran over 100 times faster and used 1,000 times less memory than those incremental batch models. So not only did it have good performance, but it was also doing this in a computationally and memory efficient way. So this comes with pros and cons, of course, right? So it learns incredibly fast and it serves as a strong baseline. If you're interested in more results, we also showed that it was provably order agnostic and could learn from different data streams orderings in the paper. But this really got us thinking about, well, is this algorithm suitable for embedded device learning? Because it works well under compute and memory constraints. I do want to just keep one con in the back of your head, which is that it just trains a shallow output layer, right? We train a fixed feature extractor, and then we don't ever update it, so we're not necessarily doing representation learning. I do want to keep that in the back of your mind because we'll talk about that a little bit later in the talk. So this leads me to the next paper, which will appear at this year's Conference on Lifelong Learning Agents, which is called Online Continual Learning for Embedded Devices. So embedded devices are devices that have been purposefully built for a particular application. They're typically resource constrained in terms of the compute, storage, and power that they have available for processing different data. So with this paper, we were really motivated to understand how well embedded continual learning would work. So this means that we're under those significant hardware constraints like limited memory and compute, but we also wanted to study several other factors that we think are important for real-world continual learning systems. So on the right, I'm showing you those factors that we evaluated. So the first is the ability to scale, right? How well can these methods actually work when they're provided with these large-scale data streams with hundreds of classes, millions of examples? How well can they perform in the face of imbalance, right? Our natural world around us is not necessarily balanced. There's a lot of classes that contain a lot of data and some classes that don't contain a lot of data. So it's important that the algorithms are robust to both types. We also wanted to understand how well they learn from different video streams, right? So this is a temporally correlated inputs, which are providing a naturally non-IID environment to the agent. And then another thing is low shot learning, right? So how well can they generalize when they are only trained on a few examples from a particular class to other examples from those same classes? So to study this, we used 5 different backbone CNN architectures typically designed and used in mobile devices. And we pre-trained them on the ImageNet 1K dataset in a supervised way. We studied that SLDA algorithm I presented just a moment ago and 6 other lightweight methods that update only the output layer of the CNN. So on the left, I'm showing you the continual learning methods that we evaluated, and on the right, I'm showing you the mobile CNN architectures that we used. So we studied a traditional fine-tune method that just updates one example at a time, the multi-class perceptron, a streaming one-verse rest model that basically compares how close an example is to the nearest class mean, as well as how far it is from other class means, nearest class mean classifier, Gaussian naive Bayes, and streaming linear discriminant analysis, and a replay model that basically stores examples in a replay buffer and then updates the output layer using those. We studied 5 different mobile CNN architectures, so 2 variants of the MobileNet v3, 2 versions of EfficientNet, and the ResNet 18 architecture, which is standard in continual learning and computer vision literature that we see today. So first, I'm going to show you the results for how well each of the backbones performed in terms of continual learning for embedded device learning. On the left, I've basically averaged all of the results over all of the methods for each of the backbone architectures. So what we can see is that it's really interesting. The EfficientNet architectures provided the highest performance overall, with ResNet 18 yielding the worst performance, right? This is interesting because we as a community for a long time have been using ResNet 18, and maybe it's time to start thinking about alternative architectures, especially since EfficientNets are not only providing better performance, but they're also more efficient in terms of compute. On the right, I basically am showing you the performance of each of the continual learners when using those 2 best and worst backbones, so the ResNet 18 and the EfficientNet v1. What's really interesting is some methods are pretty robust, independent of which feature extractor they use, right? So SLDA on the right, you can see it only suffers a 3% performance drop if I use ResNet 18 versus EfficientNet. But something like naive Bayes that assumes independent feature representations really suffers when using those features from a ResNet 18 architecture. On this slide, I am summarizing the results across those 5 factors that I mentioned much earlier, right? So these are basically radar charts, and what you can do is plot the performance on each of the axes and then draw a polygon, and those methods with larger areas and their polygons have performed better, right? So we studied things like classification efficacy, compute and memory, the ability to learn from videos, the ability to perform in a low shot learning setting, the ability to scale, and how well they performed in the face of imbalance. And so what you can see at the bottom are the highest performing methods. So we have the replay method, the SLDA method, and the nearest class mean classifier. And on the top, we can see that methods that didn't perform well are things like fine tuning or a perceptron, right? And this is sort of to be expected because they're not necessarily going to perform well if they're never able to revisit classes. So the main takeaways from this paper are, if you're interested in doing an embedded device learning, perhaps you can start with something like SLDA or a memory efficient version of a replay architecture, or even something like a nearest class mean classifier works quite well. And maybe we should be considering things like EfficientNet backbones instead of ResNet 18. But I mentioned much earlier that all of these methods use a fixed feature extractor, and it might be more important in a continual learning setting to actually update those feature representations as the stream is naturally evolving. So the most common way to do this is replay, where we basically store a subset of images or a generator that can generate us data from previous classes, right? So at the bottom, we can see that we're storing images of penguins and jellyfish and fish. And then as new data from the environment becomes available, like geese, we can mix the old and new data together and then actually update the feature representations of something like a convolutional neural network. But the idea here is that storing raw pixel images in a buffer is not only memory intensive, but it's not necessarily biologically plausible. We're not necessarily storing raw images in a memory buffer and then replaying them back to ourselves. So that inspired us to write this paper, which was published in ECCV 2020, which is called Remind Your Neural Network to Prevent Catastrophic Forgetting. So the main motivation behind this paper is that we as humans are storing compressed representations in our hippocampus. And not only are they compressed, they're also from higher visual processing areas. So this means that they're not necessarily raw pixel representations. During sleep, we then consolidate these representations to our neocortex, which learns slowly and more generalized feature representations. So using these motivations, we developed the Remind architecture, which is inspired by 2 theories from neuroscience. The first is hippocampal indexing theory, where we basically store compressed representations in the hippocampus, and then complementary learning systems theory, when we go to sleep, that we can actually consolidate those representations from the hippocampus over to the neocortex. So in terms of convolutional architectures, this is what Remind looked like for this particular implementation. We would store intermediate feature representations of visual features in a compressed manner. So if you take something like a ResNet architecture, maybe you break it in half somewhere, and then you can push images through and extract feature tensors, right? So instead of storing raw pixels, we could think about storing those feature tensors from somewhere in the middle of the network. And we do that in a compressed way. We can then actually train the deep neural network by reactivating or reconstructing some of those stored representations and then updating the plastic layers of our neural network. So this now provides us with the benefit that we're actually performing representation learning and updating feature representations in the neural network instead of just the output layer. So first, I'll show you the results on the ImageNet 1K dataset. So on the left, I'm showing you 3 state-of-the-art methods from the time that this was published. So iCarl, Unified, and BIC, which all operate in that incremental batch learning setting that I mentioned much earlier, where they're provided with batches of data. They spend time looping and batching through them before being evaluated. We wanted to understand how well those methods would work if we just deployed them in the streaming setting to compare them fairly against this Remind architecture. So what you can see is that in the batch setting, BIC works quite well. In fact, it works even better than Remind. However, when we move over to the streaming paradigm, we can see that all of those batch methods actually suffer a significant performance drop, with even the best method suffering nearly a 20% performance drop, whereas Remind is still maintaining a high performance even in the streaming setting. On the right, I'm showing you the associated learning curves in the streaming settings. So what you can see is SLDA, that method I presented much earlier, is in green, and Remind is in orange. So Remind ends higher, indicating that doing feature representation updates actually provides us with some benefits. But Remind is really just this idea of storing compressed high-level feature tensors and consolidating them into the rest of the network. So it doesn't necessarily mean it can only be used for image classification. In fact, it's so general that we can apply it to many other problem domains. So we use this in order to work on online visual question answering and online object detection. So if you're not familiar with visual question answering, it's a multimodal problem where at each time step, we basically provide the agent with an image and a natural language question about the image. So for example, we have a picture of a dog and it says, what color is the dog? And then the agent would be required to produce the correct answer to this question. As you can imagine, there's a wide gamut of questions that we could ask. So this requires many different vision capabilities like counting, attribute detection, scene classification, etc. So to study different data orderings, we either randomly shuffled our entire data stream. So basically taking those image question pairs, just randomly shuffling it and presenting them to the agent. But we can also use the visual question answering task to our advantage to actually structure the data stream in a more unique way where we can actually organize it by question type. So the agent maybe first learns counting questions before learning attribute detection questions and so on. So here are the results on this Clever data set. So Clever test for multi-step compositional reasoning. I'm showing you an example of it on the left. So basically it asks, are there an equal number of large things in metal spheres? So first the agent has to understand how many large things are in the image, how many metal spheres there are, and then reason about if there's an equal number of them. On the right, I'm showing you the associated performance of 4 methods, including Remind on the IID and question type orderings. What's interesting is I overall thought that the IID ordering would be easier. However, for Remind, it actually proves beneficial to organize the data stream by question type. So this begs the question of, are there unique curriculums that aid these algorithms when they're actually learning over time? We also performed object detection. So this was published in BMVC 2020 and it was called Rodeo. So on the right, you can actually see Rodeo's performance ends quite high on the COCO dataset, close to the offline model. But if you're interested in running even significantly faster and using fewer resources, we also implemented a version of SLDA that has a regression component to actually perform object detection as well. All of these methods use some form of pre-trained features, right? Either it's the entire backbone is pre-trained and then frozen, or it's a subset of the backbone is trained and then frozen. In all of them, we're trained using supervised pre-training. However, in the past couple of years, we've seen that self-supervised learning has been gaining a lot of attention, and we were interested in understanding how well self-supervised feature representations would actually work in order to update those offline features for the neural networks. So I'm going to show you the results where we compared performance of Remind when we pre-trained these features on the ImageNet 1K dataset using supervised or self-supervised learning methods. So on the left, you can actually see the % increase that Remind obtained over using supervised feature representations when using 3 different self-supervised representations. So we tried using Barlow Twins, Moco V2, and Suave. On the x-axis, what you can see is how many pre-trained classes we were actually using. So what's really interesting is all of these bars show a positive % improvement, right? This means that using self-supervised learning to pre-train our features overall provided performance benefits. But what's most interesting is the performance benefits were even higher when we were only using a few pre-training classes. This could be desirable since it means that we don't need a lot of pre-training data, and perhaps we don't need to spend a long time pre-training the actual network. On the right, I'm showing you the same associated learning curve that I showed you much earlier, where the original remind method with supervised learning is in orange, and remind using SWAB self-supervised representations is in blue. So just swapping out supervised representations for self-supervised ones using SWAB gave us nearly a 15% relative performance improvement by the final time step. So perhaps we should be considering using things like self-supervised learning in order to pre-train these networks. So I've talked about a lot of different things today, and I think a lot of the components of what I've talked about are necessary for performing real-world continual learning. And this can help us facilitate several new applications like on-device learning, like I mentioned before. But how can we make our continual learning systems more applicable in the real world? I think we need to be considering some of these factors that I've talked about. We need to be considering memory and compute requirements. How robust are our agents when they're faced with different orders of the data streams? Can they work well when the data stream is imbalanced? And we have a lot of examples from some classes and very few examples from other classes. Can they generalize well when they're provided with very few inputs? And how well do they scale? I also think it's interesting to consider additional problem domains, right? We as a community have started working on some other domains outside of classification, like detection and segmentation, but I think there's even more work to be done there. So I'll just provide a brief summary of what I think is next for continual learning, but there's obviously a lot of things that we could talk about today. So I think the biggest one is just moving beyond catastrophic forgetting. As a community, I think we've spent a long time focusing on the forgetting problem, but I think that there's a lot of other interesting factors to be considered. Again, that backward-forward knowledge transfer problem. Not only is it hard to perform, but it's also hard to measure, right? How do we actually understand how well we can forward transfer to unseen data? What is the role of curriculum learning in performing continual learning, right? We saw earlier that Remind actually benefited when I ordered the curriculum by question type. So maybe there's other domains that this is very important. You can think about how we as humans first learn algebra and later we learn calculus, right? Calculus builds on algebra, so it kind of makes sense to learn in this order. What about things like test time adaptation? Instead of performing a static test cycle where my agent gets something wrong, perhaps it also wants to say, okay, I got this wrong, but now it's time to actually update and learn it. Semi or self-supervised updating, right? So that we can actually use unlabeled data to our advantage. Open world learning, so this goes beyond incremental learning so that we can actually identify unknowns and then update on them. And then considering additional problem domains. I think some of the most interesting domains consist of problems that require reasoning or robotics. Outside of those additional problems, we could also take more inspiration from neuroscience and biology, right? There's a lot of differences in the way that we implement replay in biological neural networks versus artificial neural networks. So again, we can consider using things like unsupervised feature updates, using generative models instead of just storing raw samples in a replay buffer, or even using the temporal structure of experiences during replay to our advantage. If this is interesting to you, we do have a paper that was published in Neural Computation last year where we collaborated with a set of neuroscientists in order to understand the exact differences between these domains. So none of this would have been possible without the help of these great collaborators, as well as the people who helped sponsor the research. So thank you very much for your help. And with that, I'm happy to take any questions. Thank you for your attention.
Sorry, I think here we use the mic, or otherwise people from Zoom. Yep, no problem. Here. So I just had a question with regard to the self-supervised pre-training. I noticed that your low end of classes was 10. I wonder, did it continue to increase, or is there an optimal minimum that you were able to measure? And then beyond that, do you have an intuition for why the performance is so much better on fewer classes?
Right, so I will first mention that this is percent increase over supervised learning. So it doesn't necessarily mean that the system overall obtained a higher accuracy at the end of training. It just means that the performance that we obtained using self-supervised feature representations was higher than supervised, right? So using 100 class pre-training is still providing better performance in terms of overall accuracy. Yeah, the performance differences, I think that the reason we see such a high performance gain at 10 classes is due to the fact that perhaps we're not overfitting as much using self-supervised learning, right? If we're only training a neural network in a supervised way on 10 classes, it's highly likely that it's overfitting to that data. And using self-supervised learning perhaps isn't necessarily learning those particular class boundaries in such a distinct way that it's prohibiting us from generalizing well to classes outside of those domains. To answer your other question, we did not try any pre-trained classes fewer than 10. Yeah, thank you for your question.
So I guess follow-up question to that, I was trying to understand, are you doing pre-training with 10 classes in self-supervision, or are you using 10 classes for supervised training and self-supervised is a standard set?
Yeah, so that's a good question. We were just doing self-supervised learning on the 10 classes directly. So just grab 10 randomly selected classes, do the self-supervised pre-train, then learn 990 remaining.
So it's not the question relevant. One of the issues we're trying to deploy real systems, right, is that very often you don't get told it's time to learn, right? It's simply continual. How do you, have you tested any of these systems to figure out how well they can decide, I don't know what this is, please give me an answer, as opposed to being told it's time to learn?
Yeah, I think that that's an interesting open direction, and we actually haven't studied that in this particular paper, but I do think that that's an important next direction. And of course, yeah, it makes these systems even more applicable in a real world setting when we don't necessarily have to tell them, okay, it's time to learn. I think that there should just be, the synonym, we just have one stream of data. If the agent sees something it doesn't know, it can say, hey, I don't know that, I'd like to learn that. And I really do think that's crucial for, making these systems more robust and something we should be considering more in the future.
Yeah, hi. So just a question, and thanks for your talk, by the way. I was just curious about Remind and continual learning. So you showed that Remind is able to exploit a structured learning experience. But does this happen also for the other strategies and Remind as a boost, like is able to better exploit this fact, or the other strategies are not able to learn with a curriculum like this?
Yeah, so I mean, this is really interesting, right? If you look at these results, I think that this indicates that at least the three other methods we evaluated, fine-tune, extreme, and SLDA, they don't benefit from that curriculum, right? Because their performance is higher in the IID setting. But I do think that it's interesting to actually think about, what should the curriculum look like and what types of methods make it a use of this, right? So Remind is different than these other methods since it actually updates feature representations. Maybe for methods that actually update the feature representations, it's important to structure the curriculum in a particular way. And perhaps that's why Remind is actually benefiting from this. We didn't perform any additional experiments to actually dig into this question too much, but I do think it's an important question. And I think it's something that maybe in the future we should start thinking about. Yeah, thank you.
We have a question from Zoom. It's about Remind. Can you elaborate on how the delete representations are reactivated today?
Yeah, so in this particular implementation of Remind, we were actually performing product quantization on the representation. So we would extract feature tensors from somewhere in the middle of the network. We would compress them using a pre-trained product quantization model that was pre-trained on the same set that the feature representations were pre-trained on. During the replay cycle, we would then just randomly select some examples from the replay buffer. Reactivation actually meant decoding or reconstructing those examples using that PQ codebook. And then we could use those reconstructed examples in order to update the remaining features of the neural network.
Here you mentioned doing continual learning on device, but in practice usually there's no label for the new thing. So do you have some insights on how to use it in the practice?
Sorry, I couldn't hear the ending. Can you repeat it?
You mentioned continual learning on the device, and on the device, when you get the data, you don't have, usually we don't have the labels, you don't have the function. For example, like autonomous driving, but you always have mutant, sometimes you have a correct test, but you don't have the functions. So how do we make it work in the practice?
Yeah, I think that's also something really interesting, and that is one of the drawbacks of our work. So we were assuming that all of the labels were available to the agent, but I agree that something, like self-supervised or self-driving cars, right? We wouldn't necessarily be provided with this stream. I think techniques like active learning could come into play here, and this also goes back to the question about open world learning, right? So first, the agent would have to identify which pieces of data it doesn't know, and then perhaps use something like an active learning technique to identify which examples would be most beneficial to get those labels for to actually update. So I agree that is a limitation, and I do think it's an important next step to start considering things like open world learning for identifying those unknowns, and perhaps things like active learning techniques for being able to actually label those unknowns that would be most crucial to update the performance of the network. Yeah, thank you.
So the question about those towards the part, I wonder, is it the gap of the performance because when you do the supervised, you freeze the backbone, the feature backbone, so that's why you said that the reaching number of classes per also overfitting workflow. Is it because you freeze the backbone or something?
Yeah, so it perhaps is due in part some to that, but we're not freezing the entire backbone with Remind. We only freeze part of the backbone, but it does continue to update that backbone over time. One thing that I guess needs to be considered here is the way that we're actually updating the backbone in an incremental way is still in a supervised setting. Perhaps there's more performance improvements to even be had if we continued updating the backbone in a self-supervised way.
Okay, so that reminds also that like the installation strategy in updating the backbone or not just freeze the like lower layers and which one?
Yeah, so the motivation for freezing some of the earlier layers was kind of twofold. I guess the first being that the early feature representations learned in CNNs are usually visually pretty similar, right? Like edge detectors, bar detectors, Gabor filters. And we did show in the paper that if you update all the way back to the image layer, you would see a performance improvement. But storing intermediate feature representations is not only more biologically plausible, but it also saves memory. So really our motivation here was to get the memory benefit of storing higher level compressed representations. But I agree, it could potentially be more important in some settings to update the feature representations, right? It's going to be a trade-off between the memory efficiency and computational efficiency versus how much performance benefit you want to see.
Okay, so that's like for like on device communication, then this is more suitable, right?
Yeah, probably, or even just updating the output layer, depending how limited in terms of memory and compute you actually are.
Oh, okay.
Yeah, definitely. Thank you.
Any other questions? Yeah, so maybe I have a follow-up question on the mic. So since we freeze like the low-level features, but have you actually determined where the network you have this low-level features and where you get this mapping information?
Yeah, and this is a really important question about Remind as well, right? In this paper, we performed ablation studies, and we basically chose the layer that was optimal in terms of how much memory trade-off there was for actually updating the backbone, but we didn't necessarily provide a heuristic or anything for choosing that. And obviously it's architecture dependent, right? We provide some set of layers to extract from for ResNet 18, but this is obviously going to change if you move to something like an efficient net. In terms of actually doing choosing which layer to extract from, alternative architectures, I think it's kind of an open question, and it perhaps even is dependent on your application, right? I mean, if you pre-train on some data set that looks wildly different than what you're actually doing continual learning on, it will be really crucial to update a lot of the backbone in order to get good continual learning performance. But if your pre-training set is very similar to your online learning set, then maybe only updating 1 or 2 feature representation layers is enough. So we don't have a heuristic right now, but I do think that that's another important question, is how to actually choose which layers to extract from.
So if it's dependent like on the data you're seeing, I think it could also be a possibility that this like boundary could also be adapted like based on data stream you see.
Oh yeah, definitely. So I mean, that's also an interesting direction, right? Is thinking about extracting at different layers for different types of data that are input, or even extracting features from multiple layers, storing those as one representation for a particular piece of data, and things like that. I guess the only other thing to consider there again is the memory, right? So or storing earlier things will take up more memory, but maybe storing only a few of those earlier things is better for performance than storing a lot of things closer to the output. But in practice, I've generally found storing more is better. But that doesn't necessarily mean that there might not be a trade-off there for actually storing stuff higher or lower in the network. Yeah, thank you for the question.
We have a question from the Zoom chat. Did you analyze the reason why self-supervised training is superior to supervised?
Yeah, so we didn't actually study why it was necessarily better. We only made some intuition about overfitting and things like this. But I think, again, that's an interesting question to ask. And studying that is also an interesting question, right? Would you study that at the feature space level? You probably have to, right? Like looking at the clusters and things like that.
Okay, so do you have any idea of how to study this apart from the accuracy?
Oh, so yeah, I mean, I think it could be interesting to develop a metric to understand how generalizable a feature backbone, like the features from a particular backbone are. What would that metric actually look like is a harder question, I think. Again, so I mean, you could study the decision boundaries in feature space, right? You could compute the distance to the decision boundaries or metrics like this. But yeah, so I don't necessarily have a great answer for that right now, but I don't think accuracy should be the only thing we're studying, especially when we're looking at feature representations. You could study representational similarity as well, but yeah, I don't necessarily know what that would look like. I guess you could compare the similarity to supervised, but that doesn't necessarily guarantee that if it's dissimilar, self-supervised would work better or not, right?
Yeah, okay.
Thank you.
Thanks, Alan, for your presentation. It was a great intro about the online continual learning. And I recognize that typically many methods that use pre-trained models right now uses pre-trained model by using classical like IID supervised learning or like self-supervised learning, that just like the one you introduced. And is there any of your ideas, like it may be an open question, but is there any idea about building a pre-trained model for the continual learning, like any special properties that the model should have?
Yeah, I think this is an interesting question. I think this kind of relates to the question from Zoom that Antonio just mentioned, is actually how to study or how to quantify the robustness of particular features, right? For the downstream continual learning application. Yeah, I think coming up with some metrics for understanding which features would transfer better for certain continual learning tasks is interesting. But again, I guess there's some considerations about what would that look like. Maybe we study the distances in the decision boundary space or the feature space. Maybe we look at representational similarity. Things like that. But yeah, I mean, there's obviously differences between using different backbones. So I think it's an interesting question to ask, right? I mean, we found that efficient nets worked significantly better than ResNet 18s. So it does kind of beg the question, okay, well, what should my ideal feature representation look like? Yeah, I think it's an interesting open question. Thank you.
Any other questions?
On the other side of what you just said, do you have any indication towards on these strategies, whether target specific new features can be learned on the backbone, given your expectation and strategy?
Okay, so on the flip side, how to actually learn more discriminative features during continual learning for the new tasks. Yeah, I mean, that's also an interesting question, right? Yeah, again, I think that this would again come down to understanding particular different metrics and things like that, but it could also depend on the structure of the actual network, right? So perhaps there's certain ways of structuring the network that might be beneficial during continual learning. I think much later we'll hear about sparsity and the role that maybe sparsity plays, because perhaps this is sort of making distinct parts of the network useful for distinct tasks and things like that. So it could be interesting to think about how that plays a role, sparsity, or even something like modular networks, right? So modularizing different concepts and then kind of building those up.
Could be related to initialization instead of working with another patient.
Yeah, so I mean, in terms of initializing the actual feature representations, sure. Yeah, I mean that's an interesting question as well, right? Is thinking about how to actually initialize the features and then which neurons to actually update, right? So we could think about how useful some of the neurons are. I mean, we do this in pruning techniques, right? To identify which of the neurons to prune. So maybe identifying which of the neurons to actually continually update would be also an interesting question to ask. Yeah, thank you very much for your question. Hey, Alex.
I had a question to remind, the sampling strategy that you use for kind of choosing which images to remind, how is that driven and motivated?
Yeah, so that's kind of one of the limitations of Remind is actually for this particular paper, we just randomly selected data from the memory buffer. We did try some alternative techniques, but found that they were more computationally expensive and didn't yield much computational or accuracy improvements. But in a more recent paper last year, we studied this particular question of selective replay for an analogical reasoning problem. And so in that domain, we actually found it was quite crucial to choose techniques alternative to random sampling, so that you could think about distance to the decision boundary, the margin between the highest predicted probability and the next highest predicted probability, you know, even task specific things, right? So for object detection, we chose images that had a lot of objects in them, right? And that yielded the most performance improvement. So I think this is also a really interesting line of research is which examples to replay, when to replay them, how many to replay. I think there's a lot of interesting questions there. Yeah, thank you.
I think we can switch to the next talk. Let's thank again.
Thank you, everybody.
Okay. How can I see the Zoom chat here? To make it larger. Okay, so for the next talk, we have Sebastian Risi virtually over Zoom. Hi, Sebastian, can you hear us?
Yeah, I can hear you.
Yeah, okay, great. So Sebastian is the director of the Creative AI Lab and co-director of the Robotics, Evolution and Art Lab at the University of Copenhagen. He is also the co-founder of Model.ai, a company that develops AI technique for game development. In his talk, he will talk about self-organizing machines. I think this will be a very interesting topic since it's not as popular as many other things that we will see today. So Sebastian, the stage is yours.
Yeah, thank you very much, and thanks for the invitation. And yeah, I'm sorry I couldn't be there in person, but happy to present nonetheless. Yeah, so I think this talk might be a little different to some others. So I'm going to talk about how can we use ideas from like collective intelligence, things like self-organization to create more robust and lifelong learning machines. And so one of our favorite workhorses is this is of course backpropagation, and that works surprisingly well for a lot of different domains, but it's quite different to how adaptation works in a lot of systems in nature. So while in backpropagation you train a network, and it's very common that after training, after you found the right parameters, you freeze the model and then you just apply it, which gives limited ability to adapt to changes that were not anticipated during the training process, and also results in limited ability to continually learn. What we see in nature actually often is this kind of self-organization process. So in nature, adaptation basically never stops. You see like, and this gives organisms in nature amazing abilities, like these ants that you see here that are able to build a bridge together, or termites that are building these huge meter-high termite mounds, schools of fishes that swarm together, or of course also our nervous systems and our whole bodies that are basically a process of this kind of adaptive self-organization. And in these kind of systems, they adapt the whole time. There is no division between a training phase and then a deployment phase, but we have this adaptation, continual adaptation, self-organization the whole time. And so one hypothesis is that this kind of self-organization maybe is the reason these systems are so adaptive, resilient, and allowing this kind of lifelong adaptation. And our hypothesis is basically that incorporating these ideas into our deep learning systems might be also able to make them more robust and also ultimately to continually learn during their lifetimes. And we study this on different domains and different problems. So I'm going to talk about basically two types of different things during the talk here. One is kind of trying to make more adaptive nervous systems, artificial neural networks that can kind of continually learn, that organize their weights the whole time. And then the other thing is also talking about some of these morphologies of robots, which is also important. When they're damaged too much, learning cannot continue. So how can we also use this to create more robust, maybe morphologies that can recover from damage to be able to continue learning? And so the first is this continued adaptation to basically damage to the morphology. We see that organisms in nature, like this dog, can still learn even though it, for example, lost a leg. So we do similar experiments where we have these simulated quadrupedal robots, and then we want to see if we cut off a leg, can this robot still function in its environment, or will it basically break down? And if you use a traditional static neural network, like you train the network with your favorite learning technique, reinforcement learning, or for example, evolutionary algorithms, then these networks will work well on the morphologies it's trained on, these two first ones. But then in the third one, it hasn't seen during training, so it will most likely fail in that morphology where one of the legs is shorter, and it doesn't know what to do because it's not adapting during its lifetime. So we see the typical fixed network. Here's the visualization of the network, and what is typical, that during the lifetime, there's no changes to the weights of this network. We have changes after the episode, but not while the agent is interacting with its environment. These weights are in the traditional deep reinforcement learning paradigm. They are fixed during the lifetime of the individual, which limits the ways it can adapt. And so in one of the works I wanted to talk about here is where we basically said, okay, let's move away from these fixed networks and we don't learn any weights at all. So these systems, every episode, they start with completely random weights, these networks. And the only thing we learn is local update rules. And then we see if the system is able to self-organize its weight while it's interacting with the environment. And how we encode these rules is we use what's called Hebbian learning, which is a more biologically, it's how our brains learn just through local communications. And we learn basically just these parameters of these rules that take into account the presynaptic activation and the postsynaptic activation. And then we weigh these differently with these learned parameters A, B, C, D, and the learning rate. So for each, instead of having one parameter for every connection, we don't have any parameter for the weight, it's random, but we learn these additional, we learn 5 parameters for each weight, that then every time step, it looks at the pre-postsynaptic activation from each connection and changes the weights based on this activation. So, and every connection can have their own basically learning rules in this network. And these weights, we optimize these parameters, these learning rules through evolution strategies, but you can also imagine optimizing them with some other deep RL methods. But the important part is that the weights are all random, and the only thing is learned is these local update rules. And then we see as we train the agent, we employ them in an environment with initially random weights. We see if it organizes, self-organizes, and we give the reward is basically how far can you locomote in that given amount of time. And what we see is actually after training, so here the weights that you see are dynamic. So the weights, every time step, the weights basically are changing. And on the right side, we see the static network that I showed before, which fails with a morphology not seen during training. But on the left side, this morphology hasn't seen during training, and it's still able to basically adapt to that insult, to the injury, and is still able to locomote. It's not the most graceful locomotion, but it is able to still work. And so this is a different type of neural network, a more dynamic neural network where the weights never stop self-organizing. And we also applied this approach, does not just work for, in this case, of robots, but here the agent is trained directly from raw pixels, trying to control this car in this in this car racing domain. 1 second. Where it just has to learn from pixels. And we can see here is also that it's able to work, and very quickly, only after a few steps, to organize the weights in a way that it allows the car to drive. So we were actually quite surprised that this actually works at all, starting from completely random weights, and in a few steps it reaches some kind of state in that weight space, some attractor that allows it to control this car driving around. And what's also interesting, that the system is also it's quite resilient also to if you remove some of the weights. So here we have the weights, and what would happen if we set all of these weights in one of these middle layers to 0. And what we can see is that only 10 time steps later, through the self-organizational process, these weights are recovered. They look a little different than they did before, but the agent is still able to reach the same level of performance. So we have here the episode, and performance drops when we remove the weights or set them to 0. But then after only a few time steps, it is able to recover, and also recover basically performance in the domain. So this is some quality that is often observed with these self-organizing systems, that they're quite robust to all kinds of different basically damage and perturbations. So we think they're a promising avenue to explore for these kind of also these lifelong and continual learning, and making robots that basically never stop learning. Of course, there can be times when damage is too severe. So in this case, we cut off half a leg, and the robot was able to recover. What if we cut off like most legs of the robot, or some other types of damage? In this case, it might not be enough to only change the control system of the robot, but it might be necessary to actually recover some morphology of the robot to still being able to learn. And so again, what we often do in our research in my group is we look at nature kind of for inspiration. How does nature solve this problem? And nature solved this problem through morphological regeneration. So we have this, salamanders have this amazing ability that if they lose one of their legs, then they can basically, of their appendages, they can basically regrow the whole thing, and it looks quite similar to what they had at the start. So if we could give our robots that ability, then they would also be able to learn more continually, because some damage like this would not render them basically useless. So how can we incorporate these ideas of morphological regeneration into our machines to make them more robust? And so this work is basically building on techniques that have been around for a long time. The idea of a cellular automata, which I assume most people here are familiar with. The basic idea is that you have, and it's a prototypical self-organizing system. The idea is that you have these cells, and each cell only looks at its local neighbors to determine what should the next state of the cell should be. And traditionally, these cellular automata the roots have been hard-coded. So for example, if you have 3 neighbors, then add another cell. If you have 4, then it's overcrowded, so the cell would die. But then approaches have shown, researchers have shown that you can actually, instead of having hard-coded rules, you can use a neural network that is that would learn the rule of the cellular automata. So basically, imagine in each cell you have a copy of the same neural network running, like similarly to a graph neural network, that looks at the neighbors and decides what should the next state of the cell be. And then you can train these neural networks either through supervised learning, if you have a target in mind that you want to maybe grow, or you can also train them through evolution or reinforcement learning. And then kind of what invigorated this field again is that this differential neural cell automata. So if we actually have a target, we can actually differentiate through the whole network, and we can efficiently train these through supervised learning to grow a particular target structure. And so this is some work we did where we tested the system. So again, we are quite cruel to our robots. So we perform all kinds of different insults to them, where we, for example, here we have a robot that has evolved, a soft robot to locomote, but then we cut off half of its body and it's not able to work anymore. But with these neural cell automata, we actually running in each cell, this robot is able to regrow the missing parts, again, only through the local interaction of the cells, and is able to basically work again in its environment and can allowing a more lifelong type of learning. And then in follow-up work, we wanted to see if we can not only use this to grow soft robots, but can we actually use it to grow functional machines? And for this, we used this Minecraft domain. So we extended this to growing functional machines in Minecraft, again, just based on neural cell automata. And in this case, again, the structures are that we wanted to grow are human design. So we're basically learning through these differential NCAs to grow a particular target structure. And so, for example, here we learn to grow trees, just again, based on the local interaction of the self and this self-organizing process and a neural network running in each of these voxels. And so we tested this on these kind of static structures, but then later, as you see, we also did it on functional machines that are then able to, again, recover from damage, able to continue their learning process. So here's a very simple functional machine in Minecraft that is just locomoting forward. Then we also applied it to slightly more complicated functional machines, this salamander that is able to locomote. And then we did, again, some cruel experiments where we cut the salamander in half and wanted to see, can it learn to basically regenerate its morphology? So here is cut in half, and then it's able to regenerate both parts of the salamander and then, or caterpillar. And then they were able to, and it still works, it's able to basically locomote forward. So the last thing I wanted to mention is basically what is the most kind of extreme form of lifelong or transfer learning. And again, we look at nature for inspiration, and it's basically this what we find in nature is this idea of metamorphosis. So that's one of what I think is the most extreme form, where you basically have a caterpillar and that is reconfigured somehow and made into a butterfly. And so we wanted to see, can we create systems that can do this kind of extreme reconfiguration where you use some information that it was used to create the caterpillar, and that is also information that is used to make the butterfly, but it's a complete rewrite of the nervous system, of the morphology. And we didn't test it to that extreme, but we have some initial work that shows that it's kind of possible using this for slightly different robot morphologies. And again, what we did here is we used basically a neural cell automata to grow a pattern, and that pattern we then turned into a neural network. So you can see here is the neural network, the pattern created by this neural cell automata, just again, based on this process of self-organization. And here you can see the policy network that is grown based on this network. So it's we initially, before we deploy the network, we run this growth process, growing a neural network, then we deploy it as a policy network into our reinforcement learning agent. So you can see here the pattern is growing and the neural network is growing, the policy network. Once this kind of growth process is done, we put it in the environment and the agent is able to locomote. And what we can now do, since we have this kind of growth process, we can actually, what we call this metamorphosis network, we can grow not only one network, but we can grow multiple different networks. So we grow one network for a small quadruped, then we continue this growth process for morphology that's slightly bigger, and we continue the process longer to grow a nervous system for a larger quadruped. And so this is what we showed here. And then we grow a nervous system for this robot, we grow a nervous system for this robot and this robot. So the same neural cell automata is able to grow various neural networks, with allowing these robots to still locomote. And here we mapped kind of the development of this weight space. How do these systems learn? And we also show that there is some type of transfer learning happening. It takes more time to train for each quadruped individually than if we would learn one neural cell automata that grows consecutively these different nervous system for increased larger and larger quadrupeds. So to kind of conclude, so we have seen that, so basically living system can construct and prepare themselves and have very robust lifelong learning capabilities. So and we're starting to see that incorporating these ideas from collective intelligence, such as self-organization and only kind of local communication, can enable more robust and resilient agents. And we hope that that is one little contribution to trying that we move as a community a little away from this kind of strict division between training phase and deployment phase, but have systems that can continually adapt and continually self-organize and react to changes that have not been seen during training. And if you're interested in kind of more biological perspective on this, which gives a lot of motivation for the work, then I can suggest this recent review article that we wrote with many co-authors, Biological Underpinnings for Lifelong Learning Machines, which came out of this DARPA L2M program recently. And with that, I want to thank you very much for the attention, and thank you to the members of my lab. Without this work wouldn't have been possible, and also the people supporting this work. And if you're more interested in also this kind of self-organization, I will also point you to my blog, where I recently wrote a little bit about these ideas of self-organization and collective intelligence and how we can combine them with deep learning. Thank you very much for your attention.
If there are any questions, you can come to the microphone. Okay, I have a question to start. I'm wondering what are the key properties, or at least the properties that you think are important for Ebyan learning, why Ebyan learning is so successful for continual learning. To me, it seems like the two important things are maybe the test time adaptation, so the ability to adapt even after the network is trained and when you have a change, and maybe the sparsity and having an unsupervised objective that you can actually adapt without needing targets. So do you think there are any other components that are fundamental?
Yeah, I think that is kind of idea of that it's basically trained to be very robust, because it has to basically deal with a new random weight pattern each lifetime. So I think that helps the system to find a find like a dynamic attractor in that weight space that works no matter what kind of your starting conditions are. And of course, Hebbian learning is only one of the mechanisms that our brains learn. So there's also follow-up work by other groups, like where you need other mechanisms like neuromodulation that would allow switching Hebbian learning on and off, which can give you even better lifelong learning abilities. So I think this idea of that you have to work from random weights at the start probably helped, and the idea that this kind of this local updates, I think, are two of the reasons why it's working so well. But it's definitely not all like that. There are definitely extensions we can add, like neuromodulation. I think that would make it work even better.
Yeah, thank you.
Okay. Hi, and thanks for the talk. So I think that this line of work is quite interesting for continual learning, but I was wondering if you are aware of, I mean, if you have any opinion about the application of maybe also existing continual learning strategies to the neural cellular automaton. But I mean, if in any way the current deep continual learning strategies can be applied or can be useful even in what you showed, right? So I don't know if you have any thoughts about that.
Yeah, so you're meaning, so like applying it the other way around. So using current continual learning techniques to make, like, to help neural cell automata training.
Yeah, exactly.
Yeah, so there's work, and that's also something that we took advantage of, like to train it basically for being able to recover. It's basically like a technique where you add different in this training pool, you basically add a lot of damaged morphologies. So it's inspired by, I guess, techniques from continual learning, that you have this rehearsal methods that where you add data that it should be it should learn from. But other than that, I'm not aware of other work that incorporates more continual learning techniques, but it would definitely be interesting to have this merger of the two techniques as well. But I'm not sure I am aware of other work that does that. Yeah.
Okay, we have a question from the Zoom chat. Do we expect techniques like Hebbian learning to scale? Can we train a large self-supervised transformer with these techniques?
Yeah, it's interesting because actually there's quite a lot of connection to this Hebbian learning, which is it's basically like transformers. They're also based on this kind of self-attention. Which is basically it's a form of this kind of, I mean, it's related to this form of Hebbian learning. So I don't think like it would make sense to only train the whole thing through Hebbian learning. But I could imagine some interesting architectures where you have a pre-trained maybe transformer, and then you add something like a Hebbian learning on top that would allow it maybe to be quickly adapt to different modalities or different circumstances. So I would say that my money would be on making some kind of hybrid model that kind of combines the best of transformer and Hebbian learning. But there's definitely a deep connection, I think, between this kind of self-attention and things like Hebbian learning, which are interesting to, I think, explore further.
Yeah, thanks. Do we have any other questions? Matthias?
Yes, so thank you for the great presentation. What I found really interesting is, like, in these morphological processes, can imagine like the loss objectives or rewards to design are also very important, but like specifically in like this example with this Minecraft self-evolving modules, like what kind of objectives do you use for that, and what's the importance of designing?
I could only, it was a little cut off. Like I heard with objectives in Minecraft, but then the audio is still.
You can come here if you want.
Yeah. Is this better?
No, or maybe you can just repeat it, like the.
Yeah, like what is like the importance of the loss objectives and rewards you have, especially keeping in mind for me like this example in Minecraft where you have the self-evolving modules in this virtual world, right? And what is like the really importance of this
It's hard to understand, but I don't know if can be repeated there on the Zoom, like the. Okay. Yeah, the audio it's a little difficult.
Okay, so is this better?
Yeah, that's better. Sorry.
Okay, great. So yeah, my question was like, I was wondering about like the loss objectives and rewards you have to design to get like this morphological processes, like you showed in these Minecraft examples.
Yeah. So in the Minecraft world, what we did there is that we basically the loss is defined on the reconstruction, like how well can you regrow this human designed artifact. So the artifacts are designed by humans, like the apartment building and the tree, and then it's just about how close can you get from growing to making that structure. In more recent work, where we try to move away from having these human designed structures, we actually use artificial evolution to discover a large variety of things, and then we use backpropagation to make them to make these structures robust to damage. So you can combine kind of the best of both worlds, that you use the creativity of evolution and then you train it to be robust to supervised learning. But it's not what was shown in those Minecraft examples.
Yeah, like for this growing objective, how do you define or how do you know when to stop growing, for example?
Right. So the cells can also decide to there's a live mask, and then we basically we start basically if they would grow too much, then the loss would be there would be higher error basically. So whatever comes out of the growth process, you compare how close is what you were growing to the actual structure that you were given. And that way, if it would not stop growing, it would basically be punished for just continue growing. But it's actually quite a hard thing to learn, that we also give it variable time, like variable developmental steps, so that it even after, if it's only trained to grow 50 iterations, it should not grow more than if it's given like 100. So we varied that time during the training process as well.
Okay, great, thank you. So we have any other questions?
Maybe you can come here.
Oh, sure.
Hi, thanks for the nice talk. I was curious. So we see the forward adaptation when the robots receive damage. I was trying to get a sense, and I didn't get it from the slides that we saw. How resistant is the approach to catastrophic forgetting? Can the same network be presented with the undamaged version of the robot and still perform?
Yeah, so the results I showed where it works for those 3 different morphologies, that was all the same network. So that network still works for the undamaged one, and it can during its lifetime adapt to the changes. So if you switch back, it will still be able to, it will change again and be able to work for the original morphology. But it's of course still limited in the type of, if we would have done more severe damage or changed the robot to something completely unexpected, it will probably not work so well. But since it has seen 2 of them, it kind of was able to generalize to the 3rd one that was unseen during training.
Thank you.
Okay, so okay, we have the last question.
Do you have any comments on what you think would be a good approach if you wanted to modify this to grow superstructures that maintain the same functional sort of properties of the smaller ones?
Oh, you mean like self-similar systems, or when you?
Yeah, I guess in this case, self-similar systems.
Yeah, I think what you could do is that you would train the systems to grow various sizes, but we haven't thought about it so deeply. I know there's some work in growing fractal robots, where like a larger robot is made out of like the same components than the smaller robot by, I think, Josh Bongard and Sam Kriegman. But I do imagine you could. One thing we want to do in the future is extend this approach, which I think is related to your question, that we would, if you grow a machine in different environments, like let's say you grow it in a small room, you grow it in a large room or a bigger room, the machine should adapt to the size, for example, of that room. So taking into account the environment in the growth process. So I think this way, if you would train it this way, you could probably get like a smaller caterpillar in a smaller room, and in the larger room would get a larger one, and that it should figure out that that they should still work. But it's something we haven't tried yet. Yeah.
Thank you very much.
Thanks.
So thank you, Sebastian, for your time and for the great talk.
Thanks again for the invitation. Thanks.
Now we have the break, the coffee break, and the poster presentations until 10:30. So we will get back in half an hour for the second round of talks.
Yeah. Keep in mind it's a bit of a walk, so might come in advance for the next talk. Also, maybe the people having an oral presentation, could you maybe pass by to organize a lot of stuff? Thank you.
I mean, yeah, I certainly think there's. Right. That is true. Right. Right. Sure. I mean, in some sense, they're a little bit orthogonal because of what you mentioned. But I do think that perhaps it could be interesting. You know, if I did pre-training and I did a curriculum-based pre-training, right? So I build something and then build up. Could those feature representations be more robust going downstream continual learning than just training in a certain way? But then again, that's kind of like an incremental learning-based pre-training. So yeah, I think this is an interesting question. To think about, like, what is the moral of that? In a streaming setting where you don't have control of the acquisition of the stream. Right, yeah. Yeah. And I usually find it hard to what is allowed, what is not allowed. Yeah. I don't know. At least it's the rules of the game for an outsider. Yeah, I mean, you could always follow through it, but sometimes paper code is great share and it's useful, but you know, oftentimes that happens in some of my work, you have to design make things that make sense, and then on baselines in those settings. It becomes more difficult because you can't just look over papers, you have to like re-adapt that to be able to perform well in those settings. Yeah, in terms of curriculum learning, rules regarding what to do for that, I don't know if there are many papers on that. I think it's still kind of like what it means to actually study that, what types of problems should study that, what should the curriculum look like, how to decide where if you want to do a difficulty-based curriculum. Yeah, I think it's something we don't get trained. Yeah, thanks so much. Hello. How are you? Oh, it's okay. Yeah.
I still have a number. The day the workshop, no, this was for why I came actually, because I was not going, and then I got the ratio, and then okay, let's go. Sometimes, yeah, I did one, it's the next 2 hours, so that's the other one. Yeah, I need another 15 mil of euro. And 5 now from March. Especially, I believe it. I did it time, yeah. I did it once, but then the internet connection collapsed. I got the measurements which I don't need. We had to get out of Zoom, in of Zoom, out of Zoom.
Yeah, so I mean, one thing, so here's that 22 today, I kind of want to make noise. So there's one thing to consider is the amount of. Training, so. That's kind of like a. That's like. Let's ignore the. Yeah, I mean, it's, yeah. Because I do.
One time in the Netherlands, only the French, they go really for the. Maar de Spanish kan voor de host. Ja, hij was in Grenoble. I kind of like Mediterranean style. But I wasn't the biggest. So this one is these are, you know, maar je moet doen is 20 kilometer van de zee hoor.
Yeah, you don't really use the question. So I haven't, so I mean, besides this stuff, I haven't done the full.
Okay, so we'll be waiting for just 5 more minutes just to get people into the room. Sorry for the short breaks, but yeah, we're pretty much restrained by the CVPR rules, and we will start in 5.
Oh, actually, it's good. It's good.
Daar zie je het ook een beetje. Het is wel leuk voor mensen dat je kijken naar de images. De zaken nadat het pas begon. En in de andere kant but yeah.
So I'm not sure this domain is Yes, absolutely. So the challenge, is quite tough. So I just gave him a bit of advice based on the experience of the previous years. But then, yes, it's a tough job.
Ja, proberen studenten motiveren om ze op te bereiken.
Yes.
Assuming people are finished here.
Yeah. just as practically, we are surfing, but in terms of number of data, it's an exponential. In the challenge this year, I think a bit more, but that's also the
All right, so we're ready to start again. So now it's my honor and pleasure to introduce Joost van de Weijer, is the head of the Learning and Machine Perception team at the Computer Vision Center in Barcelona, and is an internationally renowned expert and leading researcher in the field of computer vision. And I can say, I think definitely that is also one of the leading researchers in continual learning in Europe. I'm really excited to hear about his talk today. That will be about a very hot mainstream, I would say, topic now in continual learning, that is source-free domain adaptation towards unsupervised continual learning. So thank you so much, Joost, for being here with us, and please, the stage is yours.
Thank you for the introduction. Yeah, so today I will mainly talk about domain adaptation. For the workshop, I pushed it a bit more to continual learning. And it is a form of domain adaptation which actually looks a little bit like continual learning. It's source-free domain adaptation. And source-free means that you're not allowed to use any data from the source domain when you're doing the adaptation on the target domain. So I think this field has seen a large growth in recent years, and I think it's interesting for the continual learning community to be aware. I think we are aware, but okay, to see what can we learn from there and what are the similarities. So lifelong learning, just for some terminology, I think lifelong learning is maybe bigger than continual learning, and it includes other problems. Continual learning is one of the problems. In lifelong learning, maybe you have a knowledge base with different models which you might want to apply to a task. You have data which to adapt to, and then you maybe want to put this knowledge back in the knowledge base and continue. So in this talk, I will focus on a domain incremental learning, if we want to talk about incremental learning. So the set of classes stays the same while doing new tasks. So I always have the same set of tasks, but the domain is changing. And the second question I put here is, do we care about the previous task performance? So typically in a domain adaptation, you do not care about the task performance on the source data. You only care about the performance on the target data. And in transfer learning, the same. And in continual learning, you do. So that's a big difference between these fields. Yeah, okay, some other things which come into play if you think about lifelong learning here. So domain adaptation, you have a source domain with labels in the today, and a target domain without labels. The target domain is as a domain shift, for example, from synthetic data to real data. And you want to get the best classifier on this target data. Yeah, today I talk about a number of versions, and I will show this table a few times here. Let's say I put as a goal unsupervised continual learning, where you don't have to store any data. You don't need labels for the source, nor for the target domain, and you care about performance on all the tasks or domains you see. And unsupervised domain adaptation, which is by the biggest, I think, domain adaptation field, it does need storage of the source domain. It needs labels on the source domain, and you do not care about the performance on the source domain. There are a lot of methods developed for this field of research. I just wanted to show one, this adversarial domain adaptation, which is very famous. So you train a backbone which trains features which are invariant for the source and the target domain. So there's this ping classifier is trying to distinguish between these two domains, and you want it with the gradient reversal layer, you make sure it fails in this task. And you have a classifier which is trained on the source data and which you can then apply on the target data because you have this backbone which is features are invariant for both domains. So in this case, you really need the source data to do this training of this domain adaptation method. Yeah, today I will go through 3 works in this direction. The first one is intrinsic neighborhood structure for source-free domain adaptation. So this source-free domain adaptation really got a lot of attention in recent years. I think mainly because of sort of edge computation, where you maybe have a large model trained on the cloud, which you then download to edge devices, and then you want these to adapt to the local data, to the user or to the domain. But at that moment, you don't have the source data anymore. So you cannot apply, for example, the method I explained yet. So another set of methods needed to be developed for this scenario. And it really became a hot topic there have been already hundreds of papers on this topic now, I think. So the normal situation is where you have source and target data and you want to test on the target data. And now we consider when you adapt to the target data, you no longer have access to this source data. So here, what I call source-free domain adaptation, it has one tick more. It doesn't need storage of the source data when compared to unsupervised domain adaptation. I wanted to shortly say the first method which was proposed for this source-free domain adaptation, which is a very nice work from the ICML 2020. And they proposed 2 losses. It's very simple ID. And the first loss is an entropy loss, and it just says, I want my target classifier to be sure about its predictions. So if it would be successful, that would certainly be a property I would like it to have. And the second loss is a diversity loss. I wanted to find all the classes I also have in the source domain. I think this is a sort of use knowledge which we have of academic data sets, but okay, this works also pretty well. And using just these 2 losses and a little bit of pseudo labeling, they managed to get a very good domain adaptation method. So this was the first method. And what I showed, surprisingly, is that I could get similar or even better results than the methods which did use source domain data. So that was a very nice result. So we started from that paper and thought, what can we do more to further improve these results? And we are looking at the local structure of data. So if you send your target data to the source model and you make a T/E of the plots in the feature embedding space, then you get something like this, and you clearly see clusters in this space. So this made us think, can we somehow exploit this fact that neighbors in the source model that I probably need to have similar predictions at the end of the adaptation process. No? Secondly, we were thinking, okay, neighbors, can we do more than neighbors? So we looked into the concept of the reciprocal neighbors. A reciprocal neighbor is if A is a neighbor of B and B is a neighbor of A, then it's a reciprocal neighbor. So in the example here, for example, 2 is a reciprocal neighbor. If you look at the 2 nearest neighbors, 2 is a reciprocal neighbor of 0, because 0 is also within the 2 nearest neighbors of 2. But 4 not, for example, 4 is a nearest neighbor of 0, but 0 not of 4. So that's a normal nearest neighbor, let's say. And if you look at the prediction correctness of reciprocal neighbors and normal neighbors or non-reciprocal neighbors, then you get this curve on the right. And the reciprocal neighbors are given in black, and the non-reciprocal neighbors are given in red. And you see this gap of 5% in accuracy. So really, the reciprocal neighbors more often predict the correct label to a point. So this could somehow be weighted while doing this consistency minimization. So, okay, this is a sort of overview of this whole method where you have some not so nice organized data in the source domain, and we want to get a nicely clustered data in the target domain. So how do we do about this? So we make a feature bank of all the data in the target domain, and we store the features as well as their predictions. And we have an affinity matrix A, which is 1 if it's a reciprocal neighbor, and which has a value R, a hyperparameter, if it's a normal nearest neighbor. It's set to 0.1 in these experiments, which was found to give good results. And then we minimize the loss here in the top. So it just says if 2 nearest neighbors have similar, are close in the space, so they are nearest neighbors, then we want the predictions S and P to be the same. So we just optimize this while doing the adaptation on the unlabeled target data. We add a self-regularization term, so nearest neighbors don't include yourself, so you should also stay close to what your own prediction was saying at the beginning of the process. So that's what the self-regularization does. We also use a diversity loss, so we want to see again all the classes we had in the source domain in the target domain. And we also, in addition, we looked at expanded neighbors, so the nearest neighbors of nearest neighbors, if that could further help results. So with these tools, we wanted to use these local structures we saw in the embedding space to do unsupervised source-free domain adaptation. Here is the algorithm, which I will skip. So for you who don't know the domain adaptation field very well, here's one of the most popular data sets, Office Home. It has 4 domains: real world product, clip art, and art. This is the Vista dataset. It's a much larger dataset, so it has synthetic objects and real data as a target, about 150,000 training data. And as a third dataset which we use is this point den dataset, which had several point cloud domains with different densities of these point clouds. So to start with the ablation study, I will focus on the Vista here. So then if you add the diversity loss, which is the first tick, you get a jump of 3%. If you then look at the nearest neighbors, you jump to 74. So it's a really huge improvement of the domain adaptation. If you also include this recursive, the reciprocal neighbors, you jump another 6%. And the expanded neighborhood can also give you another 4%. So all these things help to get you final performance. So then we compared it with a set of existing methods. Here on the Office Home, we got slightly better results, or similar results, I would say, as SHOT. But then on the more difficult Vista dataset, we got a decent improvement of about 3.5%. Or sorry, 3%. So it's important to see here, on the left, there is a column which shows the methods, if they use the source data or not. And only the last methods here are made for source-free domain adaptation. And you can observe that these methods are competitive with each other. So actually in domain adaptation, it's not so sure if we really need the source data. So now, I guess it's this CVPR, maybe there is another paper which will beat it, the last source-free, but it's very close, the results. On the 3D data set, we also get a decent improvement. And here we beat several existing methods which were based on source data. So we get the improvement of 4%. So one of the maybe drawbacks of this method is that you need to have this feature bank of all the target data. So we looked at reducing the percentage of features you stored. And we found that, let's say with 5% of the features, you still get a decent performance here of 85.1. So it drops maybe 1% in this case, but then it would speed up and have lower memory requirements than in the case where you want to save everything. So especially if we would even go to larger data sets, I think this is an important observation. So, okay, this is the first part where we show that this local neighborhood structure we see can be exploited for domain adaptation in the absence of labels on the target domain. And this method was found to get good results. So then in the next paper, we will propose a new setting, which is generalized source-free domain adaptation. In source-free domain adaptation, we had this scenario, which you see here. But after adaptation, let's say as a continual learning person, you might think, how good do we do on the source domain? Or maybe we should care about the source domain, or maybe your application does care about it. And normally in domain adaptation, you don't evaluate this. So we propose generalized source-free domain adaptation, where you also care about the performance on the source data. And it has to be source-free again. So in this table, we get the line where we now also care about the source performance, which is the last one. I also put domain incremental learning in this one, which is maybe more known to the continual learning community. Typically in domain incremental learning, you have labels for every domain. And in the case of this generalized source-free domain adaptation, you do not have. But I don't think it's a requirement for domain incremental learning. So you could choose any name here. I think it's close. So, okay, we want to do, this setting where we also care about the source domain performance. We started with a simple source-free domain adaptation method in the same spirit as the last one, where we want the nearest neighbors in the feature space to have similar predictions. So it's this first term in the loss in the bottom. And we have a diversity term, which is this KL term, which is the second one. So it's like a simple version of the previous paper I discussed. And if we look at this performance of this method, then if we look at the target performance, for example, on Vista, it goes up from 48 to 74, so decently. But while doing so, we see that the source performance drops now. It was 99, it drops to 72.1. So we want to maybe use techniques from the continual learning community to see if we can do better than that. We were inspired by hard attention to the task work from Juan Serra, which introduces masks on the attention layers. And we use this ID for domain adaptation. So now we learn a mask while training the source domain. And this mask AS in this drawing is optimized while learning on the source domain. And it makes sure that the neurons between the feature extractor and the classifier are not used all. So it imposes a sort of sparsity on the neurons which are used. So the non-used neurons can then be used when adapting to the target domain. And the neurons which are used in the source domain can be left untouched, let's say. So that's the main ID. So it's just a simple multiplication of the feature extractor FX output, which is then going into the classifier. This is trained, and then during backpropagation, you use this, when you learn on the target domain, you have a target mask in your forward pass, but in the backward pass, you use the source mask to make sure that you do not update the weights which are relevant for the source domain. No? And in this case, it's only a mask. It's not on the weights, it's on the activations of the feature extractor. This method is task aware. So head was in the task aware incremental learning method. We also made a task agnostic method when we used a few exemplars from the source and the target domain. And since these domains are typically pretty different, only with 100 samples, you can do a pretty good classifier. So just to, let's say, the base domain adaptation method, source-free domain adaptation method obtained good results at that moment. If we look at the source performance and the target performance, we see that the target performance goes up. There is forgetting, so the source performance, which is the curve in the top, goes down, but after a while it stabilizes. No? So this mask, since it's only on one position in the network, it still has some forgetting in the backbone. So the backbone can still move, but it remains at least stable after an initial drop. So then for final performance on these data, let's look at the Vista again. We see that the source performance now goes up from 72 to 90. So yes, we did much better. We still have forgetting, so 9% here. More surprisingly for this method is that actually also the target performance went up. And we don't have a good explanation for that actually. We see this to a lesser extent even on Office Home. It could be that not touching the the neurons which are important for the source domain actually makes for a more stable adaptation for the target domain, even if you only care about the target performance. Yeah, we compare these, let's say the task agnostic and the task aware variant, if we have the domain ID and not. And you can see that with this small buffer of exemplars, we can get similar results. So we drop from 87.6 to 87.3 in this case, if you do task agnostic. So if you need to estimate the domain. So from this, we have a source domain and a target domain. We thought, okay, we can also continually do this and get to continual source-free domain adaptation. And we did this with a number of domains. So this can be repeated, this process. And here we do it on the Office data set, and it has 4 domains. So we only have labels for the first domain, and then you do unsupervised domain adaptation to the second, third, and fourth domain. And you get some table like the one you see here on this slide. So the first row has the performance after training only on the labeled source data. And you see that for the task 2, 3, and 4, for example, for clip art, it doesn't do so good, so 42. So when then unsupervised adapting to clip art, this performance jumps to 56. It manages to maintain most of the performance on the original data set with 71.4, and etc. And it goes on the other tasks. So I think this is an interesting setting. So this unsupervised, generalized unsupervised domain adaptation, and using this post dimension attention is one technique which really helps to prevent forgetting. So for the final part of this talk, it's a paper we recently put on archive towards open set recognition on the domain shift. And typically, often we evaluate things in a closed set situation where the training classes are the same as the target classes. But in open set recognition, you also allow to get test data which you haven't seen during training. No? And then for this data, you want to say it's an unknown class. I don't know about it. So in domain adaptation, we go from one domain to another domain where there is a shift between the 2 domains. And then there is the more difficult situation, even which is called universal domain adaptation, where you go from one domain to another domain. But now in both domains, you are allowed to have private classes. So the source domain might have classes which are not in the target domain, and the target domain might have classes which are not in the source domain. So this makes the whole adaptation process even more challenging. So with this method I present now, we can look at 3 of these settings. So here we have a table which distinguishes between 3 factors. Are the classes in the source and target the same? Do they have the same distribution? It's the second column which distinguishes, which makes it domain adaptation. And transductive means, am I allowed to adapt to the target data? So there is some work, and at 2020 there were 2 papers on this subject, and they what they propose to do is train, let's generate out of distribution data. So that what you see here on the left, they combined classes to make imaginary classes. So a MAC and a back image were combined to make an imaginary class, and this was added to the classifier. And by doing this, you can now learn a classifier, and you see the result on the right. The blue classes are in distribution classes. The yellow classes are, let's say, out of distribution classes, which they made up by combining in distribution classes. And now this classifier, let's say, it's more precise. No, it makes room for unknown. So everything which is yellow would be actually unknown class. So this is very nice. However, you have to come up with this maybe complicated way of making these out of distribution data. So we were thinking, can we do this get the same result? Problem of generating classes. And looking at this, so here the in distribution classes are blue. Oh, that's maybe not a good idea. Let's see. The in distribution classes are given in blue. The out of distribution maybe here are in yellow. And what you see is that, let's say the nearest neighbor of every class yeah, first of all, it's itself, but then it is an out of distribution class. So that's how you make this space between the classes. No, so we come up with this, let's say, simple observation that the second closest class for every in-distribution class should be the unknown class. And why is this useful? This allows us to train a classifier which has the in-distribution classes, but also has an unknown class. And how do we train this? We first train it by cross-entropy loss, which pushes the ground root label to be the first class which is estimated. And then we have a second cross-entropy loss where we remove the label, the ground root class, but of all the other classes it could predict, it should, as a second class, predict the unknown class. So we push for all images in the source domain to have as the second most probable class, the unknown class. And by doing so, we can learn a classifier which includes the unknown class, which doesn't need any data for the unknown class. Yeah, here is an example of training a normal cross-entropy loss. On the left, it is three classes here, black, red, and blue. And we put a out of distribution class, which is purple. This one, in principle, could be placed anywhere. And you see that the cross-entropy loss finds nice decisive boundaries. And that our loss found here, let's say this unknown class, also makes nice space between the classes to say areas where it's not sure about the class label. So in this case, it would correctly label these pink points or purple points as unknown. So this is an overview. The method doesn't require any generating of out of distribution data, so that's its main advantage. And it simply enforces the unknown class to be the second highest predicted class. So this can be used to open set recognition, where you directly evaluate on the target domain your model trained on the source domain. And here we compare with a number of methods. Here this ARPL number 5 is a PAMI of last year. And we see that we get slightly worse results, but pretty close with this very simple idea of just using these two cross-entropy losses. You can also do this open set single domain adaptation. So now you have domain adaptation and you have new classes in the target domain, but you're not adapting the model. So you're only training on the source data. So in this case, I draw this in the bottom. So the blue is the source data, green is symbolizes the classes of the target data, and you see that the source data only has part of the target classes. If we do this, then we get an improvement over the state of the art of 12% in this setting by using this method. Now, for the more challenging setting of universal domain adaptation, here you have unknown or classes in the source domain which are not in the target domain, and classes in the target domain which are not in the source domain, and you are allowed to adapt, or you're supposed to adapt to the target data, which is unlabeled. So we propose to do first to adapt both by doing an entropy loss on the known classes and another entropy loss on the unknown classes. So again, we want the prediction to be sure about its outcomes. So we just say the classifier should be sure about what classes it's, or should be sure if it's unknown or not unknown. In addition, we also combine it with a source-free domain adaptation. Another paper we published on Archive this year. I will not go into details here, but it's similar like the other ones I discussed. So here are the results. So OVNet was a method, I think, of ICCV last year. It needs source data, so we do not need any source data. And here, if we look at the harmonic mean, so which is the mean between it's the mean between the source and target, the accuracy on the known and the accuracy on the unknown classes, unknown class. Then you see that we get an improvement of 13% over this method. Yeah, and this is the results on Office Home, and also a decent improvement of 8%. Interesting here is already that only the source model does actually very good, 76%, so without any adaptation at all. So in conclusion, here we propose a simple method to do open set recognition. It simply enforces predictions for each of the data points in the source domain to have as the second most likely class the unknown class, and this really seems to work pretty well. It doesn't have a hyperparameter, so normally you would maybe need a hyperparameter on the entropy of your prediction. It gets state-of-the-art in several data sets. So this is the things I showed today. Finally, let's say unsupervised continual learning would be maybe the objective. We have another talk on this at this workshop, so I hope you will all be there. And in conclusion, I think source-free domain adaptation, it's a very similar setting as continual learning. So you're also not allowed to use source data. They have another set of tools. I think it's very interesting also to do more unsupervised continual learning. So maybe this setting where you have labels in the first domain, I think also that's a very applicable situation. So you might on the devices you no longer have labels. We have proposed several methods, and finally, yeah, let's say we have proposed one method also to do out of distribution or unknown class detection, which obtains very good results for universal domain adaptation. And yeah, I want to thank Shiji. He is the first author of all of these works, and my other co-authors on these works, and as well the sponsor for this. Thank you all.
All right, thank you so much, Just, for the great presentation. So we have some time for questions. So if you have questions, you can go create a line on the mic, or if you're attending remotely, you can write in chat and I will ask the questions myself.
First of all, regarding the source training for IQ but also on the other ones, the final results seem to be very sensitive to how you train source. Over training the source or improving the source performance does not improve the final adaptation results. How did you choose your source training strategy? How did you know when to stop training the source?
Yeah, so in the domain adaptation community, if I'm correct, I think you just use a cross entropy loss on the source data. And recently there are some works which use other strategies like self-supervised learning, which also generalizes better. So in principle, most people try to use the same method on the source domain to make methods more comparable for domain adaptation, or even use the same network. So in this case, yeah.
So how did you do it, for example, in short, how did you choose the strategy? How did you decide how to do it?
No, it's just a cross. You just train your cross entropy with the source labels on the source domain. Yeah, classification.
So second question regarding the pre-training model. Usually people take a resonance 50 and pre-train from PyTorch. So the baseline is very low regarding the source only. And then, for example, in short, you reach 72.5. But if you take a pre-trained model a little heavier, you can get even on the resonance 50. And source only accuracy above 80. I'm wondering, does the benefit of adaptation saturate when the source free is so high? Are there any results of it?
Yeah, that's a good question. Yeah, I'm not sure. Yeah, I would actually expect it not to. I would still think that the domain shift is very bad. Also, maybe even worse for larger data sets, for larger networks. So I don't think they have a better generalization to other domains than smaller networks. But that's not, this opinion is not based on actual experience I run. Yeah, but yeah, it's interesting to verify. I agree. Yeah.
More questions? That's fine.
You traced a very nice connection with the domain adaptation community, right? You see some new insights we can gather from this community towards supervised learning. And so, why did you make this explicit connection? Is it because of your background? Is it because there are many insights, things we can learn from the domain adaptation for the future in this area?
Now, yeah, I think especially if we want to go to, let's say, unsupervised continual learning, where you maybe have labels at some points, but not anymore for all the domains. Yeah, then actually, I think this domain adaptation communities may be already ahead of continual learning. That's really what I do. I'm self, this entropy loss, which is super elegant and easy, it would be nice to do more experiments also within continual learning context. I think that's one of the other things. Yeah, that would be my main two things at the moment, I think.
Thank you for the talk. I just wanted to ask, so in your results, you showed that source free and using source both have similar accuracy in domain adaptation, especially in the first paper, I think. Is there any analysis on why that is? Like, has it been shown that we don't really need source domain when we're doing domain adaptation?
Yeah, I think there hasn't been, let's say, I don't think this analysis is there, but I think, let's say this, the fact that you had the source domain data, a lot of focus in the beginning was to get them, let's say, features which are invariant for both domains. And I don't think these are optimal, no? You want, because you might lose a lot of the discriminative power of some features which are good for your target domain, but not for your source domain. And domain invariant features are not allowed to use these, no? Because immediately, let's say, if you think in domain invariant features, these features which are only discriminative for the target domain are by definition not domain invariant. So I think that maybe that focus was wrong, or not complete yet. I think maybe because of that reason, but yeah, I don't think there is a good answer. Yeah, many, let's say, also reviewers always ask for that. There is a feeling that you should be able to do something with the source data, no? But yeah.
In the second cross-entropy loss pass, when you're kind of adjusting towards the last step and remove the truth bus, it seems. Right. I was wondering what your opinion is on whether or not that makes it more robust or less robust when adversarial exploitation. I think you make an argument either way. In this case,
Yeah, I would think more robust maybe, because okay, you're robustifying, you're being more exact about what you really consider to be the classes. So there are no, let's say, there is, you're more honest about the whole region, which you say it's unknown, no? So I would say more robust. I don't know how you would argue towards the other direction.
More robust, right? After some thought, I think we could make a comment on it.
Good. Okay, yeah.
Right. If you don't have any questions, I think we can thank you for the great presentation again. And
Okay. All right. So the next speaker for this session is Siddharth. Siddharth, I can see you there on Zoom, so we should be okay. Great. So you can already share your screen. We can see your slides. Let's try the mic. Can you hear us? And you can speak. Yep.
Yes, can you hear me?
Okay, great. We can hear you
Great.
well. So Siddharth Zwaru is a young and talented PhD candidate in the Computational and Biological Learning Lab at the University of Cambridge. And his research interests are about designing algorithms for large-scale machine learning systems that can learn sequentially without revisiting past data. And are private over user data and are uncertainty aware. And this talk today will be about knowledge adaptation priors for continual learning. So with that, let's give Siddharth a round of applause, and please, the stage is yours.
Thank you. So as said, I'll talk about knowledge adaptation priors for continual learning. And first off, I feel like I'm missing out not being able to be there in person. It looks great. I'm currently in the UK, but I'm actually going to be moving to the East Coast in America in a couple of weeks' time. So if you're around there, then please email me. I'd love to meet up. But this conference came just at the wrong time while I pack and get ready to move. And as a side note, before I start, a lot of this talk is going to touch on parts that I've written up in my thesis, which is referenced at the bottom here. So if you're interested in reading more, I recommend you look at that or email me or whatever. So by now, we've heard about many different parts of continual learning and types of adaptation and so on, and I'm sure we will hear much more in this workshop. But I mean, one thing is key throughout is that we know that intelligent systems need to adapt quickly to changing environments, and they want to do this while still remembering previously learned information. So in this talk, I will focus on the case where data is constantly arriving and we want to update our model accordingly. For example, one can consider the spam email classifier where new spam emails are arriving every day, or consider an image recognition system trained on images from the web. New images are constantly being uploaded, and we would like to update our model to account for this. Always, we want to use neural networks, of course, as they perform very well in many settings, such as image classification. So a little more formally, this talk is considering the case when data arrives sequentially and can change with time. We crucially cannot store all of our past data, whether that is for computational or privacy reasons. And unfortunately, standard deep learning methods quickly forget old information when training on new data, as we've heard already, and this is known as catastrophic forgetting. And we want to design methods to overcome this. There might also be other properties we want our systems to have, such as forward transfer, where we use previously learned information to improve performance on a new task, and backward transfer, where we use new information to perform better on old tasks. So let's consider an example to make things more concrete. So in the small scale split MNIST benchmark, there are 5 tasks. In task 1, we see the 0 and 1 digits, and we perform binary classification. Then in task 2, we see digits 2 and 3, and so on, without being allowed to store all past data. And each of the 5 tasks introduces 2 more digits. So vanilla deep learning methods such as SGD or ADAM would catastrophically forget previous digits. Previous work has identified a few different learning scenarios within this setup. When it comes to test time, we can provide the system with knowledge of which task a digit belongs to. For example, when providing the digit 8 at test time, we can tell the system that the digit is either an 8 or a 9 and require the system to always perform such binary classification. And this is known as task incremental setting or task incremental learning. And it can be realistic in some sort of restrictive settings. On the other hand, in class incremental learning, we do not tell the system which task the digit belongs to. So when we provide the digit 8 at test time, the system has to perform full 10-way classification, and this is strictly harder than task incremental learning and is more general. But the most general continual learning setup, as previous presenters have also mentioned, would see data arrive sequentially with no concept of tasks, perhaps 1 or a few images or data points at a time. However, having gone through all of these in this talk, we're going to focus on the easier task incremental learning scenario, and we will look at some Bayesian approaches for this. I mean, we would like to eventually move to more general settings, and the later approaches that I'll mention in this talk can be applied to the more general approaches. We will compare methods performance on split MNIST. We will also consider split CFAR, which consists of 6 tasks, 10 classes each. Classes are from C410 and C4100. So both of these benchmarks are relatively small scale, but I include them and I want to give sort of performance because I want to give some ideas of performance while sort of mostly focusing on theory in this talk. So let's start by looking at two non-continual learning baselines performance on these two benchmarks to get an understanding of how hard the benchmarks are. The separate tasks baseline consists of a separate neural network trained on each task's data separately, and therefore requires storing many models with no potential of transfer of information between them. The joint tasks baseline trains a single neural network on all data at once, and therefore it breaks continual learning as it requires storing all data. And it can be seen as an upper bound of performance. So on the left is split MNIST here, and we see that both separate and joint tasks perform very well and very close to each other, because split MNIST is very easy. For split CFAR on the right, there is a bigger gap between separate and joint tasks, showing more potential for forward and backward transfer in this specific benchmark. All right, so many methods have been proposed for sort of this kind of continual deep learning over the past few years. These methods can be broadly split into three approaches: regularization-based approaches, rehearsal-based approaches, and architecture-based approaches. So here I've listed a non-exhaustive list of methods, just some. I mean, there are very many methods out there, and what approach each of these methods correspond to. Regularization-based methods on the top left, they usually regularize parameters by penalizing against large changes for parameters that were more important for previous tasks. So examples include elastic weight consolidation and variational continual learning, amongst many others. Rehearsal-based approaches in the top right either store a core set of examples from past tasks and replay that, or they train a generative model and rehearse pseudodata from that generative model. And architecture-based approaches at the bottom, they change the neural network architecture directly, such as by introducing new parameters for new tasks. These methods often freeze old parameters and train only new parameters on the new task. So in this talk, we will start by considering Bayesian approaches to weight regularization. We will then discuss how these methods can fail. This helps motivate us to combine weight regularization with function regularization or with rehearsal-based approaches. We will consider knowledge adaptation priors or K-priors, which allows us to look at the error induced by limited memory, the error from an ideal solution. And Bayesian principles are always going to be in the background of the talk. So let's start by looking at why a Bayesian approach to continual learning might be beneficial. Here I have written out Bayes' rule after we see data from task 1, x1 and y1, that's the data. The posterior over weights W is proportional to the likelihood of data multiplied by the prior of the weights. Now let's imagine that we were allowed to see both task 1 and task 2's data together. When we write out Bayes' rule, we see that the new posterior is proportional to the likelihood of data 2 multiplied by the likelihood of data 1 multiplied by the prior. And the last two terms are repeated from earlier, and we can replace these terms to give us a new equation, where the posterior after task 2 is proportional to the likelihood of the new data multiplied by the previous posterior given data set 1. Crucially, we no longer need to access data set 1 directly, and therefore we satisfy the requirement of continual learning. However, exact Bayesian inference is not possible, especially in neural networks, so we need to make approximations. So let Q of W be the approximation of the posterior. And we're going to imagine that's some kind of projection of our true posterior. For example, it could be a Gaussian. We will consider Gaussians mostly in this talk. So we can replace the previous posterior of a data set 1 with our approximation Q1 of W, and then run approximate inference again after we see task 2's data with the likelihood of data 2, and we get Q2 of W. And again, we got this without having to access past data set 1. So what kind of approximations can we make? We could use a Laplace approximation, where we calculate the new weights, WT, using a loss function consisting of a new data term, this is the log likelihood, or negative log likelihood, and a weight regularization term given by the old posterior qt minus 1 of w. The covariance of our new Gaussian, sigma t, is going to be calculated at our new solution wt. And it sort of takes this kind of form, and it depends on the previous covariance as well. Many methods, such as Laplace propagation and online EWC and so on, use this kind of approximation, and we will focus on mostly this in this talk. Hopefully this kind of loss function is familiar to many of you. However, we could also consider variational inference as an approximate Bayesian method, where we jointly optimize for the mean and covariance of our Gaussian, Qt of W. So here the objective function is slightly different. There's an additional expectation of Q of W. There's still this new data term, weight regularization term, but then there's also this entropy term, log Q of W. So variation inference methods have shown promise, such as with variational continual learning. We won't discuss this approach too much in this talk to keep things relatively simple mathematically, but I note that because all methods in this talk will have a Bayesian interpretation, it is actually a relatively small change to go from the methods I discussed in this talk and then from the effectively Laplace kind of style, and then run them in a variation inference style. Okay, let's get straight into it and see how our weight prior approaches fare on two benchmarks. We consider EWC, which is the Laplace approach, and Vaughan, which is a variational weight regularization approach. Both perform similarly on split MNIST on the left, getting sort of just under 99%. And on split CFR on the right, the variational method is a bit better than the Laplace method, but both are, I think, short of the joint task performance, showing potential for improvement even on split CFR. So now I want to discuss why these methods may be performing poorly, even at the split CFR scale, and this will motivate ways to improve performance. So I now argue that weight prior approaches fail, even at the scales we've seen so far, because they have independently regularized weights across layers in the neural network. So to get some intuition, let's look at a cartoon example. So in this cartoon example at the bottom, this is just a single unit in our neural network. It's got an input, it's got inputs, so we're just going to consider one of the inputs X in, there are some others. We're going to consider one of the outputs X out, there are others. And after training on previous tasks or previous data, we have some kind of independent Gaussian distributions over our weights. So Wn is the weight corresponding to the input X in, it's got some kind of Gaussian, W out is the weight corresponding to X out. And so when we see new data, these distributions are going to be the prior, and this is what we're going to regularize towards. In particular, the width of these Gaussians indicates how strongly we regularize when training on the next task. So now let's see new data. And now these distributions are going to change. So consider when the input weight distribution, W over Wn, moves slightly towards the right, just as a cartoon example. So here it's moved to the blue towards the right. Ideally, we would regularize towards maintaining predictions X out over our previous data. And this would lead to a signal to move the output weight W out towards the left. So that sort of cancels out the fact that the Wn moved towards the right. However, as the two weights are independently regularized, the distribution over W out may not move sufficiently. For example, if W out has small uncertainty, it's very tight, then W out may be overly regularized and our predictions X out will not be maintained. This can lead to poor performance at even medium scale benchmarks, and we saw poor performance in split CFR. This applies to all methods that regularize weights independently across layers, not just the ones that are motivated using a Bayesian lens. And this motivates us to directly regularize outputs instead of just the weights, specifically independently regularizing the weights. There are many methods that regularize the outputs or functions, but we will look in detail now at knowledge adaptation priors. So, knowledge adaptation priors, or K-priors, are a class of priors that were designed for quick and accurate adaptation of models across a wide variety of tasks. They take in some kind of base model trained on past data, some kind of small memory, some memory inputs, and then update the model over the adaptation task. So the adaptation task could be adding some new data, removing old data, changing the regularizer, changing the model architecture entirely, for example. So all these adaptation tasks are interesting for deploying models to the real world, but let's focus on the add data task like in the rest of this talk. I'll also note that I will mostly talk about some new ideas in this talk rather than talking about the theory behind K-Prize and its links to other works, which are all summarized in the paper. And my co-author and I have also given talks at other workshops on K-Prize, so please look that up online if you're interested. So in the add data task, the K-Prize takes this form. It has a new data term as before, and then it has both a weight regularization term and a function regularization term. And they are both divergences. That's what these Ds are. So the weight regularization term has some kind of making sure the weights don't change too far from the previous weights WT-1, and similar for the functions. The outputs don't change over the past data. So for supervised classification, I can write down exactly what the K-prior would look like. The weight regularization term is some kind of L2 loss where W is being kept close to WT-1, the past weights. And then the function regularization term is the normal loss, L, but with soft labels from the past model WT-1 instead of hard labels. Why do we use this exact form of K-priors? Like, where does this come from? So this comes from wanting to exactly reconstruct past gradients. And in fact, we showed in the K-priors paper that this loss exactly reconstructs past gradients on generalized linear models when we store all past inputs in our memory. Now, of course, that comes with a big addendum. We are storing all past inputs, but this allows us then to reduce the memory size and allows us to analyze how much error we are inducing as we reduce the memory size. And therefore, we can start thinking about how to reduce this error. I think that this is a very important way to approach continual learning, as it gives us a framework within which we can provably reduce the error and improve performance. And so in the next couple of slides, I will show how recently we've used this framework to suggest new ways of combining previous methods. And I'll look at combining online Laplace methods with function regularization. There is an additional error term with neural networks, but we can still write the form of this error term down and analyze it. In fact, as some of you may have noticed, the K-prior loss is related to knowledge distillation and such methods in continual learning, such as ICAL, learning without forgetting, dark experience replay, etc. I don't have too much time to go into this in this talk, but please look at the paper or previous talks for more information. So let's consider when there is a limited memory M, which is a subset of the past data set D. We can write down the gradient error, which is the sum over the data points that are in D but not in our memory set M. So this is the sum of the data points not included in our memory M. The phi i's here are features or Jacobians in the case of neural networks, and the error, as written here, depends on the prediction disagreement between the current outputs given by weights W and the previous outputs, or the previous weights WT-1. But we can't work with this term directly, as we do not know what our new weights W will be before we start training on new data. So instead, we can make a first order Taylor series expansion. And this gives us this equation. The H primes here are the second derivative of the loss function, which is usually very simple to calculate. For example, in classification, this is P times 1 minus P, where P is the output. In fact, this entire term in the square brackets is a matrix called the generalized Gauss-Newton matrix, calculated at WT-1, or as I've noted here, GWT-1, calculated over inputs not in our memory. It is independent of our new model weights W, and so we can use it to choose points to store and hence reduce the error from using a limited memory. In the K-prize paper, we used a very simple method. We simply sorted and chose points by this H prime value, and we saw pretty decent results. But now I want to talk about how we can use these insights even more than in that original paper to reduce the overall error further. And we will do this by changing the objective function itself. And just to emphasize once more, we're able to do this because we are quantifying the error exactly and hence reducing it. So the idea itself is simple. We're just going to add the error back onto the k-prize objective function, and it gives us this form, and I'll go over it. So this new data term is the same as before. This function regularization term is also the same as before. It's over inputs in our memory, and it's got this soft label. The only difference is the weight regularization term, where we now have this generalized Gauss-Newton matrix at Wt-1. The rest of that weight regularization term is actually the same as before. So we call this the quadratic k-prime, and we know that this will have less error than the vanilla k-prime because we've added back a first order approximation of the remaining error. We can get some intuition as to what is going on with all of this by considering a few cases. So when we store no points in memory, it turns out we actually exactly recover weight prime methods such as online Laplace and online EWC or so on. This is an appealing property as we know that these methods can perform at least decently in continual learning. When we store all data points in memory, the Gauss-Newton, the matrix is actually equal to 0 because it's calculated over 0 points. And we go back to the vanilla k-prime from the k-prime paper, and we know that this is exact and will recover a good solution. So this is also an appealing property. And then in the interesting case, when we have a small subset of points stored in memory, then we want to perform, then we perform function regularization over only a few points. We want to choose points for which the calculation, the Gauss-Newton matrix changes the least, or put differently, the points for which the predictions change the most. The other points, such as the points which we will always classify well or are very typical of the class that they are in, these other points are not so important, and they can be included in the weight regularization term and dealt with in the Gauss-Newton matrix. We only need to find, pick, and functionally regularize over the more interesting points. And this is the same reasoning as before in our previous slide. So as this is a new method, I don't have proper results for you yet, but I did just want to show it performing on the tiny benchmark of split MNIST. So on the x-axis, as we increase the memory size per task that we store, we see that the quadratic k-prior in black squares gets better and better, and is always better than the weight prior here. That's online EWC. So there is ongoing work where we are applying this method up to ImageNet scale with promising results so far, but so hopefully I'll be able to share those results in a paper soon. All right, so in summary, we started by looking at how Bayesian approaches can naturally handle continual learning, but we also saw how weight space approaches can fail, and that's because they are independently regularized, and these are sort of the approximations we have to make to scale to large neural networks. We then looked at knowledge adaptation priors and how it's useful to look at the method's error from an ideal solution and look at the error as we decrease the memory size. And just a note on future work, we're looking at scaling some of these ideas up. I'll just end with some acknowledgements. I'd like to thank Richard Turner and MT Khan for all their chatting and collaborations over the years, and also thanks to many people who have contributed to work I presented. So Eric, Kazuki, Runa, Miguel, Rio, Tang, Kung, Pingbo, and Alex. Thanks.
Thank you so much, Cedar, for your great talk. So we have time for a couple of questions. You can ask remotely by writing in the chat or just opening your mic. And yeah, we have one question here from the audience.
Hi, Cedar. Thanks for a really nice talk. In terms of the objective for the knowledge priors, you have the weight and the functional regularization. Now, when I played with these methods, I noticed that this regularization terms intransigent. Otherwise, it's very difficult.
Sorry, I can't really hear you very well.
Okay, is this better?
It's slightly better, yeah.
Okay, I have a question about the objective. The final objective is both a weight and a functional regularization. And playing with methods that have either weight or functional regularization terms, I noticed a certain type of intransigence. In other words, it's difficult to learn future tasks. Is that something you observed as well? And if so, what is error that you suggest?
You're saying it's difficult to learn future tasks with these methods?
Yes, that's right.
Yeah, I haven't particularly found this issue. I mean, so when it comes to weight regularization methods like EWC, people typically have a factor in front of the log prior term, which is some hyperparameter that they tune, and this actually is normally quite high, between like many orders of magnitude, like 10 to the 4 or something. And that's to make sure that you remember past tasks better. So I've actually found the opposite, if anything, that with weight regularization especially, you might forget past tasks if you don't weigh it up. With K-prize, I haven't seen this to be an issue too much. Function regular, so that's obviously doing function regularization in a specific way. Perhaps if you do it in other ways, you may have to have another hyperparameter and increase that.
Okay, any more questions? Nope. So thank you so much, Siddharth, again. And now I invite on stage Bartolomiej Twardowski, who is a PhD student working with Just van de Beers, as mentioned, in same lab. And he will talk about continual learning, self-supervised representations with projected functional regularization. So here, I think we can share the slides here. Or, oh, you're inside, right? Okay, great. But before that, actually, yeah, to share the screen again. Good. Let's show. Thank you.
Thank you. Thanks for the introduction. This work is done in a bigger group with Alex, Lou, Andrew, and Jost. And yeah, I will talk about the continual learning of self-supervised representation with projected functional regularization. So in general, continual unsupervised representation learning is not an easy task. If we got all of the data at once, the task is quite simple. We can jointly train, and this is common, right? But if we have the stream of different tasks, the task is going to be more difficult, especially like if we don't have the hint about the task. So then we're moving from task incremental learning to class incremental learning. But learning representation is far harder, especially in an unsupervised way. And in this work, we do not use exemplars and we do not change base architecture. And during the poster session, there was one good question. We as well do not use the pre-trained model. So that's our assumptions. And if we go outside the lab, so continual learning can address some of the problems, but like having vast amount of data without the labels is another one. Here we can use the self-supervision. And one of the motivation is for sure the latest improvement in self-supervised learning method, especially those based on the continual learning, where we can see that the gap between the supervised and current approaches are quite small. It's closing. Yeah, it was, I think, December 2020 when we actually started with SimSciam method. We simply take SimSciam because first it requires small, like it doesn't require large batches, but as well it do not requires negative sampling. And this feels like perfect for continual learning, right? So we simply done fine tuning and the results were quite promising. So we continue with that. So what we can do next? There are some well-known methods, right, for the class incremental learning. Basically, if we're talking about functional regularization, we can use learning without forgetting. In a weight regularization, we can use EWC. So this can be applied to self-supervised learning method, but you need to make some decisions. So for example, for the learning without forgetting, we try to mimic the output of the old network with keeping some of the distance on the feature level. So we called it feature distillation. For the unsupervised EWC, basically you need to calculate the feature information matrix with the contrastive loss. That's all about the adaptation here. But okay, keeping the new backbone with the feature distillation, like based on the distance, feels like it's quite strict, right? It's like do not allow to have too much of the freedom. So we started to investigate what will happen if we introduce additional projector. We call it temporal projector here. For us, it's nothing like, it's in general, it's nothing special. It's 2-layer MLP with non-linearity. But this enforced that the new backbone is learning new things. So it's encouraged plasticity. And in general, the method itself, it's very similar to learning without forgetting. We as well got the same hyperparameter here, lambda. That's it. So the first result is like the base experiment for us on the Cypher 100 and 4 task split. Here we got like joint single train and fine tuning for a reference. We can see that both feature distillation and EWC not so much, but feature distillation gives better results. But if we use our method, PFR, the results increase. Below, we can see the evaluation on a downstream task. The task is the same, it's still classification, but the data set is different, it's household number. So it's 32 by 32 size. And we can see that here as well, the PFR is still very good. What interesting here is that fine tuning here is actually the value is quite similar to joint train, but we saw that in a different paper. So yeah, this is interesting. On the right, we can see the task-aware accuracy matrices. And PFR gives not only the good forward transfer, but on the right bottom corner, you can see that we receive as well a good backward transfer here. The method is generic. We applied it to not only, I already said that we started with SimSciam, but we applied with it with Barlow twins and as well with SimClear. All of them are giving some of the improvements if we apply PFR. We couldn't afford to go for the full ImageNet. So this is like there were some of the experiment that we could make. So this is tiny ImageNet, 64 by 64. We couldn't afford mainly because of the computational reasons. But here as well, we can see that PFR is doing a good job. And the downstream task, we evaluated on few more data sets because here we took cars and aircraft as well as other data sets. And we just simply resized to 64 by 64. And we see that PFR is still the best method. So one question can be asked, like maybe we cherry pick the lambda to present the best results. So we were thinking how to present it in a way that we can say that it's not that. So in this plot, we have the forgetting and intransigence. So the best area for us is to be on the bottom left corner. So almost zero forgetting and the best plasticity. So very low intransigence. The referential point here is the fine tuning. So for example, you can see if we increase the lambda for EWC, we fighting with forgetting, but intransigence is getting to bigger. So it's like a trade-off as always. And if we compare PFR to FD, so you see that we are still better, we are still on the better side of the plot, especially when you look on the right where the difference is
No
quite
way.
clear. Okay, I will continue. So this is the last experiment, but I think the most interesting one. So here we do the split with 50 tasks and 100 tasks. 100, it means that we only have like one class per task. So in each iteration, we only have data for a single class. And we can see that on the red, we see the PFR 100 task, that even in this long training session, the discriminative power is still very good. Conclusions, we propose new method, projected functional regularization, that encourage plasticity in self-supervised learning. We evaluated with different data set and scenarios and proves that the method works. The method is not connected with any of the approach for the particular approach for self-supervised learning. For the next direction, applying this for the task-free setting for sure will be interesting. Using different backbone architectures and maybe with the reply buffer. But for me, the most interesting would be to understand what's happening with the projector. We've done some analysis, but so far we don't have the conclusive results. Yeah, if you find this work interesting, so this is related one. This is not advertisement. Like this is an advertisement, but I don't know the authors. Yeah, that's it. Thank you.
Thank you. Thank you so much for the very interesting talk. I think it's one of the most exciting areas in continual learning nowadays. So that really nailed it for the workshop. And so do we have some questions from the audience or remotely? And I have to mention this was an oral, the first oral of the day related to a paper that was actually published at CLVision. And so we will have more presentations, orals as well in the afternoon.
Yeah, so I was interested to ask by the projector. So talking about the installations, like that we tried multiple layers, multiple modules, like how do you learn the
Yeah, so we try to analyze the projector, and while doing this, we try to change it for the just linear projector. We try to do the SVD decomposition to understand what's happening with the dimensionality, but we got few hypotheses, but as I said, it was not conclusive. We couldn't make anything that we can, you know, put in a paper, and it's like we agree with that.
I also have one question. So you explained that this method is agnostic, let's say, to the specific self-supervised learning strategy, let's say, behind it. But do you think that some approaches, some methodologies may be more useful, may provide a bit of an edge, let's say, to this specific method or for your next endeavors?
Yeah, there is vast, like right now we see like more and more of these methods. Yeah, I don't know, like our first intuition was to use the SimSciam because of the lack of negative sampling. So that was perfect candidate. But at the end, our intuition was not so good because we ended up with Barlow twins, which is more pleasant and more stable to train, basically. So yeah, I cannot say like there is a rule of thumb to.
Yeah. So thank you so much. And so let's thank everyone, Bartholomew, for this great talk. So this ends the morning session for the Continual Learning workshop today. We have 1 hour break, and then we will come back at 1 p.m. To hear from other great speakers like Bing Liu, Fabio Cermelli, Jonathan Schwartz, Alexei Ostapenko, and the challenge results. So be ready to start for the afternoon session at 1. Thank you. Just 1 hour. Maybe I don't know if it's stop the recording. Maybe the recording can be stopped.
Hi, Professor Bing. Can you hear us? Yeah, your microphone is still muted. So,
okay, yeah, sorry. I'm here.
There you go. Okay, maybe you can test if you can share your screen.
Share my screen, okay.
Great.
Is it okay?
Yeah, that's perfect. Thank you so much. So we'll start in a couple of minutes. I'll first introduce you and then we can get started. Okay, thank you so much.
Can you make the slides slightly bigger?
Yeah, like open better. Okay. That's
Waiting for something, just waiting for that thing to fall in through there. That's right.
All right, welcome everyone for the afternoon schedule of the workshop. Today it's my pleasure to announce Professor Bing Liu, the distinguished professor of computer science at the University of Illinois. at Chicago, and he received his PhD in AI from the University of Edinburgh. Before joining the UIC, he was an associate professor at the School of Computing at the National University of Singapore. His research interests, of course, include lifelong and continual learning, but he also has a vast background on sentiment analysis and opinion mining. He has too many awards to name, but to mention, he had like 4 Test of the Time awards. And of course, he's really known in the community for his go-to book of lifelong machine learning. So Professor, it's our honor to have you here, and the floor is all yours. Let's introduce him with a warm applause.
Thank you very much for the invitation and also for the introduction. So today I'm going to talk about post-deployment continual learning. Basically, we're going to talk about something which is after the system has been deployed. So the traditional machine learning basically does this sort of isolate single task learning. We have a task, we have a data set, and we have a learner, and the learner build a model, and the model basically goes to application. So we're all pretty much familiar with this, and this kind of paradigm has a number of weaknesses. The first one is non-continuous learning, and which we are all familiar with. And the second one is a closed word assumption, because the traditional machine learning assumes whatever you see in testing or in application must have been seen in training. Okay, so if you see something in real life that is unexpected, and you can't really deal with it, and what you have to do is wait for the next retraining cycle, and probably some additional data will be annotated, and then you retrain the system. And of course, this is basically lead to the third one, which is there's no learning after system is being deployed. So in the current continual learning, what we are doing is basically kind of deployment continual learning. So we're learning a sequence of tasks incrementally, and we're dealing with sort of catastrophic forgetting, and we also try to achieve the knowledge transfer. So this is what we are doing now mostly. So if we look at this pictorially, and we have a sequence of tasks at the top, and then we are learning a particular task at a particular moment, and then we have the data set, now we have kind of continual learner, and we have a knowledge base, and also we probably can leverage the past knowledge. And of course, in different implementation, you may not have this explicit knowledge base, but in some other cases, you do have explicit knowledge base. And then after you done this incremental learning, and then you basically go to the model, produce the model, and the model goes for application. So this is what is a sort of kind of deployment continual learning, because here, after deployment in the application, we don't really see anything. Okay, we don't really see anything. So this is what we call the pre-deployment continual learning. And one of the major sort of feature is one of the major characteristic is that the task and the data are given by the user or by the engineers. Okay. However, in real life, when we actually goes to application, and then we'll have lots of issues, and we cannot really deal with the unexpected situations, although we need to deal with those things in order to learn continually. So here is an example of self-driving cars. So when you have a self-driving car, and you basically drive the car, and then you probably see something unexpected that you can't deal with, then you probably have to manually take over, and then you go home and then basically retrain the system and deal with that problem. However, this kind of approach is just quite impossible to cover all corner cases, but in the real life, real world applications are full of corner cases. So in order to sort of learn after deployment, the system really have to adapt and have to interact with people and with the environment in order to learn more and more. So this is a personal experience. It's a real experience. I worked for a self-driving car company for 1 year. I was consulting for them. So once we took the car to a field test, on the real road, and when the car comes to a sort of T-junction, and the car just suddenly stopped and refused to move. And then we basically look around, there's nothing in front, nothing at the back, and the left and the right, there's nothing, everything is clear, everywhere is clear. So we couldn't, as a human being, we couldn't really see anything which is sort of could stop this car. And So we had to get a driver to manually take over and drove the car to the lab, or we go back to check. Now we find out there was little pebble, which was discovered, sort of basically detected by one of the sensors on the road. And then the system basically stops and doesn't tell us anything, and then we have no idea what's going on. Okay. However, if at that particular moment, if the system can tell us, says, I detect an unknown object on the road, and what should I do? Is it safe to drive or not safe to drive? So in that case, actually, the system detect that thing. Okay, it's not something which is not detected. So system detect little pebble, and then we, as the engineer in the car, or just passenger, whatever, can just say, oh, it's safe. I don't really see anything. Just go ahead, right? So in this case, if we can do this, have this kind of interaction with the user, and then the system should be able to learn on the fly. So in this case, of course, you have to create a new task to learn this little pebble, right? To say, okay, I have to learn to recognize this pebble, and then in the future, I'll have no problem. And also tell the system, next time you see this guy, you just drive without any issue. Okay, so this is basically, can we learn continuously? And also, this is basically learning on the fly, instead of we just drive the car back to the app, and also take a long time to figure out what's going on. Okay, can we do something like that automatically? So this basically means we have this orange lines. So the system has to basically has to detect the new tasks, and at the same time try to figure out, what is the ground truth training data. So it's basically have to acquire the ground truth training data, and then the system can do continual learning. So in this case, then we basically close the loop. Okay, and then in the application, the system can learn and create the task and get the ground truth data, and then get system to learn sort of gradually or continually. Okay, so this is basically involves some additional things. Everybody is familiar with this continual learning. We have the incremental learning process and knowledge accumulation, transfer adaptation. However, when we come to this post deployment, and the system has to do sort of self-motivated kind of learning and self-initiated kind of learning, and through interaction with the environment, with the user, with humans, or probably with other systems when we have multiple agents. And so this basically, as we see in the picture, involves identifying new tasks to learn and acquire ground truth training data, and the learning sort of incrementally. And this is basically what we're doing mostly in continual learning, just the last step. We got the task, we got the data, and then we do continual learning, sort of incremental learning. So let's just have this example, which is a greeting bot in a hotel. So for example, we have robots, which is greeting guests in the hotel, and they're just roaming around in the hotel lobby. And when I see an existing guest, just go have a small talk. So for example, John, how are you today? What's the weather today? How are you? Do you like whatever things you can say? So when this robot sees a new guest, it has to recognize this person is new, and basically I've never seen this person before. So this is essentially out of distribution detection or novelty detection, which at the same time create a new task for the system to learn. So then the bot can say, welcome to our hotel, what's your name, sir? And then this is basically an interaction with the person and trying to get some sort of information. For example, in this case, it's trying to get the class label. For example, this guest replies as, my name is David. And then of course, got the class label is David. And the bot, of course, in this case, if you want to do recognition, and you just take some pictures of this David, and then next step, basically incrementally learn to recognize David. So in this case, we can see this is basically the class incremental learning. So if we want to sort of forget about the person, previous person, somebody who is left, and then you can also try to forget that person as well. So when this robot sees David next time, and they can say, oh, how are you, David? And then you basically treat this person as a friend or something like that, and something you recognize. So you can see this process that we can do sort of autonomously. And you don't really have to get a human engineers to add new people and all this kind of stuff. This system can learn by itself, and without any intervention from the humans. However, this is just the ideal kind of situation, but in the real world hotel, the situation is much more complex. So the first question, of course, how does the bot knows this normal object is a new guest? It could be a piece of furniture, it could be a person, it could be an animal, it could be anything, right? So that requires sort of for the system to characterize this normal object. So what kind of object it is this, okay? And then with that, the system can kind of respond. So you have a different characterization, then you can respond. So in this case, when we do this post deployment continual learning, we are doing something which is not just learning itself, but we're also doing something else. Of course, there's something else. Let's say in this case, we're talking about the characterization and the adaptation. They're both related learning as well. So in this case, we can probably, in terms of characterization, say, oh, it looks like an animal, okay? Because basically, we probably have a model behind it, which is to try to detect something which is look like certain things, look like something. And then they probably, in this case, just report to the hotel staff and say, oh, there's an animal running around, probably. And it could be, looks like a policeman, may not be a policeman, but it looks like probably do nothing. And then if it looks like a hotel guest, and I've never seen this person before, this person probably have got luggage, or probably queue up in front of the registration desk. And then you probably say, oh, welcome to our hotel, and also Lemsa. And then of course, and the previous slides, which shows that interaction process at the same time, learn to recognize this person. So the process is quite complicated. So in this case, we do need adaptation, basically to accommodate this new thing in order to learn this new person in this situation. So what do we mean by characterization? It's basically try to describe this object, and then you can respond to this object. So for example, this is basically looks like certain things. For example, this looks like an animal. Then you can sort of respond like you sort of see a real animal. And so in this case, of course, if you see the animal, then you basically say you report to the hotel staff. And then you probably also want to ask this hotel staff, what's this animal, right? And then you basically, then you recognize this animal. And next time when this same animal comes in, then you can tell the hotel staff, oh, this particular animal, so for example, the dog, which shows up in front of somewhere, and then can you go to basically chase them away or something like that. And another thing sometimes we need to do is the attribute, basically try to recognize the attributes of the properties. For example, when we talk about self-driving cars, and probably in front, we don't really know what it is. And when at least we probably can figure out, is this a mobile object or is it a still object? So if it's a moving object, then you can say, okay, what is the speed or what's the direction of moving? And then in this case, with this, you can decide what will be the adaptation strategy. For example, you probably want to say, if this is the moving object, then you just wait for a while and drive slowly and wait for this thing to move away from the road. If it's a still object, you probably have to go around. Okay, so at the same time, you learn to recognize this object, and next time you will not be so surprised. So this is basically when we have the characterization. Now we have to adapt to the novelty. And of course, in the adaptation, we are also learning. Okay, so for example, I recognize this the hotel guest. It's just somebody I have never seen it before. And then essentially I can take pictures and then basically perform the continual learning to learn to recognize this new guest. And sometimes we have to deal with the sort of risk assessment, because if you look at this thing we're doing, everything's uncertain. There's the characterization, and then the adaptation is all uncertain because we don't really know what this object is. We just say this is similar to something, but what happens if it's similar to a tiger? That's going to be terribly dangerous, right? So you have to be very careful in terms of decision making. This uncertainty decision making. So this is the project which is basically going on in the DARPA. It's basically an open world learning project, and not a lot of progress being made, but this seems to be very important, and which essentially we're trying to achieve autonomous learning, all sorts of AI autonomy, so completely autonomous. How can we do that? Autonomous sort of machine learning or continual learning. So with this was basically that background that we can see this picture gets a lot more complicated. So then we have this orange lines, and again we have after we got the model, essentially when we in the application we detect something, and then we basically tells the model, and the model basically produce something, and then say, is this relevant or not? This guy is relevant or not? If it's, for example, this guy is on the, for example, in the self-driving car, and detect something in the shop, and on the roadside, something happening, so you probably don't have to worry about. And then you do characterization, and then you, at the same time, you do a risk assessment because you need to make decisions, and also adapt, which is basically the plan of what we should do next. And the first thing, of course, we have the performance task. For example, just now the case we are talking about greeting the guest in the hotel. So in that case, we have to say something, and then probably also have to do something else. For example, learning in our case. And then all this thing, create a new task. We can just create a new task and also create the ground truth training data, because we can take a picture of that thing, and then we can sort of do sort of continue learning. So this process, again, we're talking about the closed loop. Okay, everything becomes autonomous. Okay, autonomous. So this obviously is very difficult because it's not just involves learning and the characterization. Characterization is somewhat related to learning because you essentially you need the learning or need some different kind of models to detect whether this moving object is not a moving object, whether it looks like an animal, it looks like a dog, all this kind of stuff we need to do. But adaptation is more related to planning, which is essentially also related to learning in the sense we need to sort of get the ground truth data. Okay, ground truth data. How do we do that? Okay, we need to set up interactions. So I'll just try to give an example. And unfortunately, this example is a natural language processing example because we don't really have a real situation which could do this robots kind of really have robots in the hotel. So this is an example. Although I'm talking about this as a sort of research prototype, but this has been implemented in the real chatbot and has been tested. But there are some interesting issues that I'll mention a little bit. Okay, a little bit. So this is a natural language sort of interface, and just like Siri and Alexa. And you issue a command, you say, oh, what's the weather today? And then the Siri or Alexa will tell you, what's the weather today. And then basically, this involves an API. You issue a command, and then the system translates your command and then basically calls the API action, calls the API action and perform this function. So this system is basically based on this natural language matching. Okay, and this system is called CML. So the basic idea is fairly simple. How do you do this? Essentially, for different commands, you want to say, for example, I want to get the weather, and then you basically store some commands, manually write some commands, store it, which is what we call the seed command. So the application developer can do that. Okay, and then when the user says something, then you basically do the matching. You can do the matching with what you saved. And of course, inside what you save, you have some arguments. So you have those parameters. Those parameters will be given to the API sort of action to perform whatever action which is you requested. So I see essentially is a paraphrase, different kind of command the user might use. Okay, but of course you cannot really basically prepare all kind of ways people might say it. So what happens if people say something you don't understand, and how can you learn gradually and continually and basically get the system become sort of smarter and smarter? Yeah. Essentially the idea. For example, we have the example, we say, this is the API action, basically switch on the lights. Let's say this is the API for a home appliance sort of application. Switch on the lights, its location, and then what does this command look like? The switch on the lights, and then in the X1, this is basically X1 basically represent location. They can say put on the lights, so that you can have different ways. This is switch off the lights, and then change the lights, change the light color, all those things. So let's say I see this put on the lights for this particular API, essentially is a switch on the lights. And then user command say the power on the lights in the bedroom. Okay, and then the matching algorithm just basically try to figure out what does this mean, match to which one. So in this case, of course, we have to do natural language processing, all those kind of things to get these two things to match. And says X1 basically means the bedroom. Now you can call the API action the switch on lights. X1 in this case will be the bedroom. Get the bedroom, and then the system has a few sort of components is this a kind of, is the one of the specification of this thing and the command grounding module, and also have active continual learner. This is essentially try to learn new SCs. So when you have, when system has something to stand, and how do you sort of ask the system, ask the user, and then to get the ground truth and to learn this. So how does this sort of performing those sort of actions or those sort of different steps in the post deployment? So this is definitely the post deployment, because it's learning occurs during conversation, during sort of this is being used. Okay. So the step, first one we just mentioned, right? You have to detect what is new, okay? Something you don't know. So in this case, we call it novelty detection. Okay, also called as OOD detection. So for example, the user give a command says, turn off the lights in the kitchen. So just now we can see we have to switch off the lights, we have to put on the lights, we don't really have to turn off the lights. So in this case, of course, the system probably doesn't understand this thing. So this is new, okay, this is new. So how do you characterize this? So what exactly this thing is, you want to describe, and then how do you respond to this? If you do not have a way to describe it, then you don't know what to respond to this thing, okay? So in this case, the characterization basically will try to figure out, oh, this part I understand. So the turn off, it seems to be the something which is I'm not quite sure. I'm not quite sure. So then we can figure out what are those sort of commands which might be similar to this. So in that case, we can just say, I'll give the user a few options and say, sorry, I didn't get what you mean. And do you mean this? Do you mean turn off the lights, switch off the lights, or switch on the lights, or change the color of the lights? So of course, in this case, user, for example, the user choose the first one, switch off the lights. Then you can see the system got the ground truth, and of course get the task to learn this particular sort of command, and that regards as a task. And then we also get the ground truth data. That means switch off the lights in the kitchen. And then of course this system can learn this particular thing and put this into the SC. So you can see this is the continual learning. Of course, in this case, we're not talking about the type of continual learning we're familiar with in the machine learning or in the CVPR. But if you have a new SCs, next time when somebody says something like this, then you have no problem. Okay, no problem. Right? And so what is the risk? Okay, what's the risk management? Okay, so in this case, the number of risks. The first one, of course, you don't want to talk to the user too much because you get the user annoyed. Of course, some people have more tolerance, some people have less. So in the process, you can learn as well. You can learn that as well. So for example, you talk to this guy never responded, then you probably next time don't answer this guy anymore. So but some other people might be more sort of willing to interact with you, and then you probably can talk a little bit more. So and then you can learn sort of in the process. Another thing is when you do this or you detect this unexpected thing, and you want to characterize, but you probably have no idea how to characterize this thing. So in this case, you don't want to give a user a list of possible actions. So and that which is going to be completely random. The user is going to be very annoyed. I know you probably will think this system is a complete nonsense, knows nothing. Okay, so in this case, you probably want to say have a default action, which is not going to be very annoying. Just say, in this particular application, you can just say, can you tell me, can you basically say the same thing another way? So instead of giving you a list of things for you to stack, so just tell me another way. So if the guy says, you switch off the lights, okay, then you got turn off the lights and switch off the lights probably means the same thing. Okay, means the same thing. Okay, so again, you can learn, you get the ground truth, you can learn this new command, okay, this new command. And so this was basically implemented, not completely, and that's a small implementation, which is has some restriction on certain things, and was implemented in a real system, and it was deployed to about 10,000 sort of people. Okay, 10,000 people. There's some interesting things which are happening. So the system does learn quite a bit of stuff, but there's also some other problems shows up. So for example, I just give you two examples. One example is for example, the user says something, but the system does not understand. And then the system asks them, do you mean this? The guy basically forget about this and they talk about something else. Okay, talk about something completely, talk about something else. Okay, and the issue next one, for example, I want to listen to a song. And then they say, oh, do you mean this song? the guy say something else, say another song. So this is not good. So this is the one that's things which happens quite frequently. Another one is the user basically forget about it, and then you talk to somebody else, talk to a people. Yeah, because you can't be sure the environment does not have anybody else. It could be somebody else. And instead of talking to this system, now it could be just basically switch off this thing, but not switch off the same, but at the same time talking to another guy. So sometimes you got all this interesting problem. Of course, this has to be solved. Okay. So let me have a summary. So the summary and basically says, and we want to achieve this continual learning in terms of AI autonomy. So post deployment, can we learn as well? Can we make the system self-initiated? Okay, you can have self-initiation, self-motivation, and then based on what you have seen, which is a novel, because anything novel is going to be a motivation for us to learn. Okay, so this is essentially what we call the open world. You have the detection, you also have to characterize it, and you have the adaptation, and you have to learn. Okay, you have to learn continually to recognize this thing. So we need to, in order to learn, we need to discover new tasks, obtain ground truth data, and incremental doing. We can see in this case, the system get its own task, its own data. So it's not like what we're doing now. And we basically assume data is there and also the task is there, right? And now we just basically try to figure out our algorithm to get better algorithm. So this technique is still sort of in infancy sort of stage, and it's being researched as some big projects going on to try to do this. And the problem is very challenging, but some kind of application I think is possible in limited sort of in a restricted kind of domains. Okay. I think that's it, and thank you very much, and I'm happy to answer some questions. There's some students and collaborators and fundings. All right, that's it.
Thank you so much.
I have a question, right?
Yeah. So for people, if you want to ask.
Yeah. So the question says, should humans still have to be in the framework to label the data for post judgment? And so in this case, of course, if you think whether a human is labeling data, yes, it is, but this is very natural. For example, I ask this person, right, what's your name, sir? Essentially, I basically got your label, and then I know you are actually helping me to label, right? I take the picture of this person, and then I learn to recognize this thing. And then just now we have this dialogue kind of situation, and then we ask back, right? And the user will give us something, and that is going to be the ground truth data. So if you think about that, that's also kind of label. But this is different from you get a company get 10,000 people. I mean, from the villages to label the pictures and label the natural language. Because I work with some, at least in this dialogue kind of environment, and which is it's very difficult to label, because in this case, label does not mean it's not the same thing as the sort of picture sort of label. Let's say this is the car, this is that kind of thing. But this is, you have to write it. You have to write different kind of different variation of the sentences and the responses to all this thing, and then system learn from that. So this is quite costly. It's quite costly, and if we can do this sort of automatically, that'll be very interesting. Yeah.
Cool. So if there are any more questions in the room, you can go into the microphone here, so that the Zoom people can also hear it. If you're in the Zoom, you can just put on your microphone or put it in the chat.
Chat question. Or if it's applied to other specific domain. I think it's kind of the same situation, and we apply this to the natural language. The reason is you have something fairly restricted. If we go back to see there's some kind of process, and you can see it's quite complicated. And just now I talked about this greeting bots. And the first thing you have to know whether this saying, if you see something, is this relevant or not? If you, for example, you see a piece of wood or something, furniture put in the middle of the road, in the middle of the sort of hotel lobby, you don't go there to say, how are you today, right? So you have to characterize, this is relevant or not relevant. You have to characterize this thing. And then this is going to be a difficulty, right? It's not just to recognize faces, you just also have to recognize many other things, right? And then you have, so that means that you have to characterize it. And you can see this whole process is completely uncertain, is right? Uncertain, so you have to have the risk assessment, all those things. And but I think many of those things is doable. For example, even in the hotel lobby, it's possible to recognize whether, we can't recognize every individual object, but we can recognize some type of object, right? For example, is this animal or not, right? It is possible to classify for that, right? That's going to characterize it. And this, if you don't really know this is an animal or not, but you probably can see there's something else. Even if you don't really know the specific animal, but at least you notice the animal. That's probably good enough in many cases. But of course, you can't have extreme cases. Oh yeah, the tiger comes in. I mean, you can't handle that. You probably cannot handle. But in normal cases, I think characterization is still doable. Even the self-driving car, right? Characterization is doable, but you can detect something in front, is it moving or not moving, right? And then if it's not moving, and then you basically, go around. For example, you still have a passenger in your car, right? It's not just completely alone. And then you probably can ask the passenger what to do, right? And so that, I think it's doable in many cases. It's not just in this particular domain, but in other domain, it's just a little bit more complicated, I think, especially when you talk about the self-driving car. But I'm not advising you do this in self-driving car, real self-driving car, because this is dangerous, really dangerous, unless some kind of fairly safe situations.
All right.
I mean, I show you that just now, the motivation, right? That was one of the motivation. We do have that situation. I do have that experience. Even in that case, when the car stops, I tell this car, just go ahead, right? This whatever thing you see is not dangerous. It's very safe. Then you can learn that, right? You can learn that. The next time you don't really have a problem anymore. Is there a general recipe of novelty detection, or is there always about models uncertainty in practice? So this is tricky because even for human beings, we don't really absolutely know this is novel, right? For example, in the rabbit, even you recognize the rabbit, you know the rabbit, that's what the rabbit look like. But something moving in front, is it rabbit or not rabbit? You probably not absolutely sure. Okay, absolutely sure. And so there's lots of research going on, and for example, in CVPR, people call it open set classification, right? Open set recognition, and then in machine learning, people more call it OOD detection, also the open classification. And in this particular project, in this DARPA project, is called novelty detection. But they're all about the same thing. Okay, yeah. So there are lots of uncertainty. That's why the risk sort of assessment is.
So I also had a question about how you use like the user feedback. So I think it was an amazing example, like with the self-driving car that encounters this pebble, and that it would be ideal if the system could just adapt to that. Like in computer vision, we tend to focus on the classification problems with just labeled data supervised available. Do you think this is like a direction we should consider, is how to collect this feedback from the user and how we can incorporate it?
I think we need to do this sooner or later. And for example, in this particular case, it's a point cloud detected by a sensor, and it's clearly that guy is being detected. Okay, it's not just detect on that particular instance because that thing has been there, right? The car is moving. So it's not a still, it's not sort of, you only see one image of that object. Not imaging, in this case, it's a point cloud. It's a point cloud. So the guy are really seeing that thing from distance, right? And they identify that guy, but just don't know what to do about it, right? Just stop it, stop the car. And then we look around everywhere, I have no idea what's going on. But in this case, so you see here we have this interaction module, right? So you need to interact. It's just like human beings. You don't know anything. I mean, how do you know it, right? You have to ask somebody. You learn from the book or whatever things or maybe you're going to try. You're going to touch the thing and then see what happens. Right? That kind of reinforcement learning, something like that. But you have to interact, right? And I believe this will be a interesting direction to go.
Yeah, I think so too. Thank you for your response. So thank you again for the amazing presentation. So let's give him another applause. We will now be transitioning to the panel discussion. So maybe the panelists can join in the front. We'll just be setting it up shortly. So we'll be there in a few minutes. Thanks. Should I just say here? Yeah.
Seems a bit laggy in the
How do I finish?
No, he's a bit laggy, but
I think it's fine.
But there was also the other like spotlight for everyone. Maybe because it's in the Wi-Fi, right? So the quality is not. Yeah, spotlight for everyone. Yeah, absolutely.
Okay.
That helps. Yeah. Yep. Great.
That's perfect. Yeah.
So we can see everyone. Yep.
Yeah.
Hello? No? Is someone else?
All right, so we can get started with the panel discussion. First of all, thank you to all the panelists for joining and for the amazing presentations. Okay, so yeah, we have quite some time for a panel. So we tend to discuss the future of continual learning, also where we are now. Like in the beginning, we'll have like 35 minutes where we have some questions that we got from the community and some general questions to like where you guys in continual learning. Then in the later part, we also accept any questions from the audience. So any questions you might have, write them down, and then we have this amazing board here of experts in the fields that can come back to you. So to get started, really, I think we can do like a round of everyone shortly introducing themselves. Also maybe like how we got inspired to actually do continual learning.
It's not very clear from the Zoom. I can't really hear well.
Okay. Yeah, let's see.
That's better.
Yeah, this one's better. Yeah, that's gonna be hard.
All right.
Hello, can you hear me now?
Maybe can you go to the Zoom link there and speak instead of sitting there? Sorry.
Yeah, but we have a microphone here for the panel. So let's see. Let us see if we can switch them maybe. I guess. Yeah, it's not gonna be.
Just move all the chairs.
That's also an idea.
Yeah, maybe that's a bit easier. Don't have to worry about that.
That's one. Yeah, I think we'll go.
No, it's working, but people remotely.
People what?
On Zoom, they cannot hear well. I guess it's not connected to, but it's just hearing from the microphone that the laptop is capturing. But it's okay. I mean,
Yeah, it's fine. All right. Thank you for the help.
Yeah,
All right.
turn off the volume.
Yep.
Okay. Can you hear us now from home? Should be better.
It's better now.
Okay, great. Okay, so my name is Vincenzo Monaco. I'm assistant professor at the University of Pisa, and I really got interested in continual learning when I started my master's degree at the University of Bologna. And at the time, I think it was around 2015, I was trying to move from state-of-the-art CNN, so fully connected the fact to feedforward models and try to add time, the notion of time in some ways. And so at the time, maybe it was more related to sequential learning, you know, and exploiting the structure of data and time. But then I quickly realized that maybe a better way to leverage time is acknowledging the fact that you get data all the time, new piece of evidence, observations, and then I developed a strong passion towards lifelong, incremental, continual learning methods, deep learning that at the time was kind of exploding. So that was my trigger, and then I continued, let's say, working on the topic in my dissertation and up to now.
Hi all, I'm John Schwartz. I'm a research scientist at DeepMind and the University College London. My sort of first exposure to continual learning was about great consolidation. So the university has developed certain liking for models, but was quite interested in transfer learning, and colleagues had just basically published EWC at DeepMind, and I sort of liked the kind of Bayesian interpretation, which obviously was clear was quite an easy way of doing it, and so that was and I've been working with it ever since, and so the JSON skills and etc.
Hi everybody, I'm Tyler Hayes. I recently defended my PhD at the Rochester Institute of Technology. Quite similar to Jonathan, I came from a math background, so my master's degree were in applied math, and I picked up the EWC paper and I was very excited about the mathematical connections with machine learning and continual learning there. So, I mean, I think it's a really important problem to work on. It seems like there's a lot of space to grow. I was very excited when I started looking at the literature and realizing that there were a lot of interesting related domains, you know, like meta learning, online learning, domain adaptation, all of these things that could be combined into one field. So that kind of drew me into the field at first.
Hi everybody, I'm Joost from CLVision Center in Barcelona. I started working on this also around the same time, I think. With this EWC paper I started it all. And I was working already in transfer learning, mainly for generative models at this time. And so we came in from that direction and did continual learning for generative models. And since then, I've continued working on it, and especially interested also in example of free methods and also in some application, like semantic segmentation.
Okay, so thank you for this great introduction. It's great to have you all here. So let's get to the main stuff and the news of this panel discussion right away. So there have been a lot of advances in like these big pre-trained models, which raises a bit of the question, like
you have these big pre-trained models that are like generalized so well on such a wide range of tasks, where does that leave continual learning? Like, is there at some point that we have, you know, these models generalize over all tasks that are there? Where are we in continual learning? What is your thinking?
Well, my thought is that really, I mean, if we speak about sort of big general models recently, it's mainly language, right? And I think that continual learning can play a big part in training these methods and actually making it work better. Language is quite interesting. It's quite a natural sequential domain. You have language evolving on multiple timescales. Even in English, certain words are more frequent in the past than they are now. The things that people speak about changes a lot. I think GPT-2 doesn't know anything about COVID, so clearly they need to learn and adapt. For transformers, the context length was always a big kind of worry, and I think because we thought so hard about memory, continual learning, what to keep in memory and how to consolidate things, perhaps that can help us with the context problem. Also, we shouldn't forget, you know, you might all speak English, but a lot of people in the world don't, and a lot of data and big models is a recipe that works for English and French and Mandarin. It doesn't work perhaps for Afrikaans or Vietnamese or some of these other languages. So there is plenty of room for low data settings across language.
Yeah, I think that's a great response. In addition to that, I think, you know, if we have these large pre-trained models, there's not a possibility that they will know everything in the world, and maybe using that to our advantage to make more sample efficient models, right? So maybe I have a more fine-grained task that I'd like to do in a continual learning setting, and I only need a few samples because I've had such a large pre-training set. Maybe that's something that I would be interested in targeting in the future.
I think that it's true that you think, okay, adapting it to one task. The danger is that you don't need any forward transfer anymore. I think you can just adapt to your new task, and the next task you go again back to your big model you have. And I also think I see some publications coming out now with this model. I think we should really measure this forward and backward transfer because it's a key aspect of continual learning. And else it's just sort of a retrieval of knowledge from this big model, which is still interesting. And maybe it's more a continual classifier learning than a continual representation learning. So I think that's maybe the danger, that just doing extracting the knowledge from this model is enough, and you don't need to really update the representation below it. But okay, of course, the world keeps on changing, and also these big models need to continue to learn.
Okay, so if I can like recap that and maybe
They're still not hearing. Yeah.
let's check into Zoom.
Yeah, they are not hearing. I think they're still hearing from the mic.
From the. You can try it. I'll continue. Maybe you can try the settings.
Yeah, whenever you guys talk now, it's perfectly understandable. But at the panel, it's not. So if the microphone that's used there where the speakers are can just be moved a bit closer, or alternatively, you can just use someone's laptop and set it in front of the panel. I think that could work better than it is now.
All right, thanks for the feedback.
Yeah, we can try that.
I don't know, maybe I can move the.
Or can you move the sound settings to your HDMI? Or
I don't know.
No?
I don't know, because it doesn't see the other microphone. You see, like here, if I go to sound setting, I don't see
the headphones.
No, this is the output device. This is the input device.
We have the no. Can we use okay.
Okay, so maybe we can just move the chart over there. Yep. The easy solution. Sorry for you.
So let's just sit here.
Yeah. So where we left off, I was recapping a bit on your responses on these pre-trained models. So that's something that we don't need to learn features in a continual fashion. Should we only look at the task heads, or what is the value of then continually learning these features? Maybe Jonathan?
Yeah. I mean, every time I've looked at continuous learning problems, and I looked at having a part of my model frozen and adapting only some part of it, that seems to work fine in kind of small data settings. People sometimes do that in order to be Bayesian, because you can just consider the backbone to be frozen and you can do Bayesian regression. But if I then move on to a method that could avoid forgetting, so that whole model that always goes back to that. So I think no.
I missed the question.
Okay. Okay. So, like, what is the value of learning features continually?
Based the answer of previous question, right? So, I mean, I always thought that, especially deep learning, the main objective of team learning is to learn robust representation from ID data, from session data. I still think that's the case, despite the availability of these deep models, because the world is quite large, we have a lot of things to do, and especially when we want to deploy these systems, right, for all applications, it's possible that we won't have just a single big model in the entire universe at the end, right? So you always need to change the representations, and we can do that so that humans have fixed after a few years, and we should leverage that flexibility. I think that's important. So there will be always, I think a space to learn robust representations, and that's quite difficult to do, I think, at the moment. So I've shown that, maybe for some tasks, you can just learn a few weights on top of a frozen backbone or something like that. This is already quite robust in general for the task, but then if you want to challenge more complex problems, I think being a bit more flexible, also learning representation will be helpful.
Yeah, I guess I have 2 points for this. So the first point being that adapting to the changing world around us, right? Being able to adapt those representations that maybe they're similar enough to be useful for learning new things more efficiently, but maybe we'd like them to be a little bit more fine-grained in order to adapt specifically to different types of tasks that would be seen in the future, but maybe not necessarily seen in the past. Was there a second part to this question?
Yeah. Like how you can use the feature, and like the task heads, should we mainly focus on these task heads, or should we only focus like learning features? Or?
Yeah, so the idea of task heads versus features. I mean, I think this is kind of interesting, right? I guess I'm a big proponent for not using task labels for problems like classification, but I think in some sense, task labels could make sense. You're using multiple heads, but the problem domains actually differ. Right, so if I'm doing visual question answering, the output is an answer. If I'm doing object detection, the output is a classification with a bounding box. So physical output space changes. So in that sense, I think, it makes sense to have the different task heads, but maybe some shared representations could still be helpful, right? In this example I just gave, right, maybe I'm asking questions about a dog, And maybe I also want to be able to do object detection with the dog. So maybe they use a similar set of features, but when I actually come down to making the output prediction, I need the different heads in order to be able to do that. But I still think there's some merit in sharing feature representations, whether it's all of them or just parts of them, you know, things like this. It could still be an interesting idea to think about.
I agree. It's also a much harder problem. I like it much more. Let's say it feels always as a cheat if you don't do this part. But, and I think also it's really practical. My first client was actually an autonomous driving company who put new cameras on the cars, so the quality of the images went up. And they did so. This was the continual learning, and then you really need to learn your basic features. So I think it also in many real applications it is a real problem. We should still focus on that.
Thanks. There are a lot of agreements on still learning features continually. So of course, to learn these features, we need data and research also the benchmarks to represent the applications that you're interested in. What do you think are like important steps, or where are we now also in the benchmarks that exist at this point, and what are like future steps we should consider there? Maybe Vincenzo, that you have some thoughts on that.
Sure. So we proposed a few years back a benchmark or 50. That is first attempt. Let's say if you have something more specific for continual learning than I heard from the other workshop, the other world innovation workshop that was yesterday, that is to see clear benchmark specifically designed for continual learning. And I think that the community is large now enough and we provide more and more data and benchmarks to work on fascinating problems in continual learning. There are also studies that more commonly used benchmarks created from other CLVision or other assets. But I think at the moment, and this is what we're focusing on, for example, it's very, very important to have to work more on infrastructure, not just the data, the infrastructure for evaluation, training, more in software tools. And all the necessary pieces to make it more accessible to anyone and provide a basic building blocks to work more easily. So that's I think at this stage we feel even more important than having more data. Because my feeling is that people still want to discover in terms of ideas and understanding scenarios, proposals, and evaluation settings. So being able to at least have a common platform to discuss and work on this will be much more needed than just pure data.
Yeah, so I have a lot of thoughts regarding benchmarks, specifically regarding data and metrics. But I guess in terms of data sets, I do think it's important that we're making sure that our systems scale up. A lot of times this means testing on data sets that have a lot of categories, a lot of different examples, maybe a lot of varied examples, right, that don't look so homogeneous from a particular category. So making sure that we cover the gamut of possible examples, for example, right, like different cat breeds or different dog breeds. Instead of just focusing on one or two of those. So the first thing I think is scaling. I also think that a lot of work until now we focused on like balanced classification problems, but I do think imbalance is really important. The natural world around us is highly imbalanced. It's not likely that the agents are going to see these balanced streams. So I do think in the coming years it's going to be important to focus on targeting those imbalanced streams that more closely resemble the natural world, right? In terms of metrics, I also think that there's some interesting questions that can be asked, right? So for class incremental learning, maybe in a classification or an object detection setting. The goal is basically that the agent never forgets any class it's ever seen in the past, right? And I mean, I think it makes it easier to metric and to benchmark what we're actually doing. But if I think about my own life, there are certainly a lot of things that I've forgotten about, and maybe that wasn't detrimental to me conducting the rest of my life. And so I think it could be interesting to start considering some more interesting paradigms in terms of what that actually means or what that should look like when we're benchmarking and evaluating our systems. I had another thought, but I lost it, so I'll pass the mic.
So let me start. I still like experiments with cipher, and then there's also a lot of, I think in continual learning you can still do a lot of these things actually. I do think about this unsupervised domain adaptation, let's say maybe with trying to not forget your previous tasks, so sort of continual unsupervised learning, maybe with labels on the first domain. I think that's a very interesting setting, and which actually is applicable, which does give really good results also if you apply. You need to apply some continual learning techniques. So I think some sort of maybe more benchmarks in this direction would be very interesting. I saw the workshop yesterday. This clear data set looks really interesting. In their setting, you are allowed to remember everything. So I'm not really sure if that's continual learning. For me, it felt a little bit difficult to accept that. But I think the data set is very interesting. It has data of objects over years. So you have a computer in 2010, computer in 2011. Etc. So I think that's a very interesting setting to do sort of domain shift and continue learning.
Okay, so on the benchmarks, that's a topic that will also be interesting maybe is the level of supervision that we have available in these benchmarks. So right now we have a lot of supervised classification benchmarks. What is your opinion on that?
So a thing that came up a couple of times today is this post-deployment continual learning idea. That is, you have the algorithm running on someone's phone, and it's sort of not clear when to learn, what to learn, you might not have labels. I think that's quite an interesting domain. I don't think we have really paid enough attention to that. So I think that would be something to emphasize more.
I think that the field is naturally shifting way to more lower supervision, benchmarks, data, scenarios. A natural way of doing the learning is less supervision as possible. That's clear, right? No one's going to have a continual labeling human, process thing. So I think that a lot of data is there to play with, so I think we leverage advances in methodologies in self-supervised learning, supervised learning, and move naturally towards that. So I don't see any strong impediment. I just think that continual learning was born for, I guess, for simplicity within supervised learning, and I can say also the vision. That's because it was one of the most let's say, advanced fields in deep learning, let's say, at the time, especially. So I think that there's no strong barrier actually to it. And we see more and more works and methodologies and approaches for self-supervised learning. I really like also the idea of interactions. It poses some questions, right? Because if you want a real agent that needs to interact with the world, then the only way to actually do this is on simulation, or with the various instead in having a real environment in which you can let the agents actually ask their questions, interact, right? So that may be a more challenge, but still focusing on just stream of data, so without actions, forms, specifically. As we know, learning, that can be done easy, such live streams of data.
Yeah, and I also have a couple of thoughts, but I I just want to hint on that idea because I do think it is very important, this aspect of engaging with the environment to get feedback. The natural world provides a lot of unsupervised data, right? If I throw a camera on board a robot or something, it's going to collect a lot of unsupervised data. So that interaction with a human to ask for those pieces of data or labels for those pieces of data that might be most critical to improving the performance of the model could be really important, right? So maybe something like active learning to query a user to give actual labels when it's the most important, but then doing some type of unsupervised feature update on those unsupervised examples could kind of provide the best of both worlds, right? In regards to benchmarks for unsupervised or self-supervised learning, which I think we've heard a lot about today, I think in addition to just measuring performance in terms of accuracy, it's also interesting to think of these questions that a lot of people have brought up today about how do we actually measure how robust the feature representations themselves are, right? What does it mean to have a robust feature representation that could be used for many downstream tasks, right? What would some of those metrics look like? We can measure something like representational similarity or something about the feature space, right? Or the penultimate layer, something like this. But I think it could be interesting to start considering some of those additional metrics to kind of probe exactly what's going on. In terms of my opinions on supervised classification, I think that there's a lot of work in this field, but I think a lot of it could start being generalized to other fields. I think there's some really nice work. There's some people here today that have worked on like object detection, semantic segmentation. I think it's really interesting to start thinking about those problems which introduce additional considerations, right? Like the background shift problem where in object detection, in one moment the class is treated as a background, but then all of a sudden now it's treated as a class and there's this huge shift that the model has to overcome. So I think we've made a lot of progress in classification and that's great. And maybe it's time to start adapting that to other fields and to consider what those benchmarks should actually look like for those as well.
Yeah, I think in principle it's a sort of a fake problem, maybe continual learning. And the first time I started continual learning project, we had an out of distribution detector. Then we have a continual learning algorithm. Then we have an active learning algorithm to ask for the out of distribution data to be. And it was a terrible experience for me as a scientist because I couldn't conclude anything. Yes, it's unrealistic, but we need to break up things in small problems which we can evaluate and compare progress in. And the most realistic system will be the hardest to evaluate.
So like the benchmarks seem to be like these smaller problems that we try to tackle. But of course, it's maybe like the bigger goal or the vision in continual learning. Like, what would be like your ideal continual learning or application that we can use in the real world for continual learning? Maybe
Sure. So, I mean, I think in terms of my opinion, an ideal continual learner, maybe, I guess it's very application specific, even what an ideal learner means and what it looks like, right? If I'm doing on-device learning, I do think it's very important to be able to process the samples one at a time as they become available, potentially identifying unknown samples, querying for labels, and then updating, when it's appropriate. But perhaps there's other continual learning settings. I mean, if you're a large company, you have a lot of processing and compute power available to you, maybe batch continual learning is an okay thing to do, right? So I think it's very application specific, but in terms of an idealized system, I think ideally it would be able to learn from any data ordering in which it's provided, right? Maybe it's learning from temporally correlated videos, maybe it's doing class incremental learning, but I don't think that's super realistic, but I mean, just being able to handle these different scenarios, not necessarily being bespoke to a particular scenario. Learning from high resolution data, I think another important thing that we need to start considering is like multimodal data streams, right? We as humans use a lot more than just our visual system. We have 5 different senses. Often when we deploy robotics, they have different sensors on board, right? Maybe they have a camera, maybe they have something capturing audio, maybe a depth sensor, things like this. So I think ideally it would be really nice to be able to make use of those different data modalities and understand what's happening around the system from those different modalities.
ideal continual
The
learning.
ideal continual learning.
Yeah.
Yeah, I think, I don't know, yeah, I think we're doing pretty well, yeah. I have the feeling this question comes a little bit, if you're convinced about the privacy of data, then we are doing pretty well. I've always the feeling that maybe you secretly think, okay, I can save all the data and then I can train from scratch. And actually, maybe continual learning, for me, the most important lesson is how important IID training is. No? That is, so continual learning is about non-IID training, and that comes at a high price. And that's why this joint training objective is often very high still. But if you're convinced about data privacy and your application needs it, then yeah, you cannot get there. But you continue learning as we do it is slowly getting in that direction. We're not doing so bad.
To me, the question relates a bit to the benchmarks. I think the field has had an issue for a couple of years now that we, instead of looking at natural scenarios for continual learning occurs, we've sort of written papers describing what we think we want. So I'm thinking about, there's plenty of papers out there who are trying to make the case that really backward transfer or forward transfer, that community emphasis isn't good and we should do split emphasis instead. I think there's a couple of scenarios in machine learning where continual learning naturally occurs. I'm thinking about GANs at the moment. They may be a little bit out of fashion, but it was a good example where part of the reason you got node collapse is that generators and discriminators essentially sort of forgot, or generators forgot to generate certain examples. In populations of agents, you get certain interesting behaviors, that skills that have been quite useful at some point in training sort of get ruled out by the way the evolution works. And so later on, an agent that is essentially superior is actually can be adversarially challenged with one of those inferior skills that have been discarded from the population, and so goes sort of getting abused. I made the case for language earlier. I think recommender systems are a good example. There's plenty of continual learning problems on the world, and we don't have to define them. And often the metric is very clear as well, to as good as you can with the next example. And maybe that requires protection against forgetting, maybe it doesn't. We should really let the domain decide for us and not create the problem after issue.
So maybe I don't have like strong preferred application of continual learning, but what I always say to the companies I'm talking with is that understand the continual learning problem you're addressing is interesting also for us, but researchers is there an stationarity for storing the data? Do you need a high frequency of the update of the model? You have a high throughput of the data, and the data is flowing quite fast. So if these properties are all satisfied, this is a very interesting continual problem. Not like the word, these happens on the edge, the clouds, the middle of it. So, and I think that if you can make these and other properties, of course, then it may be a very interesting continual problem, no matter the context of data objectives.
Okay, these are some really interesting thoughts. Thank you for that. So Joyce, I heard you say, like, privacy, that's also like a concern in continual learning. Is that why you focus really for XMPP-free continual learning? And maybe the other thing is also like experience replay. Is this the way to go, or should we really focus on other ways to avoid forgetting?
Okay, one of the contexts I used it in was in mobile devices like mobile phones. So they're often, you have you can train a very good model on the cloud to apply to the users, and there it's maybe forbidden even by law that you pass the data. No? So I think that's a very real setting, and where you need continual learning to adapt to the user. And you also need often, because the user has a much smaller set of classes of data than in which you want to potentially apply it, you need to keep the power of the source model there. So I think that's a real relevant setting. Yeah. I think replay is also an interesting, still a highly efficient way of retracing, forgetting, maybe the most efficient way. But okay, I personally like this setting of example 3.
Yeah, I mean, I think to some extent it's application dependent, right? If your application is on-device learning, you don't have a lot of memory available to you, or you could have privacy concerns about processing the data somewhere else where it might be stored in a server, then of course it's probably beneficial to not have to necessarily replay data. On the flip side, if you have access to a lot of memory, maybe, there's a lot of interesting questions that can be asked about replay and the influence that actually has on a model's performance, right? You can imagine the upper bound being that I store everything that the model has ever seen in its past. But even if it had access to all of that data, identifying which data within that buffer is the most essential to improve performance on the future things is also a really interesting thing to think about, right? I also really like the biological plausibility of replay, right? Because humans, it's been shown that we're replaying memories during sleep to actually firm up the memories that we learned during the day, right? So I think the biological connections of replay are really interesting, but perhaps it's prohibitive in specific applications like edge computing where we don't have a lot of memory available to us.
I worked a bit on replay 3 to learn, mostly because replay from raw data is not enough, right? It's biological. And people used to do it and still do it pretty much. And then also because it's a bit harder, it seems to be harder, so it's a more interesting, challenging problem. Then I think that for practical applications, replay is definitely useful, but it's also a bit dangerous because so what we assume in deep learning is that is what's important. Everything we have seen so far is important because you are saying that you don't want to forget, right? And so this is I think just part like a sign of the coin, right? So we have seen that the main adaptation, the notion of adaptation is sometimes much more important than just being robust with respect to forgetting. Actually, forgetting is important, right? Being important because things are not valid anymore in the world. So replay and naively applying the behaviors because it destroys the natural, let's say, semantic of the world. Just for the sake of building robust representation with the hypothesis of that everything is still valid and yeah, leveraging this hypothesis improves what I would say. So these are my companies, and just absolutely just a tool we play that we can use, and there are many others and many other ways to do things.
So I've been a staunch enemy of replay since I entered the field, at least of naive replay. You know, it might be good enough in some situations, but it almost certainly wastes computation. It most certainly makes engineering more difficult because you have to worry about storing data. In some cases, I'm thinking about RL, my perspective obviously, is that in situations where you have a hard exploration problem, your replay fills up with garbage. You have a lot of episodes where nothing interesting happens, and it's almost impossible to, you're very unlikely by random to pick the one episode where you find something interesting. There is a lot of interesting work on rehearsal that optimizes the replay. Siddharth and I both have papers in Gaussian processes where people for a long time have thought very hard about what are the best examples to store because I've got to do big and computation. One more issue that we're seeing now is in the training of large language models, for instance, we're in a situation where so much data we can't actually do more reports. That's how bad it's becoming. And here's a situation where I think good memory architectures and good ways of figuring out what to store could be quite useful for other ways of machine learning. So keep emphasizing what we like to more.
Okay, thanks. So I heard that like forgetting is like in the field, you know, that forgetting is really focus and avoiding this catastrophic forgetting. There are also like instances or like examples where forgetting could actually be useful. I haven't seen a lot of work on that, but I would love to hear your thoughts on that.
Yeah, I've heard a lot of that. Bias in models, for instance, is a huge worry for everyone.
and it's often sort of quite difficult to kind of maybe can't retrain. And I think we've gotten quite good at continual learning to figure out with the early weight regularization papers, they essentially attribute the importance of certain weights to a data set of tag, right? So perhaps that information can be used to kind of manipulate your network in a way that you can debias, say, an image classifier and so on. So I think this is an example where forgets can actually be sort of a weapon or a tool against a bias and something like that.
Yeah, I think there are no so many works, let's say, within deep continual learning, working this way at the moment. There are many works in areas like learning, saturated environments, non-conceptual adaptation, let's say, incremental learning, lifelong learning, that focus mostly on adaptation, right? Let's say, knowledge consolidation, accumulation, or robust representation learning. There are many works in that area, and I'm really keen on learning more about them myself. But yes, within deep learning, that's not much explored. And again, I think that to learn robust representation, you also discard the bias knowledge over time. To have that generalization aspect, you shouldn't just accumulate knowledge. I think many methods in CL, they actually are just accumulating bias as knowledge. And the picture is maybe either, but if you test that system on auto distribution data, you quickly realize that it just accumulated knowledge about the specific tasks, right, that they encounter. So that's a problem, and I think that we will work in this area. And myself more invested in trying to find a compromise, right, in not forgetting, and at the same time forget what's not important, what's just spurious correlation that you find in data.
Yeah, so I mean, I definitely agree that there's times to forget. And I think a lot of this, again, comes back to the benchmarks, right? The benchmarks, the upper bound right now is being able to perform well on all previous tasks, which almost encourages us to never forget anything, even if it might be unnecessary, right? So I think in order to start targeting this problem, it's interesting to think about which domains or which types of problems are most interesting to consider where forgetting is actually important. And I think this kind of circles back to someone's thought earlier about let the problems define themselves instead of trying to create these artificial scenarios, right? Maybe once we start deploying these systems or making more deployed-like settings and identifying what is actually crucial for those systems to perform well, we'll start identifying, you know, what pieces of information are important to forget in order to continue learning. I guess an alternative thought to that too is, right, our representations of things are constantly evolving over time, and it's perhaps good to forget certain things, right? Like maybe at first I learned what the human category is, but now I learned Vincenzo and I want to learn more specified features for him, right? And it might be necessary for me to forget some of those biases or those spurious correlations that just generally encapsulate what it means to be a human versus the more fine-grained representation that I've now seen at a later time.
So one of the problems with non-IID training is that you, even if you do it on the same data set, like the experiment with Pascano, you cannot get to training, if you break the data set in two parts and you first train on the half and then on the whole, you cannot get on the same result as starting from start directly on the whole data set. It's really this shows that these biases, that you need to forget something, it seems. So the only method which actually works is shrink and perturb. So, and that's actually forgetting, no? Shrink and perturb, you just forget. So I think it's an important thing of continual learning. What do we need to forget to maybe better learn in the future? Yeah, and another aspect is, of course, if you really want to forget all things, if you don't need them anymore, then you could forget all classes. That's another aspect. But maybe more interesting one is one where your knowledge is blocking you to progress and most efficiently be able to do what you need to do now. How we need to do that, I don't know. Shrink and perturb. Yeah.
So, Vincenzo, you mentioned like this generalization to be very important. So then I would look to Jonathan, like for the meta learning stuff. Okay. Like, how can we connect it to continual learning? And these two tools?
Yeah, I think there's a lot of harmony, and they keep growing close together. There's very nice academic work on learning to continually learn. So people might be familiar with manual as a classic example that's quite popular. But this idea that I optimize for visualization or some sort of part of the model such that I can quickly adapt. And you can rephrase that problem and say you can learn the model, the outer meta model, in such a way that you can quickly adapt to sequences of data. So people have done that, and I think it's quite promising. It's difficult to defer on task sequences, but you could imagine it being sort of the algorithm of choice when you have a natural interaction with the user in a small data machine. There's actually later, when people are interested, I've got a presentation later on where I'm going to talk about meta learning. And it's effectively meta learning with the replay buffer over time, and it shows incredible forward transfer. And you really need to like look at meta learning forward transfer. And basically, I'll give an indicator of that later. So yeah, those are my thoughts.
Yeah, so personally, I'm not a fan, let's say, of maybe from reading that not kind of dedication of mental learning to solve continual learning problems. Mostly because I'm still not seeing them because of my knowledge, but there's a strong evidence suggesting that this mental learned model can generalize to new tasks that are quite different in terms of distributions. The one is to train. Also, they are quite expensive computationally, blah blah blah. But I mean, the main counter argument, is supporting, let's say, my science approach to the use of meta learning is I have not seen, let's say, strong evidence suggesting that this approach may be used to take on, let's say, never seen before tasks from very different distributions.
I guess I have some related thoughts to Vincenzo, but I guess they more come from the thought that, right, we have to perform a meta learning phase in order to learn these sequences and how to perform the continual learning on the sequences. But since the world is always changing, it means that we would have to do this, probably have to do a meta learning stage at various time points during, like, throughout training, if that makes sense, right? Like if I'm deploying a system for several years, I might have to meta learn how to best learn the new sequences each year. So I guess I'm interested to know about the generalization capabilities for very long streams. But again, some of this comes from my own naiveness of not actually having worked on meta learning. So I'm interested to see Jonathan's talk later about this as well.
Yeah, I think it's a very interesting direction. Yeah. So within the context, for example, of my talk, where you have unsupervised domain adaptation, there we are constantly making new losses which better allow you to adapt to this unlabeled domain. But we have a very good loss which works, which is the cross-entropy, if we have the labels. And actually we have the labels as a community. So it is very interesting to learn the loss which without labels gets you as close as possible to this cross-entropy loss which has the labels. And this is sort of a learning to learn or learning to loss function. I think that's a promising direction, and it's very difficult. I did some attempts with students. It's not easy, but I think it will really, it's needed, and it should give a good improvement if you get it.
So maybe I can answer some of those questions. Well, basically, the result of machine learning, most of the time, the better way people do it is a system that can adapt with a couple of gradient updates to data that I've seen. But there's nothing saying that I can't just keep running this for 5 years and then like continual learning algorithm. All that we get is effectively visualized, optimized visualization. And from the perspective of a continual learner, it doesn't necessarily matter where that visualization comes from. And we can deal with that and use all of the continual learning techniques after that. So that would be my answer to that. But there's also machine learning ideas that instead of optimizing task distributions, optimize within a single task, and they can be used to, for instance, to learn your hypercomputers online. And that could be, I think, also quite interesting. And in those cases, I don't necessarily have that concern about running the project. So yeah.
Cool. So that has been great so far. Like we have 25 minutes left, so also to the audience, if you have any questions, you can just go to the microphone there, and the panel can answer that for you. So go ahead.
Maybe the panelists can speak about whether they think there is a single solution to the problem of continual learning or catastrophic forgetting, or at what extent should there be different solutions under what settings?
So the question was about was if there exists a single solution, or may exist a single solution to face that sort of forgetting, or if it depends on specific context. So that's what I think no. So there's no single way or mechanism to solve forgetting. I think there are many competition approaches that have been proven to be interesting, successful to some extent, and often using conjunctions. So there are many ways, as we also have learned from biological evidence that can help us achieve our goals for continual learning, adaptation, useful last features, and so on. And then, absolutely, as Tyler said before, everyone actually, panel, having the application, these additional methods can be very different, and it's part, I guess, of our job to find a trade-off overall, and maybe provide some risk, some models that can adjust automatically, right, based on the specific needs. And something in the field argues also that maybe just, I don't know, becoming stochastic and may provide some answers, right? Continual learning seems to be at the moment still at least involved to me, but that would be great.
Yeah, so I mean, like Vincenzo mentioned, right? I think there's not necessarily one exact algorithm that's going to work for all problem domains, specifically just because of the outputs being different, right? And different problems pose different challenges that we might have to deal with. So I think from that regard, there probably isn't necessarily one solution that fits all things, but to kind of go back, I think that maybe some of those components are reusable across different domains, and maybe, you know, looking at which components are applicable to a wide range of domains could be something to consider. We've been talking a lot about today robust feature representations, right, and the reusability of those for different domains. So I think that it's kind of interesting to think about having a set of reusable features that maybe could be somehow adapted to the particular domains that they're being applied in, which might be something interesting to consider. But I mean, I don't have the answer, but intuition says to me that there probably has to be at least some specialized component for different domains, maybe on top of some larger system.
Thanks for the great question. My question is about large-scale pre-trained models, foundation models. So what changes for continual learning do you think, given this recent trends in large-scale pre-trained models that are supposed to be good on many different tasks? Thank you.
Well, I think we partially answered this question. That was the first one. It will become definitely more interesting, I believe, to work on other aspects of continual learning, not just robust representation learning, especially if you have this fixed task, fixed domain, a very well-constrained and clear problem. Then, of course, in that case, it'd be more usable to think of other interesting things, like propositionality, reasoning, all this nice stuff that you need on top, let's say, of all these word features. So it's not really about learning, I guess, anymore. Just other interesting things that we are always discussing in AI, right? And needs adaptation. Right? It is still understood as one of the main pillars of intelligence, right? So adaptation, new goals, reasoning. So the focus will shift a bit from learning to this stuff based on the this model. But again, I think that in a complex world with different agents, we're talking about distributed learning, how it intersects continual learning. We open like a world of additional problems for CL, and there's a lot of space to be efficient in adapting to the different aspects of reality, and so really learning all the time. So even if you have all these models, like for example, you have a language model, then in the future maybe something very similar to GPT-3 for vision, but then if you want them both, I don't know, you need to learn how to use these models, this knowledge. I mean, there's a lot to learn.
I was going to say like distributed continual learning. Like mainly what I heard today was about like device continual learning resource constraints, but what if you look more at this distributed approaches, like more regarding federated learning? Can we use continual learning in such a context?
Let me first speak about distributed learning and then about federated learning specifically. So I mentioned issues of distributed learning earlier, right? The fact that the way that populations evolve is such that carousel forgetting happens, and it's an issue that people have no better solution than just sort of reloading checkpoints and then adding those to the population, and they have no good methods of figuring out which checkpoints to load. So this is a great place where continual learning can actually make their lives much easier, and also the system is safer, because you can never have a guarantee that you don't have an explosion from some previous agent that has improved the population. In terms of federated learning, I feel like we've kind of mentioned that a couple of times today. So this might be setting where the data on my device can't actually leave the device to retrain, say, initialization. I think this is a very good example both for continual learning.
I'm also very excited about the future of distributed learning. So far, we have focused mostly on this agent-centric view of continual learning. So we have single agent is learning from observations, pretty much as universal learning, right? But I think this may be quite limiting for the future of continual learning. So in a sense, for example, as humans, we don't learn new knowledge just by trial and errors, right? So for example, we want to do a cake, right? So what you do is not try several times to make it work right with each and every instrument. So you just go to the internet and you download the recipe, and the first time or the second time, the cake is there. So that's great. You learn from past knowledge that someone else has used with you. And I think the same will become possible and necessary actually for continual learning. So instead of learning directly from observations, from data, that will become rather unlikely, or it is necessary, but it is a partial aspect of learning. We will learn that directly from trained or built models, so compressed knowledge that is someone else has already learned for us. And so that's quite aligned with the distributed learning, federated learning. So federated learning has a tight synchronization aspect, right? You use a Moodle, you synchronize all peers. But a more decentralized, distributed, continuum, let's say, way of learning will be very fascinating. Actually, we have a poster about this first work. We have together with special transform and so we call this regarding X model continual learning, which is that continual learning scenario that instead of learning from data, you learn from models. So X comes from Latin, from models. And so I think that's quite an interesting new way of seeing the learning, and I think it will become prominent, say, for the future.
a very interesting direction. I think, I would say we already do it in some papers. So there is a group of papers which does class incremental learning by arriving at a task and initializing a new model, which is allowed to have maximum plasticity and adapt to the new task and forget whatever it forgets. And then the problem becomes, how do I get the knowledge of this new model into the old model? No? So there are a couple of papers out there which do this, and their work actually, let's say, on our benchmark paper, for example, that the best model out there was doing this. And so this is maybe a two-agent problem then. And I think, yeah, it will be interesting also to further see this with multiple agents which go to different tasks, all come together, then how to efficiently talk together. Yeah, so at the moment, we mostly use distillation for the talking. That's very passive, I would say. It would be nice if there are more active ways of telling each other what you have learned new. I think there is a lot of exciting research out there.
Okay, so like this two-agent approach reminds me a bit of like progress and compress, right? What are like your thoughts on like multi-agents reinforcement learning, and could that also be useful?
Yeah, I'm not necessarily an expert on multi-agent reinforcement learning, but I've seen the capabilities of distributed systems and multi-agents, and if it's done properly, but it's difficult to do, and you need real experts, and it's a bit of an orthogonal problem to continue learning. But I think that if you have a specific goal in mind, and you can set it up such that multi-agent or a problem can work, I think it's quite a promising approach. But that's all I can say.
I think we have a question.
Your answer to the massive improvement in generalization was the need to be able to learn new tasks during continual learning. And I'm really interested to know, first, if you know how to measure if this is actually happening, how will you measure if it's happening, and your ideas of how to increase learning new features during the rotation.
So how to measure the improved generalization of the model? Is that the question?
No, the additional maybe target specific features, or can the model bring learn new features during the adaptation?
So yeah, I think how to measure this is the question. Then I think the model is learning new features. So one way to measure that very simply is, I think, train a classifier on your incoming backbone and train a classifier on the outgoing backbone, and you see that you will have an improvement. So I guess from that point of view, you can see that new features have been learned, and you at least you improve on your new task. If these new features, I don't know if you want to, if these new features also help you for your own tasks, that's maybe more difficult. The backward transfer.
I mean, one can argue that it's just a question of clustering the previous information rather than generating new information.
Yeah, I think you could look at mutual information. We have actually used some methods to look at but only with linear mappings between new and old representations, and see how much they compare. And there you see that they do differ. So let's say some of the features are not explainable by the old model. It's as far as we went. I don't know if anybody else has seen.
As a follow-up to your previous discussion about how to combine multiple models in a federated learning setting. So if I was to summarize, I would say it's like parallel approaches are like a single phase, like EWC, that the catastrophic forgetting happens during training, or or maybe multi-phase states where there is a training phase and then maybe combine some knowledge. So where do you see that direction for a solution to, let's say, catastrophic forgetting is a single phase or a multi-phase solution?
So let's say I currently am convinced that this multi-phase solution is a good way to go. There are multiple papers also in this direction. And Google Net, I think, emerged this year also, which has a self-supervised learner, which is a slow network, and a fast network which adapts to the new task, and then slowly this information is adopted in the self-supervised learning. I think these self-supervised features, which are really much more shared among tasks, are here to stay. So that's an easy basis for a slow learner. So in principle, yeah, I believe in this sort of two-speed systems.
Yeah, I mean, I think there's some other interesting questions. So I think the speed question is really interesting, but there's also this question once you talk about distributed learners of what the distributed learners are learning, right? Do you want them to each be learning kind of overlapping tasks, or are they going to become experts in something and then at some point consolidate their expert knowledge to each other, kind of like multitask learning at some point, right? So I think that there's some different considerations when you start talking about distributed learning about like what the individual learners are working on. Is it better to consolidate that knowledge? Perhaps it is, because now you want some learner that was an expert in one thing to also become knowledgeable in another thing, and maybe that even improves its performance further via transfer, right? I think that the idea of timescales of distilling this information from one learner to another is also interesting, right? So having something that's like rapidly learning on device, right? But then maybe I have some period where it can go consolidate knowledge back in a more slow learning or batch setting, right? To acquire those features that are more deeply necessary for understanding the information at a deeper level.
Yeah, I don't know if it is different phase, but I like let's say the approach of trying to distinguish the objectives. That is, on one hand, you want to learn theory how the world around you, right? To understand the world without specific tasks in mind, right? And on the other hand, you want to solve something specific, you want to predict something. So separating these two objectives is, I think, elegant in a way, but also practically important, because in a sense, when you're trying to just model the world and what's happen, it can be mostly a surprise, just trying to get as much knowledge as possible about the world, and then in another, let's say, the other objective, you want to use that knowledge to see that happen, to solve a task the best way as possible. So if you handle them together, you basically put strong biases, and we know in past learning already, for example. So if you want to solve that problem, you come to these new classes and you want to accumulate knowledge, is very tough on catastrophic forgetting, for example, because you want to solve both objectives at the same time. And then it turns out, as I mentioned, for many strategies, they're just accumulating knowledge, just removing the aspect of building robust features, just say, okay, these classes are going down, to distinguish them, some tricks, let's say, some heuristics to make it work all together on the overall problem. But so I really like this idea of learning over time, robust representations, and then isolate a bit the bias to learn something specific. That's really interesting for me.
Yeah, the question about multiple phases sort of reminds me of the complementary learning systems sort of perspective of things. I think it's very unlikely in practice in engineering system that has one single thing doing everything. We saw Bing's diagram earlier, which had many different components, right? You might have an uncertainty, a component, you might have an out-of-distribution detection. The question arises, what do you actually need to do with the decisions the model comes up with, especially in sensitive applications? There might be a human in the loop. And so even though in deep learning, we have this sort of romantic idea of doing everything from raw data, you know, end to end. Yeah, I feel like when it's useful, we should approach complementary learning systems very multiple
think we have some questions from the Zoom as well.
So the question is, what is the major challenge faced by online continual learning compared to regular offline continual learning? It seems the online accuracy is lower than the offline, so do you think one day online continual learning performance can match the offline, or there still exists?
So maybe Tyler, you have some gap between online and offline continual learning.
Yeah, I mean, inherently by the way that the problem is designed, it challenges the model much more, right? Like not being able to learn in batches and having to learn one example at a time is naturally much harder. So it's potentially, maybe it could reach the accuracy of the offline learner, but it might take a lot longer just because of the nature of having to see more data, right? I would be curious to see if we train something in a batch setting using some fixed number of examples, where is the performance of the online learner with respect to those number of samples, right? Like, what is the sample efficiency trade-off and the computational efficiency trade-off of, learning one sample at a time, but having to see a lot more samples or doing just a few batches on some samples, right? So I don't know if that answers the question, but I'm not sure if it will reach the performance. Perhaps it will, but it needs more training stages to actually reach that performance. But just by nature of design, it's sort of a harder problem in some sense.
There is also another one. Also, for future and supervised continual learning, do you think an auto distribution of the data should be necessary?
No, I guess in many practical situations you will move on. For all, I don't know, for all probably not, but many, but that's even in the non-continual learning setting, I guess, for classification networks, it's important. Yeah, in a continual learning setting, you can then go further now. So if you have decided it's out of distribution, you can try to learn it, cluster and learn it. Yeah, I think we commented it before. I think let's say in a total system of lifelong learning, it should be one of the ingredients.
I think perhaps there's a question of distinguishing between out of distribution, that I should be learning it, or out of distribution, and this is data that is not appropriate for the system. Anyone who's ever played real world data knows that there's a lot of rubbish in there, and you don't really want to sort of destroy your ability to do all the other tasks by basically migrating update on data of that sort. So for that reason, the answer is yes. We should probably be fine.
Maybe we have time for one last question. Yes, go ahead.
Yeah, so I think continual learning is actually a very natural generative set for basically you want to part of the applying distribution. However, as most works focus on classification, that's more natural to define. So does this make sense? Again, it's like a solution for me and to approach things, or fundamentally it has to be about discrimination. Putting on once with discrimination, I think you just need to shift your medium plus market. This means that it's also probably quite easy to just keep learning more and more lines.
I'm not sure I understood the question well, but you can model many problems. Like maybe you mentioned just classification, right? Not regression or other problems. But yeah, classification is limiting in some sense, but we have seen that many computation approaches can be also quite agnostic to a specific task at hand, right? So if you have a regression problem, many of those approaches may work in that context as well. So again, I don't think there's a unique solution to everything, but I still think that classification is if a data with a good say, approach, right? For example, weighting with other metrics, just accuracy, but with other metrics, the quality of the features, what's happening, may still be a valid, let's say, scenario for assessing the learning algorithms. Yeah, after all, you can always model an agent, right? With a fixed set of actuators as a classification problem, right? And that's it.
All right, so that then concludes the panel for today. I certainly learned a lot from you guys. I hope the audience did too, and also people will too. Thank you all for joining us. Let's give them a very warm applause. So we will be back in 30 minutes. There are posters and papers in the meantime. So I can see you back in.
Now I'm starting to think of all of the other answers that we did.
The classic.
Yeah.
Okay, now we have the second paper oral presentation from Fabio Cermelli. Fabio is a third-year PhD student from the Visual and Multimodal Applied Learning Group at the Politecnico di Torino and Italian Institute of Technology, supervised by Barbara Caputo. Fabio?
Thank you. Am I supposed to take the mask or remove the mask? I don't know.
You can remove it.
Okay. It's fine. So, hello everyone. And today we'll present you the paper I will also present you tomorrow at CVPR, which is a poster. It's a poster paper, and it is called Incremental Learning in Semantic Segmentation from Image Level Labels. And I will start from what is semantic segmentation. I think every one of you knows what's continual learning. Maybe someone of you is not familiar with semantic segmentation. And semantic segmentation is a task where you want to label every pixel of the image. So, for example, in this image, you have a cat with some background, for example, the sky, the trees, and the grass, and you want to label every pixel of the image with a semantic category. And it was CVPR 20. We introduced the setting of incremental learning in semantic segmentation. And the goal, of course, is to extend a segmentation model over time, introducing new classes using pixel level annotation only for the new classes. So we started from the model at time step 0, and we had the full pixel level annotation. So for this example, we have the labels of the horse and background. And then we started to introduce new classes over time, requiring per pixel annotation. So for example, the cow, and new classes, for example, the sheep. But every incremental step had only the new classes annotated. So for example, you see that there is a dog in the last image and the dog is not annotated, even if it's a known class. And to some extent, this was because we felt that it was not useful to relabel something we already know. So for example, we know the class dog, we didn't want to label it again. And this brings us to think even to make a step farther. So we thought it is important to have per pixel labels or not. Can we learn new classes even without any per pixel label? Because in semantic segmentation, the issue is that semantic labels are really expensive. So we end up with the new weekly supervised incremental learning in semantic segmentation setting, which the name is Infinite, where of course, instead of using the per pixel annotation, we want to use only an image level label. And what is that? It's only an information of which are the classes inside the image and without any localization prior. So we don't have bounding boxes, we don't have pixel label labels, we have just the information of which are the classes inside the image. And just to give you an overview, we have two challenges in this setting. And the first challenge is that we need to extract the per pixel supervision to train our model from the image level labels, because we still need to have a semantic output from the model, and we need to transform the image level labels to some semantic output. And the second, of course, is that we want to do that without forgetting the old classes. To give you some overview of weakly supervised segmentation, it is a field that exists from few years, even decades, and is the setting where you want to learn classes in a offline setting. So this is not continual learning from weakly labels, for example, image level label, bounding boxes, tribbles, and so on. And for image level labels, there are mainly two approaches. The first one is the two-stage framework. And in the two-stage framework, we have this fully convolutional network that has a class core at the end. And often these class core are aggregated, and then this minimizes the multi-label cross-entropy loss on them. So we can learn where are the classes by using this cross-entropy loss and the CAM technique, the class activation map technique. So after we get this class activation map, we refine it and we obtain the pseudo labels that are then used to train a downstream segmentation model. Of course, this approach is good, but requires two stages. So it's not feasible to do that end to end. So some approaches try to make it end to end, and this is called the single stage framework. That is the one we use in our work. And basically, it is different. It's simply different, but the idea is the same. We have an aggregation. We train the model with a multi-label cross-entropy loss, but instead of making two steps, we already obtain the pseudo labels during the training of the model, and we get the pseudo labels, and we train also the model with a per pixel percentage loss using the pseudo label. So it's pretty simple, but it's effective. And so, given this setting, we come up with the Wilson framework. That Wilson stands for Weakly Supervised Incremental Learning Framework for Segmentation. We started from a knowledge distillation approach. So in the gray, in dark gray, you see the old model, the model trained and the previous step. And in the white or light gray, you see the model, the current model, the student one that needs to learn the new classes. So given this architecture, how can we learn to extract the pixel level supervision from the image level labels? The first step we did is to introduce a localizer. A localizer is simply an auxiliary classifier that we use to extract the supervision for the new classes. The localizer is trained with to extract class scores in a CAM fashion, and is trained using a binary crescent loss. So we get the class scores, we aggregate them to obtain a single vector for the whole image, and we train it using a binary crescent loss or a multi-label crescent loss. But since the classification loss is will produce coarse blobs for the classes, we found that it is important to use the knowledge of the model that has been trained in the previous steps. So the previous steps are trained with per pixel labels, and we are in some way we know that we can extract better boundaries if you extract some prior information from that. So we use the information coming from the old model as a localization prior to the localizer. So we provide a guidance on the old classes. So for example, we say to the model that it should not focus on the pixel where the person are, because the person is not a cow, so we are not interested in these pixels. And also we use the background class as a saliency estimation. So when the background is low, probably there is a class inside. And so we want the model to produce an output for a class in the pixels. So it's kind of a saliency estimation. So after we started to train the localizer is able to extract per pixel pseudo labels. And so we can train the segmentation models using these pseudo labels. But since the pseudo labels are still noisy, we introduce a smoothing operation, which is simply a linear combination, a linear interpolation of the raw probabilities coming from the CAMs and the hard pseudo labels. And this helps to not feed the noise that comes from the model. And having this smoothed pseudo supervision for the new classes and having the old class prediction from the old model, we can combine them, and we can train the segmentation model using both targets. And all the training is performed end-to-end. We start with a warm-up for the localizer to extract, of course, the initial seed for the new classes, and then when we have the seed, we train the whole model end-to-end. So we compare our model with in the standard benchmark for continual learning incremental in semantic segmentation. And so we use the Pascal-Vogt 15.5 and the Pascal-Vogt 10.10, disjoint and overlapped settings, and the Coq-to-Vogt, which is kind of new, where we started from the 60 classes of COCO, which are not in VOC, and then we introduced the Pascal-Vogt classes in the second step. And here you can see some qualitative results. You can see that our model is able to extract good object boundaries, and I mean, it has a good segmentation performance, but of course it has some failure cases. For example, sometimes it mixes up some classes, or it's not able to perfectly define the boundaries of some classes, for example, the monitor or the boats. And here instead are some quantitative results. So in these tables, we compare with weakly supervised methods that we adapted to the continual learning scenario. So you can see CAM, SIM, single stage, and APS. Basically, to implement them in the continual learning scenario, we use this method on the new dataset to extract the pseudo labels, and then use the pseudo labels to train incrementally the model. And you can see that our method is better both on the new classes and on the old ones. Let's say that on the old ones it's quite comparable, but on the new class we are the best on every setting. And I think this being the best is especially due to the fact that we are reducing the noise of the pseudo labels, and we are using the old model prediction as a saliency for learning the new classes. Instead, here there is a comparison with other per pixel methods, so incremental learning methods in semantic segmentation that use pixel labels. This is the state of the art, and you can see that our middle, even using any per pixel label in the incremental steps, is close to them, and in some cases even superior. For example, in the 15.5 block disjoint setting. I think that's all. If you have any question, I will be happy to answer. I hope I'm on time.
Thank you for the talk. I was wondering, so this is a weekly supervisor setting for Montreal. There's a lot of variation of weekly, those people or those kind of stuff. Do you consider also this kind of other weekly annotation?
No, actually, I think the image level labels are the hardest, is the hardest choice you can make, because you don't have any localization queue. For example, with point scribbles, you have at least some area where you can focus to extract the new classes localization. The same is for bounding boxes. In bounding boxes, quite of the opposite. You know the region where the object is, but you don't know actually the pixels. So we started with image level labels because we thought they are the hardest, and they are also the most available and cheapest that I mean, you can find them online, for example, in a standard dataset, or you can download them from the web easily. So we decided to stick with that. But of course, it can be interesting to extend it to other weekly label settings.
Thanks for the talk. I have a question about is segmentation an application topic that makes things different in the functional learning point of view than classification?
So
there is some other problem to solve than classification.
Yeah, so talking about incremental learning in semantic segmentation, the issue is that we have multiple classes in the same image. And so from how the setting is defined, we have only annotation for the new classes. And this is, of course, more challenging because you may have an old class inside the image, but it is not labeled. So, for example, in semantic segmentation, the common assumption is that everything that is not labeled is background. So maybe you have a ground truth label for the image, where you have a null class inside the image, and you provide the label as background. I mean, you label it as background. So if you fit the ground truth as it is, you will forget. Even the forgetting is even worse because the model is forced to say that this class is background. So yeah, I think that semantic segmentation has its own challenges. Of course, we still have the same challenges we have in image classification, like the feature that will shift towards some new features. And so you need to regularize them. You don't want to forget, because of course, even if you don't have the background shift, you will tend to forget the old classes, but I think it introduces new challenges. And we demonstrate that the same challenge in some way are also present in object detection. I have another paper in this workshop where we demonstrate that the same background shift is also present in the object detection setting. So I think that going beyond image classification can be harder.
Yeah, no,
thank you very much for the opportunity.
Jonathan is here. So we now have the last invited talk from Jonathan Schwartz. Jonathan is a senior research scientist at DeepMind and at the University College of London, where he was advised by Yevi Ete and Peter Latham. Jonathan has been working on various aspects of continual learning and related topics for the last 5 years, publishing diverse methods and benchmarks. He has led teams focusing on continual and meta learning, both in research and applied settings at DeepMind. And prior to his work in machine learning, Jonathan has worked in robot navigation and built computer vision systems for climate change monitoring. So, Jonathan, you are welcome to the stage.
Yeah, thanks very much for the invite. It's so nice to be in a conference in person. I'm sure for many of us, the first time in years. The good advantage of being the last speaker is you don't have to kind of introduce the whole kind of problem. So I will dive right in. This talk is basically kind of essentially a change of my approach towards continual learning that I've sort of experienced in the last year or so. And so I will kind of split in 3 chapters. I want to bring everyone up to the state of sparsity, the state of the art in sparsity in deep learning, then how sparsity helps us with catastrophic forgetting, and importantly, 3 strategies for forward transfer for sparsity. Okay, so where do we stand in 2022 in continual learning research? So we've got a huge amount of work that's been done over the years. Really everything under the sun. We should always remember we've got these 3 goals here. Sorry, I'm gonna try and move this bit away. Okay, we've got these 3 goals. We want to be scalable. We want to avoid forgetting as much as possible, at least if we think that knowledge is useful, and we want forward transfer. I think we've made a lot of progress in terms of benchmarks and evaluations. Certainly when I review papers, I've noticed a lot more emphasis on kind of good science, and there's a lively discussion about the goals of continual learning, like today at the panel session. But still, we're in a sort of position where you kind of have to pick 2 of the 3 goals that we want. And I think about 90% of papers tend to focus on scalability and somehow avoid forgetting. And I think the aspect that's often left out here is forward transfer. And so my argument for sparsity is going to try and convince you that sparsity is actually often a much simpler, less computationally expensive, more effective way of tackling forgetting without some of the negative side effects we get from other techniques. And then finally, some of the algorithms that use sparsity as a component for continual learning directly benefit from advances made by people for entirely different reasons. So people study sparsity for a lot of reasons, and what you could basically do is implement a catastrophic forgetting algorithm, wait for a couple of years until the sparsity folks have implemented something better, and you immediately get better results. And so I've put this sort of invisible hand here to remind of Adam Smith's argument. If we can set up things such that we benefit from people pursuing their own self-interests, we're in a very good position. Now, forward transfer might not be something that you associate with sparsity, but some of the, I think, interesting sort of empirical results from last year have shown that actually continuing with sparse neural networks is one of the few methods not suffering from intransigence or negative forward transfer. There's certain evidence to believe that evolving sparsity patterns per task implement a sense of task similarity and reduce interference. Sparsity and meta-learning work very nicely together. And frankly, I think meta-learning is our best bet at forward transfer at the moment. And then finally, the sparsity community has thought very hard about dynamic neural networks. That is, how do I grow my networks such that it's particularly amenable to gradient-based learning? Okay, let me bring you up to scratch on sparsity. Most of the work, the really fundamental works, happened sort of in the late 80s and mid 90s. And there's been little impact on other areas in machine learning for sparse neural nets. Recently, we've seen a bit of a resurgence of interest in the field that has sort of been sparked by the lottery ticket hypothesis that states that within a big randomly initialized network, there's actually a sparse subnetwork that is initialized just in the right way. So it's the winning ticket that we can learn with that network from scratch. And so roughly around the same time and kind of ongoing there's a lot of work here on sparsity. And the motivations are diverse. So there's a lot of interest in theory, how do neural networks learn, on computational speedups, on compression, and this is fantastic news for continual learning because it means that people who don't necessarily care about continual learning can actually benefit us a lot. Okay, so how sparse can we make neural networks nowadays? This is a simple experiment that's ResNet 50 on ImageNet, and a dense ResNet 50 gets about 76.1% top one accuracy. And so what I've plotted, what this table shows a method at 80% sparsity and about 90% sparsity. There's a couple of metrics that measure computational efficiency, but the takeaway message here is we can actually get better results at a 90% sparse ResNet 50. And if we kind of take this to the extreme, we can go up to 99% sparsity, and we can see that at 96, you're still very close to 76. You do experience a drop, but this is a paper we wrote last year, and you can see through a very simple idea, we moved up by quite a significant margin. So there's reason to believe that we will keep pushing up to this point where we use about 1% of our network weights, perhaps. This is a similar result for DeepRL, 50% sparsity. This year's a human normalized score. We've got our dense network. This other dense here is effectively also a dense model, but with 50% of the parameter count. And these are various sparsity techniques. And the takeaway here is, once again, at 95% sparsity, some of these sparse techniques actually perform better than the dense model. And so this is great news for continual learning, because it means we can be much more parsimonious with our parameters and so free up capacity for future tasks. Okay, how do we overcome forgetting? It's actually a surprisingly simple idea, but it works very well. So this was published 4 years ago at this conference called PACnet. What happens is I've basically shown you here some weights. And what we'll do, we will train until convergence on one task and then perform iterative magnitude pruning. That is, you remove weights just by their absolute magnitude. And at the end of training on task one, you end up with weights where I have a small subset, the gray ones here, specialized for task one, and I've got a lot of free capacity. You proceed in that way until you hit the final task. And the important thing is you implement gradient sparsity. That is, you don't override the gray weights here. And so you end up with essentially with a network where I have certain weights specialized for certain tasks. So by design, I have eliminated catastrophic forgetting. It's not going to happen, but I can still get forward transfer because I can obviously reuse some of the features. So this is simple, everyone can implement it, no rehearsal needed at all, and it's very effective. To show you how effective this is, here's some results that I stole from this Continual World paper. This is a very nice benchmark on sort of robotic manipulation that was published last year. I encourage you to check it out. It's one of those few good sort of continual learning benchmarks where people thought really hard about how to build a good benchmark. And here's sort of all the methods under the sun. Simple baselines, multitask training, perfect memory, and a bunch of the techniques I'm sure that some of you know. And what we see is that, what we see is that in terms of forgetting, a lot of them do quite well in terms of forgetting. By design, PACnet effectively eliminates forgetting. But forward transfer is really the distinguishing factor here. It's really only fine-tuning that is not a continual learning method and PACnet that get positive forward transfer. And so for me, this was really sort of the moment when I realized I had to pay more attention to sparsity, because we've worked all on these techniques for a couple of years and they're really, really bad at forward transfer. Okay, I'm sorry. So seeing this paper, we came up with this idea called power propagation, which is effectively a new sparsity technique that we built with continual learning in the back of our heads. It's a simple idea. What we were trying to do here is create a rich get richer effect, ensuring that the solution to a learning problem is encoded by a small set of large parameters. It's a one-line change to your neural network code. What you do is, in the forward pass of a neural network, you effectively you do a sort of element-wise multiplication with the absolute value of that weight raised to a power of your choice. So alpha is greater or equal to 1. If you plug in alpha equals 1, you get the standard forward pass. And if you increase alpha greater than 1, what you do is you effectively raise the weights to a certain power without changing the sign. So if you plug in alpha equals 2, you effectively square the weights, but you preserve the sign. The reason you want to do that is you get this sort of effect on your gradient update. You have the standard update and you get the scaling factor here. The scaling factor ensures that the absolute value of the weight appears in the gradient update. So if you've got a small weight, any update that weight gets is effectively scaled down by its already small value. If you get a large weight, you will amplify gradient-based learning. And so this is this rich get richer effect. The parameters that happen to be initialized large at the beginning of training carry most of the solution. So properties here. the best way of showing the effect of propagation is this plot here. So this is showing for converged networks the smallest weights, the distribution of the smallest weights. At alpha equals 1, that's the standard learning setup, we get something that looks almost like a uniform distribution. And as we increase alpha, we sort of squish the weights towards 0. And so these things can be, so these weights here can be safely removed because they're effectively 0. And that's literally a one-line change in your code, and it gives you immediately implicit sparsity. What we did here is we ran this on 300 commuted endless tasks. Some of those are the best kind of results I could find, or the results I could find on the longest task sequence. The most I could find is about 70. And what we noticed is this is a version of PACNet that we worked on. As you effectively work with PACNet and propagation in combination, you can learn up to 250 tasks. And what's particularly nice here is we can compute the number of unused parameters, or used parameters in this case. And as you can see, as we increase the number of tasks, we get increasing feature reuse. And so as the gradient of that curve decreases, we need fewer and fewer capacity for future tasks. This is the same on deep generative models. Once again, it works quite nicely. Here's sort of the visual proof for that. But the reason I'm showing you this slide is actually you can use this propagation idea with some of the classic continual learning algorithms, the Laplace propagation and EWC. And what you see is that just that one line change actually improves these classic algorithms by quite a lot. The kind of computational way of looking at it is effectively we have more capacity that's free. The Bayesian way of looking at it is, since the Fisher information matrix is effectively the squared gradient, we've got more and more weights where the posterior distribution is quite broad. In other words, they're free to be used. And so maybe if you take one thing away from this talk is if you go home later after the conference and you go back to your work, maybe just try and do that one line change and see if it helps. And if it does, please let me know. Here's this is on Continual World. I'll skip this. If you want to further sort of improve catastrophic forgetting, what you can do is you can sort of apply the latest sparsity method. You just go to their workshop or see what has been published at the last conference, and then maybe it might just get a little better if you apply it in this PACNet style, and that's the invisible hand argument again. There's a couple of things I wanted to mention in terms of routing approaches, so where perhaps each example takes a different path for your network. And if you're interested in task inference at test time, there's some ways of dealing with that. Okay, forward transfer, that's sort of the kind of key element of my current interest. I just want to kind of really bring home the point of how bad we are at forward transfer. So we saw this result. Here's two more ways of measuring forward transfer that have been published over the years. And in all these cases, we're really, really bad at it. And we're great at eliminating forgetting, but we don't get a lot of speed up or better results. And so I want to focus on these two elements now. The reason I think that sparsity can help is, firstly, we can avoid some of the inherent intransigence by avoiding overregularization, inefficient parameter use, and task interference. I spoke a little bit about the first two. Task interference, I think, is more severe than people realize. So this is again from the Continual World benchmark. What the authors did is they trained on a first task and then on a second task and measured sort of the effect on the second task relative to a baseline method. And everything that is effectively orange or red here is negative forward transfer. And this doesn't come from continual learning, it comes from the fact that we get task interference. Here's a result that's actually using sparsity. So this is a simple idea. The authors used a pre-trained network, and instead of learning the weights, they just learned a binary mask on their pre-trained network. And what we see is that for each of these visual tasks here, we get quite different patterns. And so there seems to be a certain task sort of similarity that is encoded for those patterns, and that could be quite interesting. The second strategy will be primarily based on meta-learning. So meta-learning by design gives us rapid learning within task distributions, few-shot learning or learning with only very few gradient steps. Here's a paper that came out in 2019 that is using effectively an infinite replay for meta-learning. And what we see is that the amount of data needed to reach 90% performance here decreases over time. So we get faster learning over time. B, the task performance after 100 data points increases, so better generalization in low data regimes. And C, we actually get better results at high data regimes as well. So this is what we want to see. This is perfect, right? This is forward transfer that very few continual learning algorithms can rival. But of course, it's infinite replay, and so few people would argue that's realistic. So how can we turn this into a continual learning method? The answer that this paper here is giving is combining this idea with gradient sparsity. I'm just going to skip this. This is effectively the MAML algorithm. We are optimizing our initialization such that we can adapt with very few gradient steps. And what the authors did here is, instead of doing a full gradient step on all the parameters, it's just a sparse set of the parameters. So this is a sparse mask, and so we implement sparse gradients. The technical bits is these masks learned through the straight-through estimator and first-order MAML, so quite a simple way of doing it, and is used in combination with the replay methods in a task-agnostic sort of gradual drift, so the most general continual learning setting. And what we see is that as you increase the number of tasks, your sparsity actually increases automatically. The method automatically learns to not override information without any sort of additional tricks that might encourage that. And so unsurprisingly, the sparse method here gives you quite a significant kind of improvement on these baselines. It's worth saying that the sort of mask updates are is quite a simple way of doing it. And so here's a paper that we published just a month ago or so on sparse meta-learning, using a couple of tricks that get rid of some of the assumptions. And here on a image reconstruction kind of problem, what we noticed is that this is a paper from Europe's last year. So as you increase sparsity, you actually see the quality decreasing, and our technique still sort of preserves most of the visual features at 99% sparsity. So that is to say, there's a lot that can be improved in terms of sparse meta-learning, and it to directly translate into improvements in continual meta-learning. Finally, and I should speed up, sparsity folks have thought hard about dynamic neural networks, and they thought hard about how to grow neural networks. Also, it provides us with an intuitive measure of plasticity. If I give you a network trained with EWC, it's quite hard to tell sort of how much more I can learn. With sparsity, it's very easy to tell because you can simply compute just the overlap of all the masks and figure out how many weights stay unmasked. And so there's a couple of ways you can grow this. And this particular paper is a very nice paper. It's using an IBP prior on the VCL setup, and you get these different masks for different tasks. And the authors found quite a simple intuitive measure of learning how to grow. And what's also nice about the task similarity bit on per unit MNIST, what you realize is that the overlap of masks to previous tasks is quite small, because obviously the tasks are different by design. And on other benchmarks that have more visual similarity, you get much higher overlap. So there's some evidence that sparsity implements task similarity. I'm going to go through this quickly. A lot of the state-of-the-art sparsity research is essentially maintaining a constant sparsity throughout training. And that means you have to drop, or you have to set weights to 0, and you have to reinitialize them. And the distinguishing factor between a lot of these techniques is effectively how to grow. And so this is useful for us because we might have to grow because we're seeing an infinite number of tasks. And so I might just skip this. This is a way of doing it by essentially maximizing the expected magnitude of the gradients. So you initialize such that you expect high gradient information, so fast learning. And what you see here is basically the green line is the lower bound, the red line is the upper bound, and this method here does significantly better than the lower bound here. Okay, so to summarize the talk, the reason I think that sparsity is useful is it's a very strong weapon against forgetting, and there's essentially 4 good reasons for why it should help us with forward transfer. And with that, once again, thanks for the organizers, and I'd be happy to take any questions. Yeah, I think you need to code the microphone.
So you mentioned weight scaling, and I don't know if it's also gradient scaling. That sounds like a large to me, but in that case, it was more about scaling the learning rate based on what the magnitude of the weight is. I don't know if I focused anything when I was doing experiments and see if there's an effect on creating sparsity to the neural network. But could you elaborate on the difference between the approach that you outlined, to large or large, data layer wise,
Right. I'm not sure I understand the question correctly, but in terms of how to implement sparsity, there's sort of a difference between implementing layer-wise sparsity, finding a constant sparsity throughout the entire network and letting the method allocate the sparsity. And there's a lot of work on essentially predefining a sparsity distribution per layer. There's this work called the Erdős-Renyi kernel, and that is a very good way of predetermining how much sparsity you want per layer. My favorite sort of sparsity techniques are they're completely free to choose which part of the network I want to allocate my capacity in, and I found that those work incredibly well. And so this is actually what I showed earlier here. All the way back. So techniques that are free to do this effectively without any predefined things tend to find patterns that are very different from what humans predefine. And so I think this should be a data-driven decision, basically, like anything else. Yeah. Thanks.
In continual learning, there are different kinds of sparsity. You have sparsity of the weights, sparsity of the observations, sparsity of the dates. And to me, it looks like the sparsity of the activations and the updates is more important to mitigate forgetting, the transfer, and so on. Well, I'm not sure I see a strong reason for sparsity of the weights. So I would like to, if you can give me an explanation of why sparsity of the weights is important, even apart from the effect on the activations and the updates.
Well, sparsity of the weights per task is important because it sort of frees capacity to learn future tasks, right? And so what we saw in this PACnet idea is that, sorry, I'm going to try and go back. Actually, only the very beginning is you have sort of sparsity for only that particular task. In the later forward pass, you would actually run the full dense network as you get forward transfer from the previous tasks. But the reason that it's important, it is effectively directly translates into gradient sparsity. Actually, the gradient sparsity mask is the inverse of this, right? And so they are inherently connected, basically. Yeah.
Are you working on task incremental settings?
So in the power propagation paper, we have results for task incremental, class incremental, all of these settings. In terms of the class incremental setting, there's one question you need to answer, that is, if you do the standard PACnet thing, you kind of have to decide at the end of learning which task you have at hand. And I put that at the end. There's a couple of answers of how to do that optimally. I'm happy to discuss more maybe later on, but there's a few ways of doing that. Supermask position is one idea. You could try and learn the task ID as an additional class, perhaps in a complementary learning system. Maybe that doesn't need to be a deep neural network. There's work on input-dependent sparsity patterns, and meta-learning people often have a task inference network. And so there's multiple ways of dealing with that. Yeah.
Okay. So the idea is that you have a different mask for each task,
yeah,
and you do task inference to choose them.
That's right. Yeah, and if you're sort of in an on-device situation where you might have a limited amount of data from each user, you can adapt the weights and the sparse mask at all at the same time, and then the meta-learning comes in. Is quite useful for that. Thank you.
Okay.
Hi, thank you for the talk. I just have a quick question on, in addition to like forward propagation of the information tasks, do you know of any methods that kind of can go back and retrain the first task to learn knowledge of the rest without, like, first of all, if you just change the weights, obviously you're going to affect the downstream performance of all the tasks that are based off of it. But then it seems kind of wasteful to just add more parameters for the first task. You know, that work on kind of global learning, like regardless of sequence.
Yeah, I had a similar question earlier. So this is kind of, maybe it relates a little bit to the question of how to forget, right? So this PACnet idea seems very aggressive, right? It completely freezes the previous layers. I don't think that's necessary. There's multiple sparsity algorithms that don't make that assumption and that simply are very parsimonious in their use, but allow these weights to change. I think if you allow yourself the luxury of having rehearsal data, you could actually adjust the mask for previous tasks as you learn new things, and that's how you might get backward transfer. Yeah.
What do you think about the connection between modularity and sparsity, and whether modularity could be promising research direction also for enabling sparsity modular learning, explicitly training networks that have from the beginning modular structure and independent, not shared parameters.
Yeah. This is quite a big research trend at the moment. Different from the standard weight sparsity, people might have these routing networks that are trained with an RL loss effectively. What it does is basically each example can take a very different path through your network, through different blocks, for instance. So that would be an explicitly modular way of doing it. I showed some work earlier on some of the Bayesian non-parametric ideas. So this is the Indian buffet process. This is effectively a prior for sparse matrices. And what they effectively, they implement this sort of modularity. Let me see if I can find that. Yeah. So they effectively implement this modularity on a more fine-grained level, but they also allow you to grow. So there's some of evolutionary approaches that came out in about 2017 or so in the continual learning setting. So I think that's incredibly promising. And maybe you can even think about initializing entirely new modules. And I think that had actually been done as well with Chinese restaurant processes. Yeah.
Hi, thanks for the talk. So we just saw that sparsity kind of helps in forward transfer, right?
Yeah.
And you were also mentioning the fact that there are sparse methods that do not freeze the previous parameters.
Yep.
For the ones that. So don't you think that this may impact on forward transfer? So that, for example, PacNet produces forward transfer because the previous parameters are frozen, so you can exploit something that does not change over time.
Yeah.
Right. So I don't know if you have any thoughts on that.
It's hard to answer that question without making assumptions of the task distribution, right? And it's a big question in continual learning. Like, I think the reason we effectively care about about catastrophic forgetting is because we think we will see the same task again. Otherwise, it wouldn't make sense. And if that's the case and you see the same task again, you don't want any forgetting. If it's a kind of a morphing of classes or there's some of tasks and they're somewhat similar, but they might change, then yes, maybe some forgetting is useful. It's very hard to answer the question without having sort of a particular application in mind. But you can do both, right? Yeah, sorry if I don't have a better answer. How are we doing in time? Okay, I think there might be a Zoom question here. Are you reading it out? Okay, yeah.
So could you comment on the difference between the described sparsity using approach and starting for the first task with a relatively small model and rather growing the model with additional tasks?
I think this relates to the lottery ticket hypothesis. A big question right now for the people who are interested in sparsity for, let me see if I can find the right slide. All the way to the beginning. Okay, here it is. Yeah, I think this relates to the lottery ticket hypothesis. If we knew at initialization what the sparse subnetwork is, we could just train that in isolation and we would never have to actually run the whole big model. And that'd be fantastic in terms of sustainability, energy use, and so on. There is some work on trying to find that winning ticket early on, but it's still far from doing as well as training the full network and then sparsifying at the end. So this is something that remains to be seen if we can get better at that, but obviously it would be useful if we can.
Okay, maybe I will the last one.
Okay.
Connected to my previous question and so on there also. What about a domain incremental task? So you said we assume that we encounter again the same task when we don't want to forget things, but there are also situations where you encounter again the same task, but with new instances, like in another incremental. So you want to update the mask now, but if you update the mask, you may have interference. How do you fix this?
I think the answer is the same. So that there will be methods that allow you to effectively very quickly learn the fraction of weights that you want to update, and then you can run that update, right? So there are these methods that will allow you to continue overwriting old knowledge right? And so just pick that method. Yeah, I mean, I don't think this like extreme freeze all the weight sparsity is something that you would use, necessarily in a practical system. It's something that looks fantastic if you get a great result out in a paper because you compute the average accuracy over all tasks. But I think as we move forward in continual learning and tackle more challenging results, the reason I emphasize forward transfer is because I effectively think that performance should be calculated on the data that we're actually seeing in our systems. And that might very well be a repeat of previous data, and then this is useful. But in practice, I think it may will almost be some sort of modification or mix of previous problems. And so we should let the task decide what to forget and what not to forget. And sparsity allows you to do that. Thank you. Thanks. Okay, it's now time for the third oral of the workshop. This is a very interesting paper that we selected because of the mainstream topic that we also discussed during the panel session. And so we have now the pleasure to hear directly from the first author, Olsky Ostapenko, that is a PhD student at Mila. And so please, Alexei, the stage is yours.
So yeah, I will introduce our recent work called Continual Learning with Foundation Models, a latent study of latent replay. And so in continual learning, we usually, what we want to do is we want to train our machine learning models on non-stationary streams of locally stationary tasks. And we use replay buffers to prevent forgetting usually. And so in this framework can result in potentially unbounded computational footprint, because we never stop training the potentially large feature extractor, and because we may always need to replay more samples as new tasks arrive. On the other hand, in the recent years, we have witnessed development of these models that we call foundation models. So these are models that are usually pre-trained on a very broad data distribution. And the promise of these models is that they can generalize, or they can generate features which are useful for a wide range of tasks.
Sorry,
sure.
Can you share the screen?
Okay. What do you do?
I think we are not sure. It's a what? Okay.
Sorry, no problem. So yeah, the promise of these models is that they can produce representations which are useful for a wide range of tasks. So this was shown, for example, in the recent CLIP paper, where this figure comes from, where they show that using CLIP features with zero-shot transfers compatible with competitive with fully specialized baselines. So the main question that motivated this paper was how can foundation models impact continual learning? So if the promise of foundation models is fulfilled, namely that they can generate useful representations for a wide range of tasks, then potentially maybe this can even lead to sidestepping even the problem of continual representation learning, because we can just replace our continually trained feature extractor with a foundation model or with a large-scale pre-trained model. And this is exactly what we did in our main setting. So the setting that we study is called latent CL. So we just replayed the feature extractor that is usually trained continually with a pre-trained model, and we just fix it. And then we train continually a smaller model on top of those features, which can be, for example, a small MLP or even a non-parametric model. And yes, so obviously in this setting, you will, this setting is much more compute efficient because you only have to train a much smaller model. So you don't have to backpropagate into the feature extractor. So yeah, The overall high-level goal of this study was to understand to what extent can we sidestep continual representation learning, and more specifically, the goals were or are to propose and motivate this setup of studying continual learning on top of pre-trained models. So the motivation here is because, first of all, this the rapid progress of these large pre-trained models, and secondly, is that experimentation becomes very compute efficient in this setting. So we leverage this compute efficiency also for studying interference, transfer, and forgetting as a function of data, what we call. So more specifically, what I mean by that is that instead of varying the algorithm for continual learning, we can fix the algorithm and just test our models on many different streams. So in this study, for example, we had 120 different data streams. Additionally, we are interested also in the relation between the upstream and downstream data distributions and the continual learning performance, as well as the relation between the pre-training regime and the final continual learning performance. As for the baselines, we use the latent ER baseline. This is training a simple two-layered MLP on top of features extracted from one of these foundation models and using latent replay. We also use end-to-end experience replay baselines, which is standard continual learning on top of raw data, where we also train the feature extractor, and we use a simple non-parametric baseline. So here in the non-parametric baselines, there is no forgetting by design, and no replay is needed. On the data set size, we distinguish between two different types of streams. So we have the in-distribution streams and out-of-distribution streams, and this is with respect to the pre-training data. So on the in-distribution streams are constructed from CI400 and CB200 data sets, and the out-of-distribution streams are constructed from cars and aircraft data sets. So this distinction is made based on whether the classes of the downstream streams are in the pre-training data, as well as on inter-class similarity measure. I will not go into detail on this, but you can come to our poster and we can discuss this further. So yeah, now I will present a subset of our results. So first of all, we look at the trade-off between the compute and the accuracy of end-to-end versus latent ER baselines. So the latent ER baseline is in orange and end-to-end is in blue. And so probably as expected, we see that on the in-distribution streams, there is no big difference in accuracy between these two baselines, despite the fact that end-to-end fine-tuning has much more capacity. But on the out-of-distribution streams, there is a big difference in terms of accuracy. And while latent ER strategy requires much less compute. Another interesting finding was that on the model level, we always found a latent ER model which performed on par with end-to-end fine-tuning, also on the out-of-distribution streams. So this motivated also looking into the ensembling of different representations coming from different pre-trained models, which we also explored a bit. And the conclusion from this maybe is that as this large-scale pre-trained models become better over time, we are more likely to have more problems that are in this in-distribution situation on the left, where actually doing end-to-end fine-tuning does not improve our accuracy a lot. Next, we looked also at, we compared metric-based baselines. So these are the non-parametric baselines, which are the horizontal lines here with latent ER. So on the x-axis here, we have the replay buffer size. So for the both stream types, what we see is that for the small replay buffer size, non-parametric baselines perform on par or better than latent ER. This is mainly because in latent ER strategy, we have the MLP that can forget. But for larger replay buffer sizes, especially for the out-of-distribution streams, latent ER performs much better. So here we have similar conclusion as before, namely that as pre-trained models becomes better, maybe because of domain-specific pre-training, or maybe because of pre-training on broader data distribution, we are likely to end up in the in-distribution situation. And this is where we may even relegate replay as a method of choice for continual learning. So as I mentioned before, the latent CL is very compute efficient. So this allows us to study continual learning where we on a large number of different streams. So each stream is, we obtain a stream by taking one of the raw data streams and encoding it with one of the pre-trained feature extractors. So I will give you a small overview of some results. So for example, we looked at interference and transfer here. So on the interference side, the interference is intuitively can be defined as how much worse does your model perform on each of these tasks that you have in your stream when trained IAD on this task versus when trained on each task separately. So there is no forgetting. So what we show on the left and the central plot here is that there is more interference in the OD streams. There is also more interference for larger replay buffer sizes. On the transfer side, we show that transfer is more important for smaller replay buffer sizes. We also looked at the role of pre-training, the broadness of the pre-training data and the pre-training regime. So as for the data set size, I think as expected, the more pre-training data you have, which is a proxy for the broadness of the pre-training distribution, the better will your model be on the downstream CL. And as for the pre-training regime, an interesting finding was that self-supervised pre-training resulted in better final continual learning accuracy on the out-of-distribution streams, despite being pre-trained on less data. So self-supervised models, for example, like Dyna, were pre-trained on ImageNet 1K versus supervised models were pre-trained on ImageNet 21K. And on out-of-distribution streams, self-supervised models, as well as DITE, which is a mixture of supervision and distillation, performed better. As for the conclusions, so can we sidestep continual representation learning? It depends a lot on the relation between the downstream and the upstream data. So if you can do domain specific pre-training and your representations are already good, then trivially you probably don't need continual learning anymore. You can just train continually non-parametric model, which doesn't have forgetting, but it relies on the fact that your representations are already good. But if you're not, then you need continual learning. As for the setting, so we conclude that latent CL is a very light setup, and I think it enables this studying continual learning as a function of data, which we think is a very promising research direction. And as for the long-term perspective, we think that we should keep in mind this tendency that large-scale pre-training gives us always better models, and that there is this danger that this might lead to sidestepping continual learning in some domains at least. So maybe one interesting direction could be finding ways or algorithms that generate features which are better for the downstream CL. As for the short-term perspective, we think that latent ER baselines, they can be improved by, for example, ensembling representations, domain-specific pre-training, obviously, or designing smart ways of using data-dependent metrics, for example, task similarity, to design better algorithms. Thanks for listening.
Okay, do we have some questions? Also from people attending remotely. You want to write your question in the chat, I can take that.
So you said that the head was a two-layer NLP, so in principle then there can still be some feature sharing between the different tasks, no?
Yes.
Did you notice this? Or did you...
So there is a two-layered NLP trained with experience replay. Whether there is feature sharing between tasks. No, we didn't analyze that in detail, but I guess on the in-distribution streams, there must be more feature sharings because of the good accuracy that you already achieve. No, it's single head with experience replay. Yes, yes, yes. So If that answers your question, or so I think because you have good accuracy on the distribution streams, there must be feature sharing because that means the representation is good for all of these tasks. I see, but there is interference. I see. No. The feature extra. So yes, in the classifier, yes. In the classifier, yes.
These are shared. So that
yes.
Still some forward transfer. Because if you only learn a single linear layer, there is no forward transfer.
Yes, for sure. There is, so in the latent ER baseline forward transfer is possible, yes, because you have two-layered MLP. We didn't evaluate forward transfer explicitly, but we looked at the interference, for example, and so in the in-distribution data set, the interference was smaller. That could mean that there is more features that are being shared, because if there, well, at least it means there are no features that are interfering.
Yeah.
I think we have a plot on transfer in the in-distribution versus out of distribution data sets. And I think, no, we'll have to look more precisely in that plot.
Any more questions? Okay, that's case. Thank you so much, Leslie, for the great talk.
Okay, so now we're moving towards the end of the workshop, and we will open now the chapter of the challenge. So we had this challenge based on the kindly provided a new dataset Ego4D by Meta, and it was mostly focused on detection. We mentioned several times that in this workshop that despite the interest in classification, object recognition, there's a strong, especially practical interest as well in the future of the field for detection and detection tasks. And so this was one of the first, I would say, challenge, trying to assess, let's say, the maturity of recent methodologies that can be used for the tasks. So it was quite large scale with respect to previous attempts. And so I think we can now hear from directly from the videos that we prepared from some of the challenge participants and the challengers to learn more about the challenge and the main, let's say, methodologies developed. Then at 5:40, more or less, we will announce, let's say, the winners, and we give the awards for both the challenge and the overall workshop. Okay, so first of all, I would like to thank all the people involved in the challenge. It was a strong, let's say, commitment, and especially Lorenzo Pellegrini, who is still a PhD student at the University of Bologna, and was the main, let's say, challenge lead, and then also Jing Chang here from Meta, as well as Jia Chen, right? That helped very much in the organization of the challenge. And so I don't know, we have the video from Lorenzo, or Jing Chang, do you want to say something, or do you want to play directly the video from Lorenzo?
We'll start with the opening remarks of Lorenzo. So we record the video after Jing Chang will be alive.
Okay, great. Sorry.
Okay. Yep. This is the one. I don't understand. It's hard to just please because of no Zoom is okay.
I do think because we reconnected that way. So like a thing like 6 is a host.
So maybe this one is not the host anymore. I don't know. There's a mic on.
Jeremy, I hate to interrupt you. I just wanted to give you a card real quick. I put a paper here. It's like a lot to do with what you were asking about earlier with the sparsity. So I just figured I'd pass it along to you.
Yeah, thank you. I will
Yeah,
check it.
of course.
Jeremy?
Jeremy, yeah.
Okay, sorry, just one few moments to fix the output audio.
Nice to meet you. Mind if I scan your speech?
It's really weird.
Cool. Feel
Does it
free to
work?
send me an email. Let me know if you like it.
Yeah.
Maybe we can just remove these and move the mic.
Yeah, I can do that.
We want to remove these and use the mic. Maybe.
Do you have set on your? Oh, the video has been set.
Something with the connection.
No, I don't know what's happening.
Try another video. Just to make sure the video has the audio.
Yeah. No, it's a problem with the audio settings. I don't know.
Try spoons.
It's still playing. No, or maybe it's a problem with Zoom. Yeah, because
Strange.
yeah, like Zoom is taking the output. Okay, how do I open the
Maybe I can check.
Faster. It's definitely very hard to find it.
And earlier today, we haven't played sound from the laptop.
Oh wait.
We haven't played the sound from the laptop.
Oh, okay.
We didn't try that.
That's it. So it's not playing on the laptop.
Yeah.
Okay, wait. Maybe
So
now it's disconnected and that's like no.
Oh, I mean, already in the previous presentation, earlier today, we haven't played the sound from the laptop.
Yeah, but we tried it in the first one.
Hello everyone.
Okay.
My name is Lorenzo Pellegrini and I'm happy to open the presentations for the challenge.
Let's try.
First of all, let me thank the workshop organizers for their great job in making.
Okay. Okay, I don't know. It was at the max. Okay, it's fixed. But I'm not sure if I'm hearing it through here.
Hello everyone. My name is Lorenzo Pellegrini and I'm happy to open the presentations for the challenge. First of all, let me thank all the workshop organizers for their great job in making this workshop a reality. I know that it's not an easy task to organize these kind of events, and I hope.
I mean, we can use it like this.
You don't have to. Okay, tell them to go ahead and talk. Play the video.
Everyone is enjoying their presence here. And let me especially thank the challenge co-organizers. In the last month, we worked very hard to push the challenge. We already received a lot of appreciation messages, and no matter the outcome, I hope this has been a great experience for all participants. This year's challenge has been co-organized by Zicheng Yan and Chenchen Zhu from Meta, and me, a PhD student from the University of Bologna. As you can see, I am not able to attend in person as I have a meeting with for the moment, let me.
It's a computer. Oh, you're still gonna use the computer?
Yeah.
You can't put it on a different.
You can put it?
No, I'm saying you can't put it on a different
Well, it's
laptop.
okay. I think that ARC was enough, right? Just to speed up.
The problem is that we have to move the video.
Yeah.
It will take a bit of time. Yeah, it's okay. So.
Alright. I don't want the feedback. Check, check.
Thank you.
Still very, very hot. Sorry about that.
No, no problem. Thank you. Okay, we're back on track. Sorry about the technical problems. And so let's see the summary prepared by Lorenzo.
Hello everyone, my name is Lorenzo Pellegrini and I'm happy to open the presentations for the challenge. First of all, let me thank all the workshop organizers for their great job in making this workshop a reality. I know that it's not an easy task to organize these kind of events, and I hope everyone is enjoying their presence here. And let me especially thank the challenge co-organizers. In the last months, we worked very hard to push the challenge. We already received a lot of appreciation messages, and no matter the outcome, I hope this has been a great experience for all participants. This year's challenge has been co-organized by Zicheng Yan and Chenchen Zhu from Meta, and me, a PhD student from the University of Bologna. As you can see, I am not able to attend in person as I have commitments related to my PhD defense, but I'm looking forward to meeting with you during the next year. And for the moment, let me just spend a few words about the competition and why this is so important for our research field. And then I leave the microphone to Chen Chen that will explain the data set and the challenge tracks in more detail. The presentation is split in two parts. And in the first part, we will try to explain the data set, the tracks, and we'll show you some technical, interesting facts about the challenge. We'll then leave the microphone to the challenge winners so that they can explain their solution. And for this year, we opted for 10 minutes presentations. We hope that by giving them 10 minutes each, they will be able to explain their solution and the ideas behind them in more detail. This is the third edition of the workshop, and in each edition, a different challenge has been proposed. These have been a great way to push the limit of continual learning, and in each year, the focus is put on a different aspect, on a different element of novelty. Apart from the more novel tracks, however, these challenges feature a more classic supervised classification track, and in addition, a different data set is used in each edition, which makes all these challenges unique. For instance, the first edition of the challenge was based on the core 50 dataset. In that case, a challenging track featuring 390 incremental training experiences was proposed, while the challenge held at the second edition of the workshop featured a novel continual reinforcement learning track based on the Monster Comp video game. As you can see, novelty is a huge thing in these challenges. For this year, we propose a challenge featuring 3 tracks, with the continual object detection tasks being the novelty aspect of this challenge. The continual object detection field is becoming more and more popular, so we use this occasion to push research in this direction. We do this by using a novel, large-scale dataset designed with continual learning in mind. This is a huge step. This is a very important resource because this dataset is huge. It features 1,110 unique objects. And speaking about objects, we also introduce another aspect of complexity, which we deem very important, which is the instance versus category recognition. And for this year, tracks feature object classification and detection tracks at different granularities. So depending on the track, we ask participants to provide a solution able to distinguish objects either at the category level or at the object specific level. So I think we here call instance. And finally, another goal of this challenge is to close the gap between academia and industry. So the industry is betting more and more on continual learning. And we think that this challenge can be a good occasion to close the gap. I now leave the microphone to Chen Chen, who will describe in detail the dataset and the challenge tracks. I want to thank you all for your attention, and I'm looking forward to seeing you in person during the next year.
Okay, that's great. That was the summary prepared by Lorenzo. Now we have Chen Chen here. I can take the lead and explain something more about the dataset. Just a quick correction. It's not the Ego 4D dataset, but the Ego object that is a different one and was specifically, let's say, tailored for the challenge.
Yeah, let me. How do I close the? I just drag it down the window. No, they just the window. Get that. It's cool. Hide. Hide. No, I don't. I did it. Okay. No, it's different. Oh, here. Okay, this is what I can go to the. Yeah. Okay. Okay, thanks Lorenzo for the introduction. And you can see this year we are focusing more on the egocentric object understanding, where we build the ego objects dataset, which is the first massive scale egocentric dataset for objects. So the motivation to build such a dataset is that existing egocentric datasets are either not object-centric or not large-scale. For example, we compare our datasets with other recent egocentric datasets. For those egocentric object datasets like Epic Kitchens, Objectron, and Code3D datasets, normally they may have a few number of categories, or they may have limited video sources. Whereas in our dataset, we have up to 600 number of categories, and our video source is from multiple devices. And for the recent large-scale egocentric dataset like Ego 4D, it's not object-centric. So in that case, there's limited annotations for the objects. And in our ego objects dataset, we use diverse capture devices, including 3 types of AR glasses, and also the mobile phones with ultra-wide lens to simulate the egocentric viewpoint. Here I show some example videos from our dataset. So each video featuring one main object as shown as the plotted plan in those videos. And those videos are, for each main object, we collect like 10 videos on the 3 different settings. On the different settings, including like 3 levels of camera to object distance, 3 camera motion directions, 2 levels of background complexity, and 2 levels of lighting conditions. Also, for besides the main object, you can see there are a lot of other surrounding objects in each video. And in terms of the taxonomy, we have a large taxonomy with multi-level granularity. So for those main object categories, we have like more than 200 categories. And for all the other surrounding object categories, we have up to 600 categories. For each video, we also provide rich metadata information, including the detailed description of the surrounding environment as a background, and also the device type, as well as the country locations, and etc. So for this challenge, we hide some of the informations to prevent the shortcut solutions. And in terms of the annotation, we annotated 2D bounding boxes of the objects with both category labels and also the instance IDs. In this case, we can not only distinguish between the categories, but also the multiple instances of the same category. And for those main objects, across all the 10 videos, the main objects will share the unified category and instance ID. And for those secondary surrounding objects, they will share the unified ID across some videos, but may share a different kind of ID for in the other videos. And we use the Halo 2D video bounding box tool developed by Meta for the annotation. And for this challenge, we released a challenge version of the dataset with a total of 277 number of categories, with like more than 1,000 main objects. And there are like more than 3,000 overall objects in both the training set and the testing set. And we also visualized the statistics here, like the number of images or annotations per category. You can see it's more like a long tail distribution, which makes the problem more challenging and also real world oriented. So our dataset can support 3 different challenge tracks, including 1 classification track and 2 detection tracks. And for the instance classification track, we set up the dataset as class incremental learning with 15 experiences. And for the category detection track, we set up the dataset as the data incremental learning with 5 experiences. Finally, for the instance detection track, we set up the dataset as a class incremental learning on all the more than 1,000 objects. So for track 1 and track 3, the main instance is the only target object. And for track 2, we create this experience by the class incremental style on the main objects, but also we included the annotation of other objects in the video. So technically it's more like a data incremental learning. We used the popular average mean class accuracy as the metric, AMCA as the metric for the evaluation. And for the classification track, we average the classification accuracy across multiple experiences. For the detection tracks, we average the MAP across experiences. So in this challenge, we don't allow training during the test time, so no GDOM style approaches are allowed. And we give very generous prices for the challenge, including a total of $10,000. Because the goal is more focusing on continual learning in a detection setting. So we give higher prices for the track 2 and the track 3, which are detection tracks. And it turns out we have a huge participation this year, especially for the more classical classification track. In total, we have around like 37 participating teams with more than 300 valid submissions. We didn't expect to have many teams participating in the detection tracks because the tasks are kind of new, but we still have more than 10 teams on both the category detection track and the instance detection track. And also we observed that the submission for the third track ramp up during the last few weeks, which indicates a good participation. And here we visualize some of the participation over time. You can see on the in the first track, we have very active participation from the beginning of the challenge to the end. And this is the second track. And for the third track, we have the least number of submissions, but in the end of the challenge, we have observed more submissions. To summarize the submissions, all the teams are using maximum replay buffer size, and the distillation-based method like LFW or LFW style is widely used. And due to the rise of the VIT models, many solutions are using recently published vision transformers. For example, in the classification track, some methods are using the Twins SVT backbone, while others are using the CNN-based backbone like the RegNet X. For the detection tracks, the submissions are more diverse. Some teams are choosing different kinds of detector architectures like the fast RCN, FCOS, and varifocal net. So both anchor-free and anchor-based detectors, as well as both single-stage and two-stage detectors. And for the backbones, most teams are using the CNN-based backbones like the ResNet, deformable convolution net, and the Res2 net, etc. Okay, without further ado, I think it's time to announce the winners of the 3 tracks. So we would like to congratulate the U2 Fuxi CLS team, Baseline CL team, and the Fantasy 9A9 team on winning the instance classification track. And congratulations to the U2 Fuxi DET team, NUS LV Lab, and the A-star team, as well as the USTC IAT United team on winning the track 2 category detection track. And also congratulations to the U2 Fuxi DET team, the NUS LV Lab and the A-star team, and the Angelo Meneses team on winning the third track, the instance detection track. Congratulations to those teams. So here we show like more detailed second level details for each team. So here we would like to congratulate Jiawei Zhang from the Tencent U2 Lab, Tao Xu from the Institute of Automation Chinese Academy of Sciences. For the third track, we need to confirm the team members in the future. So for the category detection team, category detection track, we would like to congratulate to Jing Xiang Lai from also the Tencent U2 Lab, and Xinyi Yang from the National University of Singapore, and other members. Some members are from the A-star, and the third place is congratulations to Junyu from the University of Science and Technology of China. And for the third track, it turns out we have the first top two teams from the same team member. Yeah. For the third place, we would like to congratulate Angelo Meneses as a solo player. Yeah, congratulations to those teams again. Okay, so next, let's give the stage to the winners to present their solutions. So first, we have the winner of the instance classification track. We have unfortunately they cannot join the meeting, so they pre-recorded a video to present that. No, sorry, this one.
Hello, everyone. First of all, thanks to the chairs for organizing the CLVision challenge. Our team belongs to Tencent U2 Lab, Shenzhen, China. I am Zhang Jiawei, and here I will introduce the solution we used for this competition from 3 aspects. The first part is about the dataset analysis and augmentations. The second part is the network and architecture of our solution. And the third part is about some important continual learning strategies we have outlined. Then there are some implementation details and finally some summaries. As we all know, deep learning is data-based learning. Thus, the processing of data is very important. Since the training input is restricted in benchmark to be read with a force size of 224, there is no significant gain from setting a larger scaling size in the data transformation. And we use augmentation to perform most data augmentations, including shift, scale, rotate, blur, distortion, and noise. Besides, due to the characteristics of the dataset, many samples from different categories were semantically close to each other. It was even difficult to distinguish whether some cases were the same instance or not. So we consider letting the model to exploit brightness, contrast, and hue to assist in classification. We turned off those augmentations and found that these improved the overall performance by about 1%. In addition, These like augmentations methods, such as cut out, mix up, cut mix, and mosaic, did not achieve performance gains in our experiments. So we decided to deactivate these strategies in the final delivered solution. Regarding the selection of models, we initially pulled the table of imagined pre-trained models directly from TIMM GitHub, sort them based on top 1 accuracy, and strictly selected the models that met the requirements of the competition. Note that we try other models with small differences in top 1 accuracy from the table. After all, the data distribution may be varied, and a model that works well in other datasets may not work well in our ego object datasets. In the end, the twins SVT-based model stood out, which is an improved version of the PBT model. The reported top 1 accuracy on ImageNet is 83.2%, and the number of parameters is 56 million. As a result, we directly use the model and pre-train weight from their website as our baseline. The final fully connected layer was replaced with 1,110 categories to match the number of categories in a competition dataset. Regarding continual learning, which is the core of our competition, we analyze through upper bound to allocate our effort for generic classification and continual learning. Specifically, we calculate the performance supposing that continual strategy is perfect. That is, supposing that no catastrophic forgetting occurs at all. The gap between this metric and the current result is the gap of continual learning, while the gap between this metric and 53.3% is the gap of generic classification. By using the result, we can determine whether we should currently spend more time on generic classification or on continual learning. Our overall solution consists of the following modules. Firstly, the training data of the current experience is generated by experience-aware buffer management. After that, the training of the feature extractor and classifier is performed. The wave fusion between experiences is performed by experience-based CWR++ after training is finished. The training process uses experience-oriented learning rate decay to elevate the catastrophic forgetting among experiences. Now, invite my colleague Zheng Yi to present the details of the implementations of these modules.
When training deep neural networks, it is often very useful to reduce the learning rate as the training progresses. Previously, this technique was only used between different epochs within the same task. However, we find that after the first experience is completed, the feature distribution of the model has not changed very much. As a result, using a large learning rate in the later experience has a higher probability of forgetting old categories due to randomness. So we propose to gradually apply a decay to the initial learning rate between experiences. This strategy leads to a little improvement in the average accuracy. It is known to us all that replay is one of the most effective techniques to tackle the problem of catastrophic forgetting. Therefore, this strategy is very essential to our solution. In this challenge, the replay buffer can only contain a maximum of 3,500 training samples. Under this condition, we find that in the early experiences, no matter we make the samples in the replay buffer balanced over experiences or classes, it is able to significantly reduce the problem of forgetting old classes. However, in the later experiences, there emerges a performance drop in the classes belonging to the earlier experiences. This implies that old class forgetting starts to show up during the training of the later experiences. Based on this observation, we propose a novel buffer management strategy termed Experience-Aware Buffer Management, short for EBM. Specifically, under our EBM, the number of samples for categories belonging to the same experience should be equal. As for classes for different experiences, we should treat them differently, considering that classes from earlier experiences are more easily to be forgotten. In our experiments, between two adjacent experiences, our replay buffer will take 25 more samples from the earlier experience. We have also tried other numbers instead of 25 and find that there is little difference. So our EPM is not very insensitive to this hyperparameter, and we just take a reasonable one. Copying weights with init, called CWR for short, is proposed in this paper. This method performs very well, in spite of its simplicity. CWR maintains two sets of weights for the classification layer. CW is a consolidated weight used for inference, and TW is a temporary weight used for training. CW is initialized to 0 before the first experience, while TW is randomly reinitialized before each training experience. At the end of each experience, the weights in TW corresponding to the classes in the current experience are scaled and copied to CW. This strategy works in scenarios where the classes between different experiences are completely segregated. To avoid annoying tuning hyperpump WI, CWR plus is proposed in this paper. Two major improvements are introduced in CWR plus. They are zero initialization and mean shift. For more details, we refer readers to these two papers. In this challenge, considering the overlapping of categories between different experiences caused by using replay data, we improved on the basis of CWR plus. In contrast to CWR plus, the weights in TW corresponding to the new classes in the current experiences are also scaled and copied to CW. But for all classes present in the replay buffer, a moving average is calculated using CW and TW. The weight of moving average is a ratio of the number of training samples when the class first appeared to the number of training samples corresponding in the current replay buffer. Our experience-based CWR double plus works at the end of each experience and can greatly elevate the forgetting of old classes with little impact on the accuracy of new classes recognition. It is very useful on longer sequences of tasks and can be seen as a simpler and lighter counterpart to PNN with a fixed number of shared parameters. In addition, we find that it is better to not freeze the weight of the feature extractor in our experiments. The average accuracy is about 1.2% higher than using freezed ones.
Regarding the training process, we use the SGD as the optimizer. The specific details of the parameters are listed here. Note that we use the cross entropy as the loss function, and we train the network with a label smoothing of parameter alpha, obtaining considerable performance gains. The training was performed on an NVIDIA Tesla V100 GPU and could be completed in less than 10 hours. The video memory used for training was approximately 11 gigabytes. And let me conclude with a brief summary. In this work, we investigate the problem of continual learning from semantically similar data streams of a large number of instance classes. In addition, we propose experience-aware buffer management to address the potential forgetting problem in long-time continual learning. Then, we propose improved CWR methods to solve the fusion problem of classification heads based on replay. And we also provide data augmentation and learning rate scheduling methods to improve the performance of the model. For more information on contribution of each module, you can view the diagram on the left, which will hopefully be of some help and inspiration for future research. Regarding our failed attempts, which can be seen on the right, this doesn't mean that these methods are not valid. but rather that they are not quite applicable to this domain or this dataset. And that's our presentation for today. We hope you will stay tuned for the rest of our lab's research. Thanks so much.
Which one is it?
Yeah, so for the track 2 and track 3, we actually have the same winner from also from Tencent U2 Lab.
This is the presentation of first place solutions for CLVision Challenge Track 2 and Track 3, which are continual, category level, and instance level object detection, respectively. Our solution is called NVFnet RDC, Replay and Non-Local Distillation Collaboration for Continual Object Detection. I'm the presenter, Jingxiang. Our team members for Track 2 and Track 3 are as follows. We are from Tencent U2 Lab. Firstly, we will give a brief introduction for Eagle Objects dataset and benchmark setting. Then we will introduce our solutions for CLVision Track 2 and Track 3, experiments and failed attempts. The challenge is supported by the Eagle Objects dataset provided by Meta, a massive scale egocentric dataset for objects, which contains around 70,000 images for training and 10,000 images for testing. Videos feature a great variety of lighting conditions, scale, camera motion, and background complexity. Video frames have been sampled and annotated with rich ground truths, including object category, object instance, and bounding box. According to our observation, images of train set and test set are from the same themes. These are some images from train set and test set, which are from the same themes. Both Track 2 and Track 3 are belonging to class incremental object detection. Since these two tracks are very similar, our solution is general for both of them. The evaluation metric is average NAP. Specifically, for each experience testing on whole test set, the MAP is calculated. Then these 5 results are averaged to get the final score. Our solution is called NVFnet RDC. We propose a NVFnet detector, which consists of VFnet and non-local dense classifier. We propose a continual learning approach named RDC, which consists of replay and non-local distillation. Other components include REST2 backbone retrained on COCO and photometric distortion data augmentation. Overall, the framework consists of feature student models and adopts replay and feature distillation strategies. The one-stage VFnet is chosen as the base detector. It uses a dense classifier, which makes classification for each pixel of embedded features. We propose a NVFnet detector. We are modifying the dense classifier of VFnet into a non-local dense classifier. Specifically, a non-local module is inserted into the dense classifier. This is the non-local module. Given input feature to non-local module, it models the relationship between instances, which is able to improve the accuracy of pixel-wise classification. This slide shows the used replay strategy. Replay rules are as follows. The replay buffer contains up to 3,500 for check 2, 5,000 for check 3 training samples. The buffer must be initially empty and can be populated using data from the current experience only. This means that the replay buffer cannot be populated beforehand, nor it can be filled with data from future experiences. The only samples from past experience must be the ones chosen before terminating the training on that experience. On the below is our replay buffer. Task 1 to task 5 are the 5 incremental tasks. Data 1 to data 5 are the chain sets for the corresponding task. The training data for each task is shown in each column, which contains current data and replay data. Best view in color. Orange is current data. Yellow is replay data. As we can see the replay data for each task, the same amount of data is sampled from the previous task. We use video-wise random sampling to obtain the replay data, which selects the same amount of samples from each video. Here, we introduce the detailed NVFNet RDC framework. With the replay strategy, the input data contains current data and replay data. There is a teacher model trained from previous tasks, which consists of REST2NET backbone, FPN NAC, and detector heads. This is the student model needed to be trained for current tasks, which has the same structure with the teacher model. Along with the conventional supervised loss, we further apply non-local distillation for the features generated by FPN. Specifically, the non-local module is utilized to model the relationship between instances for the input features. Therefore, it distillates the relation features, comparing to the directory feature distillation. The non-local distillation is a weak feature distillation, which enables the model to learn a more discriminative embedded features for current tasks, and also alleviates the forgetting problem. Next, we show the experiments for check 2. Table 1 shows the improvements achieved by different components. Best view in color. Green are the detector components. Purple are continual learning strategies. The right side are the results, and we mainly focus on the average results. The first row is the baseline without any continual learning strategies. The second row shows replay improves around 15% than the baseline. Cocoa per chain improves around 4% than using ImageNet per chain. Now local distillation improves near 2%. Now local dense classifier improves around 0.5%. Photometric distortion data organization improves a little bit. The deformable REST2NET backbone is around 2.5% higher than REST-NET 15. This is the experiments for check 3. The proposed replay and non-local distillation achieves around 9% improvements than the strong baseline. This is the ablation study of different detectors and backbones for check 2. Table 3 shows that, first, VFNet is the better detector than others, such as faster RCN, ATSS, FCOS, and GFL. Second, the performance of REST-NET 15 and SwingT are pretty much the same. This is the ablation study of different distillations for check 2. Table 4 shows that, first, non-local distillation is better than others, such as directory feature distillation and feature attention distillation. Second, logic distillation is not helpful upon feature distillation. Here are some failed attempts for check 2. The popular DETR and default DETR are time-consuming. Multi-scale data augmentation is not effective, and Mosaic causes performance drop heavily. The long-term strategy class balance is not effective. Adding scene or video classification branch causes performance drop heavily. Well, thanks for listening.
Okay, thanks the team. So next let's welcome Xinyi Yang from the National University of Singapore, and he's joining virtually. So welcome Xinyi to give the presentation. Let's share the screen. Stop.
Oh, yeah. Okay. Is he online?
Yeah.
Should be able to share the
Yes,
screen.
Xinyi, can you share the screen, and we will leave the stage for you. Oh, seems like we have some questions. Do they provide the? So we are allowed to pre-training. So for pre-training, we are allowed to pre-train the networks on either ImageNet or Coco or Elvis, and I think they can just grab the pre-trained model directly from those data sets and use to plug in their methods. It is mute. I try to call Xinyi.
No, it's not muted. I don't know why.
Is he co-host?
He's in China, like in the middle night. Yes, he's in the Zoom meeting.
We can host.
If he's not responding, we can also play the pre-recorded video from
Okay.
his team.
Let's see if you can answer.
Yes.
All right. Now we should be able to open the mic and the camera. Yes.
Hi, Xinyi, you are right now. You can unmute yourself. Previously, there's no permission, so can you try unmute yourself and share the screen? I don't think he's
Okay, maybe we can use the share the recording. This one? Okay.
Hello, everybody. My name is Xinyi Yang. I'm a first year PhD student at National. University of Singapore, under the supervision of Professor Shenchao Wang. And I'm glad to have this opportunity to share our solution for the second and third track for the continual learning challenge. And our topic is a strong baseline for continuing object detection. Our presentation will be roughly divided into 3 parts. First, we introduce the challenge and the dataset. Then we elaborate on our method, and mostly on the category detection track, and the same strategy is applied to the instance one. And we'll discuss the limitation of file method. We participate in second and third track of this year, and it involves over 6,000 videos and 70,000 images in total. And for the category detection track, it has 277 categories, and for the instant detection track, it has 1,109 categories. The whole data set is divided into 5 experiences, and different from the conventional setting for the class incremental learning settings. In this challenge, we are using a sample incremental setting, and we the maximum replay buffer is 3,500 images, and the model size is limited to 70 megabytes. And we first visualize the dataset itself. We see some the scenes and objects are quite repeated because the images are sampled from video recordings. And we also see a large variation for the illumination. Some of the images are under low light conditions, and with various of image qualities. There is a blurs, low resolution images, and large motions, or also compression artifacts. And we also see the long tail patterns in the category detection tracks. Maybe the plot on right-hand side is the sorted category ID along with its images numbers. We see quite long tail patterns and of extreme data imbalance. So let's get down to our solution. First, we apply the process and with the fixed backbone for the 5 experience trainings, and we implement with the MM detectors. And through the 5 experience, we can see that there's no much improvement alongside the trainings, and we can only get to around 17 mean average precisions. We see that some of the instance learned in previous stages are forgotten in the next stage. So we resort to a multi-head strategy. And in previous papers, there has been attempt to utilize a multi-head strategy that train multiple heads for each experiences with the shared backbones. And in our implementation, we use the shared backbones, but different regional proposal networks, different feature pyramid network, and different ROI head. It can largely eliminate the forgetting problems in continuous learning setting. But more head means more parameters. If we just use the original implementations, the overall model size is over 100 megabytes, but the limitation is 70. So we dive deep into the model itself, and we see that the major parameter costs come from the ROI head, because it has a full connector layer to downsample the 7x7 feature map to vector. So we replace the full connector layer with the average GUI, and we also replace with reduce the number of full connector layer to some convolution layer, and it results to a model with 5 heads, but with a parameter of 65 megabytes. And we train this model on the legal object data sets, and without the forgetting problems, the model achieves 39 mean average precisions, and it's a tremendous improvement from the single head strategy. Then we want to come up with better loss function, better proposals, and better backbones. First, we want to address the data imbalance problem. We use seesaw loss to mitigate these problems. The seesaw loss also was originally designed for the long tail segmentation problems, and it decreased the gradient for the negative samples to prevent some majority class dominate the gradient. So that's the first loss function. And for the regression loss function, we use the GLU loss, and instead of using the L1 or L2 loss for the coordinate regression. And for better backbones, we use deformable convolution operations, and it has some offsets parameters to get rid of the traditional rigid convolution operations. So and do not introduce very large computational cost for the backbone. Then we want to get better proposal and anchor boxes for the fast RCN model. So we we adopt the guided anchor strategy. And instead of using the predefined anchor boxes that uniformly sample from the images, the guided anchor just predict the anchor boxes from the feature maps. So it adaptively fits the data sets. Yes. And with the above mentioned modifications, we can further improve the mean average precision to 43 points, and for now we have our full model. So we want to get more on the data sets. So we apply strong data augmentation to our trainings. We use shift augmentations, and we apply random brightness and contrast to the images. And we also apply RGB shift and hue saturations on the data sets. Because a lot of images are of low quality in this benchmark, so we apply the JPEG compressions and a lot different blurry operations on the image to mitigate this problem. And we also use the multi-scale training to reshape the images with a height from 640 to 800. And we also use a balance sampler for the training that we oversample the minority classes. And another direction for continual learning is to selectively apply the replay buffer and save them for next stage training. So for the track 2 and track 3, we use two different strategies. For the track 2, we select the minority category in each experience as the replay buffer for the next stage. And we empirically see that it works well, and it can also be seen as an oversampling strategy. And for the instance detection track, we select one frame or several frames from each videos as the replay buffers, because it was based on the fact that the data set contains some repeated scenes and objects in each video sequences. So in our implementation for the 3500 replay buffer, we oversample it by 5 times to make the replay sample of this similar quantity as the training sample for each experience. And with the strong data augmentation and the replay buffer, the performance can be improved to 48 mean average precision. And then we want to better regularize the model. And the very strong method is the pre-training. And because we apply a lot of modification to our models, and we trained from scratch on COCO 2019 train set, and it improves for the second row, we can see that our method can achieve 44 mean average precision on COCO 2019, and it improves the simple fast RCN baseline by 7 points. And if we allow for longer training time, it can be further improved. We also want to apply a better backbones like the swing transformer here, but we see that the ResNet 15 model with the deformable convolution provides a decent baseline already. So we do not include the swing transformer model in our final submission. And we fine-tune the 12 variable on the Eagle object datasets, and we see that it further improved by 5 points in mean average precision. Next, we apply two tricks on the training. First is the exponential moving average. It uses the parameter average for evaluation, and it can be proved that it finds better flat local minimums with better generalization performance. We also apply the drop blocks. It randomly drops some maximum feature blocks to avoid overfitting. So we apply it to the third and fourth stage of the ResNet fitting. And with all above method, the model, the data process, the data augmentations, we can reach to our final submission of 55 mean average precision. So we apply the same strategy on the instance detection track, and we also rank the second for the final evaluations. And for the full model, we can see that from the very simple Fox assay and baselines, we add the multi-head strategy, we add better loss functions, the deformable calculations, and guided anchor regional proposal. For the data perspective, we use replay buffer and data augmentations. And we also use strong pre-training method and use some advanced regularization techniques like drop blocks and EMA. And the performance steadily improved to our final submission. And thank you for listening. And if you have any questions, please feel free to bring it up. Thank you so much. Thank you.
Can I switch to the
Thanks for the presentation. CVPR. So the question is about the pre-training. How is that part? So do you pre-train just take how you train the example?
This is a question for CG, right?
Yeah.
Let's see if we can. Okay. Okay. Yeah, he's here, but we see he has a muted mic, so I don't know if he's still there. Yep.
He's typing.
Yep. Oh, if there's
we have
the chat. Okay, no, we don't have any new message. Well, so in the meanwhile, let me also thank all the Avalanche maintainers that helped a lot in supporting the challenge and introducing within Avalanche the reference library that supports the baselines. Also, some support in terms of detection that is quite difficult, we know, in terms of computational effort and tools and metrics. And so thank you so much, and people and Meta as well that contributed a lot to make this happen. And Lorenzo Pellegrini, who really spent a lot of time fixing bugs last minute, introducing new features. So that was great. And now I think within the latest release of Avalanche 2.0, this is now just a big package, right, that you can use directly. There is already some support for detection. Okay, so we don't have any news from CG, so I think we can thank as well Chen Chen and Xing Chang, everyone that helped support the challenge, and we can move to the next part of the workshop, the closing remarks and the awards announcement from Matt. Thanks.
All right, so thank you everyone for being part of this amazing workshop today. We're now here for the awards and the closing remarks on the workshop. So let's dive right into the Best Paper Awards. The first Best Paper here at the workshop is Continually Learning Self-Supervised Representations with Projected Functional Regularization. So let's congratulate the authors, and they can come to the front for a picture. So they win an NVIDIA GPU and $500 from ServiceNow. All right, so we just should take a picture, maybe the
Hey, this is also quite valuable.
Right.
Do you want to be?
You set or you do, you should make sure that it's good. Okay. All right, so time for our next award with $500 from the Matrix project. The runner-up paper award. So the authors of Towards Exemplar-Free Continual Learning and Vision Transformers, an account of attention, functional, and weight regularization can come to the front. And let's give them also a very nice applause. Also, again.
Yes.
Yep, that's right. All right, and our final runner-up paper award is it spacing loss for discovering novel categories. So let's also give them a very nice applause. All right, so for those who still have some time after the workshop, Today is also like a US holiday on commemorating the end of slavery in the US. So it's a very big deal here in the US South. So you can join New Orleans in the celebrations. We encourage you to do so. You can find more information for this also on the CVPR website. So we really want to thank all of the speakers that were part of this workshop, that has some amazing content, also joined in the panel session. So let's also give them a very warm applause. Also our sponsors who made it really possible for supporting us in this workshop, and also with the prizes here. So that's also like our sponsors. And then there's a whole team behind the workshop. So there's a lot of people here. Most of them have joined online, but an amazing team here. Vincenzo Monaco, Tonio Carta, Zicheng Yan, Shenzhen Zhu, and everyone you can see here. So it was amazing working with all of you, and it's been amazing collaboration. And let's hope we can go for future editions as well. So, so thank you to all continual learners. For anyone who is interested in having an informal drink, you can just stay here to hang around, and then we can determine wherever we go. So thank you all for participating.